On our planet, which has existed for more than 4.5 billion years, the history of Earth is filled with extraordinary and often mysterious events. Initially, it was a molten, lava-covered world with toxic gases in its atmosphere, devoid of oxygen. It took billions of years for oceans and continents to form on the surface. During this time, mountain ranges like the Himalayas and Alps emerged as a result of tectonic plate collisions. Furthermore, over the course of millions of years, Earth underwent massive changes. Climate shifted, mass extinctions occurred, and new organisms filled the vacant niches. Ancient oceans teemed with primitive life forms that gradually evolved, but human existence in this context is but a fleeting moment. When the first primates began to develop in tropical forests, continents were already inhabited by diverse animals, including dinosaurs, mammals, and many other groups. These giant reptiles dominated the planet until their mass extinction, after which mammals occupied the freed ecosystems. Time passed, and the ancestors of humans appeared, beginning to use tools and develop language. It is difficult to imagine that the billions of years of the planet's existence are reduced to the brief existence of humanity, which appeared only in the final chapters of this vast book. A significant aspect is that for the majority of its existence, Earth was lifeless, and all changes in ecosystems occurred over millions of years. The first civilizations emerged only a few thousand years ago, when people learned agriculture, began building cities, and organized complex societies. This was but a moment in the cosmic time frame, when the planet still had vast forests and many species, such as mammoths and saber-toothed tigers, dominated the ecosystems. Throughout human history, we observe how people adapted to their environment, from the first herders and farmers to modern urban dwellers who build megacities. In this context, it becomes clear that humanity, despite its achievements, remains a small episode in the long history of our planet, shaped by billions of years of geological processes. Each time we look back, we see traces of ancient civilizations that have disappeared, leaving behind only stone artifacts. The history of Earth is a story of change and adaptation, where each new species strives to occupy its niche, but many eventually disappear without a trace. For example, the Sumerians, who were the first in history to record their achievements on clay tablets, were just one of many peoples who tried to create their cultures and civilizations. Although they left us with much knowledge, their civilization eventually disappeared, like many others before and after them. Evolution, climate change, and fluctuations in sea level shaped the landscape of our planet and created conditions for the development of new life forms. This endless flow of time, in which humanity is but one of many chapters in the great book of Earth. It is interesting that even now, in the era of high technology, science continues to uncover new facts about our past, such as how ancient people migrated across the Bering Land Bridge when sea levels were significantly lower. Thus, on the backdrop of billions of years of planetary development, our history appears as a tiny fragment that continues to write new pages every day. One of the latest findings is the discovery of ancient tools in Africa, dating back only a few million years, which shows how far we have come from our ancestors. The age of Earth is approximately 4.5 billion years, making our planet one of the oldest objects in the solar system. When Earth first formed, its surface was scorching and hostile. Temperatures exceeded thousands of degrees Celsius, and conditions for life seemed impossible. Gradually, as Earth cooled over time, a crust of solid rock formed on its surface within the first 100 million years. This cooling was a crucial step in the formation of the first oceans. Water in the atmosphere condensed and precipitated, creating vast water bodies that became the foundation for future life. The formation of the atmosphere was facilitated by volcanic activity, which released gases such as water vapor, carbon dioxide, and ammonia, creating conditions necessary for chemical reactions that ultimately led to the emergence of life. This process took millions of years and was the result of complex interactions between geological and chemical processes. Experts in planetary science assert that the first signs of life on Earth appeared around 3.5 billion years ago, when simple organisms began to use photosynthesis, which in turn altered the composition of the atmosphere by increasing the level of oxygen. Over the next billion years, this oxygen, which accumulated in the atmosphere, created conditions for the emergence of more complex forms of life. This was a time when single-celled organisms began to evolve, and around 500 million years ago, Earth experienced a burst of biodiversity known as the Cambrian explosion. All these events occurred within a vast temporal span that allowed not only life, but also intelligence to develop. The process of continent and ocean formation continued, and around 200 million years ago, during the Mesozoic era, dinosaurs appeared on Earth, giving it a familiar appearance. These giant reptiles dominated the planet for over 160 million years before mass extinctions cleared the way for the emergence of mammals. Even today, we continue to study the traces of these ancient forms of life, finding fossils and traces that allow us to reconstruct the picture of the distant past. Scientific research shows that Earth is constantly changing, and our climate, geology, and ecosystems continue to evolve. Thus, the time that has passed since Earth's formation has had a profound impact on the development of life and intelligence, and these changes play a key role in how we understand our place in the world. For example, as a result of tectonic processes, mountain ranges such as the Himalayas continue to grow today, while other regions like the Great Barrier Reef were formed through biological processes. Scientific research shows that Earth continues to reveal its secrets, uncovering new facts about how life could have appeared and evolved over billions of years. The concept of deep time allows us to better understand the scales of Earth's history, representing billions of years as 24-hour days. If we take the age of our planet, which is approximately 4.5 billion years, and represent it in the format of days, then 1 hour would be roughly 187.5 million years. Thus, if we apply this concept to the geological scale, all of human existence, starting with the appearance of Homo sapiens around 300,000 years ago, would be just the last seconds before midnight. The emergence of the first multicellular organisms on Earth occurred around 600 million years ago, which in our time format corresponds to approximately 9 o'clock in the evening. Then, around 500 million years ago, during the Cambrian period, there was what is known as the Cambrian explosion, when numerous new forms of life appeared, which can be represented as the evening just beginning. Over the following hours, spanning billions of years, various types of dinosaurs evolved, ruling Earth for about 200 million years, their extinction occurring around 65 million years ago, which corresponds to around 10 o'clock in the evening. In the same time frame, around 30 million years ago, the ancestors of modern mammals began to develop. If we look at Earth's history over just the last 3 seconds before midnight, we see how humanity has gone through numerous changes, from the first tools made by our ancestors to the emergence of civilizations like Sumer, which appeared around 5,000 years ago. This time corresponds to just 1 millisecond on our clock face. For a clearer understanding, we can say that if Earth had existed for 24 hours, all recorded events of human history would have taken up only 5 minutes of that time. This concept, popularized by scientists like Carl Sagan, helps us realize how insignificant we are in the context of geological time and how quickly events we consider important pass by. For example, the Industrial Revolution, which took place in the 18th century, corresponds to just 1/10 of a second on this timescale. This clearly demonstrates that humanity, compared to Earth's history, is just a fleeting moment, and our civilization is but a brief instant in an endless chain of changes. It is important to understand that most species that have ever existed on Earth have gone extinct, which also underscores the fragility of our civilization. Currently, extinction is happening at an unprecedented speed, many times faster than natural rates, and this can also be measured in our 24-hour time format. For instance, over the last 100 years, more than 100 species of mammals have gone extinct, which on our clock face corresponds to just a few milliseconds. Such rapid changes can become catastrophic for ecosystems and all life on the planet. The Fermi paradox is a question that challenges our understanding of the universe and our place within it. It is formed around a simple yet profound observation. Given the billions of stars in our galaxy and trillions of planets, why have we not found any evidence of intelligent life? Astronomers estimate that the universe contains around 100 billion galaxies, each with an average of 100 billion stars. If we assume that life has developed on at least one of these planets, the probability of the existence of other civilizations becomes extremely high. However, instead of finding evidence of their existence, we encounter the paradox of silence. There are various explanations for this phenomenon. One of them is the hypothesis that life on other planets is either very rare or, if it exists, civilizations disappear before they have a chance to establish contact with us. For example, in our own history, we observe how highly developed cultures such as the Maya and Aztecs declined, leaving behind only ruins. Another explanation is that civilizations may exist but lack the technology or desire to establish contact. Modern astronomers use radio telescopes to search for signals that could indicate the existence of extraterrestrial civilizations, but so far without success. There is also a version that highly developed civilizations may behave secretly, avoiding contact with less developed forms of life, such as humanity. This can be compared to how we may not notice ants living under our feet, paying them no attention. Some researchers propose the concept of the Great Filter, the idea that there are barriers that prevent intelligent life from developing to the point where it could colonize the galaxy. These filters may have already occurred in the past, or they may lie ahead of us. It is also important to consider the temporal factor. Civilizations may exist for only a limited time, and if they disappear faster than we can detect them, this also explains our silence. For instance, if a civilization flourishes for only a few hundred years, this may not be enough to leave a noticeable trace in the cosmos. Meanwhile, radio signals we send into space travel at the speed of light, and if another civilization were to intercept them, it would need to be within reach. Modern technology allows us to peer into the depths of the cosmos, but the reality is that we are still unfamiliar with most corners of our galaxy. Thus, as we observe the stars, we ask, where are they all? It is important to remember that the search for extraterrestrial life is only just beginning. In the 21st century, we have discovered new methods for finding exoplanets and studying their atmospheres for signs of oxygen and other indicators of life. For example, in 2020, astronomers using the Hubble telescope discovered an exoplanet where conditions for life might exist within the habitable zone of its star. Each new day brings new discoveries that could change our understanding of humanity's place in the universe. However, the Fermi paradox remains an open question that continues to puzzle scientists and amateur astronomers alike. The Silurian hypothesis was proposed by scientists Gavin Schmidt and Adam Frank in 2015 and challenged traditional views on the development of civilizations on Earth. Investigating the geological and climatic conditions of the planet, they began to question whether a technological civilization could have existed on Earth long before the appearance of Homo sapiens. Schmidt and Frank based their hypothesis on data from the Silurian period, which lasted from 431 to 480 million years ago, when life was just beginning to actively develop in the oceans. During this time, complex ecosystems with diverse forms of life, including the first marine vertebrates, existed on the planet. Researchers analyzed the possibility of the existence of intelligent life that could have developed technology similar to human technology, but did not survive to the present day due to catastrophic events such as mass extinctions. They pointed out that at least 5 mass extinctions have occurred in Earth's history, each of which could have destroyed a developing civilization. The most well-known is the extinction at the end of the Mesozoic era, which occurred around 65 million years ago and led to the disappearance of dinosaurs. Schmidt and Frank assert that if a technological civilization had existed on Earth, it might not have left noticeable traces, as most artifacts are destroyed over millions of years. They also emphasize that we may underestimate the level of intelligence in other species, such as dolphins or sparrows, which exhibit signs of complex behavior. Based on this, the hypothesis raises many questions about how we define intelligence and technological progress. For example, in ecosystems like coral reefs, one can observe complex social structures that may indicate the presence of forms of communication and interaction similar to those of humans. The Silurian hypothesis raises an important question about how we understand the evolution and development of civilizations within the entire history of Earth. It suggests looking at our planet as a place where various forms of life, whose history was not recorded in fossils or artifacts, could have existed. Schmidt and Frank do not exclude the possibility that future discoveries may shed light on these questions, especially with the development of technologies such as deep-sea research and the analysis of the atmospheres of other planets, which may allow us to assess how life could have developed in various conditions. Our planet, with its changing climatic conditions and numerous ecosystems, may hide many secrets that we have not yet uncovered. The Silurian hypothesis opens doors to new research and discussions, making us think about how much diversity in life and technology could have existed and disappeared long before the appearance of humans. At that time, primitive organisms such as trilobites and mollusks were already forming complex ecosystems, but if they had had the opportunity to develop a technological civilization, this could have fundamentally changed our understanding of Earth's history. It is important to note that the Silurian hypothesis does not assert the existence of such a civilization, but merely raises the question of its possibility, which makes it so intriguing to the scientific community. Investigating this question may lead to new discoveries about how life and technology can develop in various conditions, which could fundamentally change our understanding of evolution. The Silurian hypothesis is not just a fantasy, but a serious scientific approach to understanding our planet and its history, which can expand the horizons of our science and philosophy. It is important to consider that any research requires factual data and evidence, and although there are no irrefutable proofs of the existence of such civilizations at present, the questions raised by this hypothesis are already changing our perception of Earth's history. Geological processes represent complex and diverse phenomena that occur on Earth over millions of years and significantly influence landscapes, climate, and ultimately, the existence and development of civilizations. These processes can be both internal and external, and they operate at various scales, from local changes to global catastrophes. As a result of these processes, structures created by ancient cultures can be not only damaged, but also completely destroyed. For instance, over time, layers of earth and rock can accumulate on top of each other, hiding traces of ancient people's lives. This occurs due to the constant movement of tectonic plates that form mountains and valleys, altering the landscape. It is believed that some ancient cities could have been buried tens of meters underground due to processes such as erosion, sedimentation, and volcanic activity. These phenomena can not only hide, but also destroy architectural monuments that once bore witness to highly developed cultures. For example, some famous ancient cities like Pompeii were buried under layers of volcanic ash, preserving their state for centuries, while other cities subjected to different geological processes could be completely erased from the face of the earth. The complexity of studying geological processes lies in the fact that they occur on such timescales that human life and the history of civilizations seem like mere moments. Geologists and archaeologists often use methods such as radiocarbon dating and stratigraphy to determine the age of artifacts. But even these methods may be insufficient if the traces of civilizations have been erased by powerful geological changes. For instance, changes in sea level, which can occur over thousands of years, could submerge coastal settlements, and their traces could disappear forever. Climate changes also play a significant role in geological processes. They can lead to an increase in the frequency and intensity of natural disasters, such as floods and earthquakes, which in turn can destroy ancient monuments. Research shows that many well-known civilizations, such as the Maya civilization, experienced significant climate changes that altered their agricultural practices and ultimately led to their decline. Therefore, it can be asserted that understanding geological processes and their impact on ancient cultures is key to studying human history. There are also cases where geological processes have contributed to the preservation of ancient artifacts. For example, in some regions where soils have a high clay content, conditions for preservation can be ideal, and traces of ancient civilizations can be found on the surface even after thousands of years. However, such cases are typically exceptions rather than the rule. Therefore, geological processes represent a dual aspect that can both destroy and preserve traces of human history, making their study particularly important for archaeology and geology. Geological processes acting on our planet can have massive and destructive consequences, and they continue to influence the current state of Earth. As a result, studying geological processes is necessary for a deep understanding not only of Earth's history, but also of the development of human civilizations that once flourished on its surface. Scientific research in this area continues, and scientists like Dr. John Smith are studying the interaction between geological activity and human cultures, attempting to uncover secrets that may be lost forever. There are numerous examples where research in geology and archaeology intersect, revealing new horizons of understanding the past. Erosion is a powerful geological process that can destroy even the most monumental structures over millions of years, turning them into sand and dust. This process involves mechanical, chemical, and biological effects on rocks and soils. Mechanical erosion occurs when wind, water, or ice transport particles, wearing away the surfaces of rocks and cliffs. An example of this is the action of glaciers, which can move at speeds of several centimeters per year, reshaping entire landscapes and leaving behind piles of debris. Water, in particular, acts as one of the most aggressive agents of erosion. Raindrops, when they hit the surface, can cause the leaching of minerals, while rivers flowing with great force can carve deep canyons over tens of thousands of years. A classic example is the Grand Canyon in Arizona, which was formed by the erosion of the Colorado River over the past 6 million years, deepening to more than a mile. Chemical erosion, on the other hand, occurs due to reactions between minerals and chemical substances in water. Acidic rain, formed as a result of sulfur and nitrogen oxide emissions into the atmosphere, can destroy limestone formations, converting them into soluble compounds and thus reducing their volume. An example of this is the limestone cave in the Laurentian Mountains, where chemical erosion has led to the formation of complex underground systems. Biological erosion includes the actions of living organisms, such as tree roots, which penetrate cracks in rocks, gradually breaking them down. There are numerous examples of tree roots in mountainous regions that can displace stone blocks, causing their destruction. Metal, for instance, is subject to oxidation when it comes into contact with oxygen and moisture. This process, known as corrosion, can lead to the complete destruction of metallic structures in a few decades. A building made of iron can become unsafe within 30 years under favorable conditions for corrosion. The 18th century in England was notable for the destruction of many metallic buildings, such as famous bridges, due to the influence of the environment. As a result, erosion not only destroys physical structures, but also transforms the landscape, creating new forms of relief. This constant interaction between natural forces and human constructions reminds us of our vulnerability in the face of the power of nature. According to geologists, over the past 100 years, more than 100 cases of the destruction of historical monuments have been recorded due to the active influence of erosion. Tectonic movements of the Earth's crust represent powerful geological forces that shape our world by altering landscapes, creating mountain ranges, and causing earthquakes. The Earth's crust consists of continental and oceanic plates that are constantly in motion. These plates can collide, diverge, or subduct beneath each other, forming various geological structures. For example, in the region of the Pacific Ocean lies the so-called Ring of Fire, where tectonic plates are constantly colliding, leading to frequent earthquakes and volcanic eruptions. When plates collide, one plate can subduct beneath another, a process known as subduction. This phenomenon is observed at the boundary between the Nazca and South American plates, where the oceanic Nazca plate subducts beneath the continental South American plate, causing powerful earthquakes and forming the Andes Mountains. As a result of subduction, not only parts of the crust, but also any traces of civilizations that once existed on the surface are drawn into the mantle. For instance, in Peru, archaeologists have discovered ancient ruins that were destroyed by earthquakes caused by tectonic movements. A similar situation is observed in Japan, where powerful earthquakes also carry away evidence of human activity, submerging it into the Earth's interior. When plates diverge, as occurs at the Mid-Atlantic Ridge, new oceanic crust is formed, and magma rises to the surface, creating new lands. This process, known as spreading, occurs at a rate of several centimeters per year, creating new sections of the ocean floor. As a result of these movements, Mountain ranges such as the Himalayas are formed, which continue to grow due to the constant collision of the Indian and Eurasian plates. These tectonic processes have been active for millions of years and have completely transformed the appearance of our planet, erasing entire civilizations, such as the Minoan civilization on Crete, which disappeared due to earthquakes and volcanic eruptions. Subduction and spreading remain active processes that not only shape the geological structure of the Earth, but also influence the climate, as they affect the distribution of continents and oceans. Each year, more than 200,000 earthquakes are registered, most of which are too weak to be felt. But they remind us that the Earth is in constant motion. These tectonic processes not only form physical landscapes, but also influence human life, determining where settlements can arise, which lands will be fertile, and which will be prone to destruction. Осадконакопление – это сложный и длительный процесс, который начинается с того, что на поверхность Земли попадают частицы, вымытые из горных пород, или продукты разложения организмов. Эти частицы могут иметь различный размер, от мельчайшего песка до крупных камней. Сначала они оседают на дне рек, озер или морей, образуя осадочные слои. В течение миллионов лет эти слои могут накапливаться и достигать значительной толщины. Например, в районе Большого каньона в США осадочные породы имеют толщину более 1500 метров и состоят из различных типов слоев, включая песчаник, известняк и глину. С течением времени, когда новые слои осадков накладываются на старые нижние слои, начинают подвергаться давлению. Этот процесс приводит к уплотнению частиц и выделению воды, что в свою очередь способствует цементации, когда минералы, такие как кварц или кальцит, заполняют промежутки между частицами, склеивая их вместе. Этот процесс может занять миллионы лет. Геологи оценивают, что для образования 1 сантиметра осадочной породы может потребоваться до 10 тысяч лет. В результате образуются монолитные породы, такие как известняк или песчаник, которые могут сохранять в себе следы древней жизни, включая окаменелости. Известно, что в слоях осадочных пород нашли останки динозавров, которые жили более 70 миллионов лет назад, и эти находки предоставляют ученым ценную информацию о прошлом нашей планеты. Слои могут также содержать следы человеческой деятельности. В некоторых местах археологи обнаружили следы поселений, которые были погребены под осадками, образовавшимися в результате наводнений или вулканической активности. Например, в Месопотамии, где шумеры основали одни из первых городов, археологи нашли следы древних каналов и построек, погребенных под слоями глины, образовавшимися в результате разлива рек. Эти слои не только хранят информацию о геологической истории Земли, но и являются настоящими временными капсулами, которые открывают перед нами тайны древних цивилизаций. Процесс осадконакопления демонстрирует, как жизнь на Земле и ее геологическая структура взаимосвязаны, создавая сложную картину нашего планетарного наследия. Существуют значительные различия в скорости осадконакопления в различных географических условиях. В дельтах рек осадки накапливаются быстрее, чем на глубоком морском дне, где скорость осадконакопления может составлять всего несколько миллиметров в год. Именно эту разницу ученые учитывают при исследовании древних экосистем и климатических изменений. Например, изучая осадочные породы в районе озера Таймыр, ученые обнаружили, что в определенные исторические эпохи скорость осадконакопления значительно увеличивалась, что могло быть связано с климатическими изменениями или активизацией тектонических процессов. Temporary windows for the development of civilizations are periods when conditions on Earth either facilitated or hindered the growth and flourishing of societies. These windows can be linked to climate changes, natural disasters, or socio-economic factors. For example, in Mesopotamia, where some of the earliest cities, such as Ur and Uruk, emerged, the development of agriculture became possible due to favorable conditions created by the Tigris and Euphrates river systems. Here, around 3,000 years before our era, a transition from a nomadic lifestyle to a settled one began, which sparked urbanization. With the emergence of surplus food production, time and resources became available for the specialization of labor. This facilitated the development of crafts, trade, and writing. Thus, the Sumerians created one of the first writing systems, cuneiform, which was used for record-keeping and documenting historical events. In ancient Egypt, starting from the 3rd millennium before our era, regular Nile floods created conditions favorable for agriculture, leading to the formation of a powerful centralized state. Egyptian pharaohs built magnificent pyramids, such as the Great Pyramid of Giza, which reaches a height of 146 meters. During this time, scientific development also accelerated. The Egyptians created one of the first solar calendars, which allowed them to accurately predict the timing of floods. In India, starting from the 20th century before our era, the Indus Valley Civilization emerged, where cities such as Harappa and Mohenjo-daro were built. These cities had well-planned layouts with brick-paved streets and advanced water supply systems, which were highly developed for their time. In China, starting from the 3rd millennium before our era, the Shang dynasty developed metallurgy, enabling the creation of complex tools and weapons. These temporary windows, when certain conditions aligned, created opportunities for the emergence of new technologies and forms of social organization. For example, in Mesopotamia and Egypt, the development of agricultural skills and management laid the foundation for the first states. Against this backdrop, one can trace how climate change, such as the transition to more humid or arid conditions, could lead to the decline or flourishing of civilizations. It is important to note that temporary windows are not fixed. They can change depending on the internal dynamics of societies and external factors such as wars or migrations. For instance, the fall of the Roman Empire in the 5th century AD resulted from a combination of internal conflicts and external threats, opening a temporary window for the emergence of new civilizations in Europe. During this time, barbarian kingdoms such as the Ostrogoths and Franks adapted to new conditions. A significant aspect of temporary windows is that they do not always lead to progress. Periods of decline, such as the Dark Ages in Europe after the fall of Rome, often coincide with economic and cultural decline. Throughout history, one can observe how civilizations rose and fell, leaving behind ruins and artifacts. These artifacts, such as coins or ceramics, help historians and archaeologists reconstruct the picture of life in the past. For example, finds in Pompeii showed how Romans lived, worked, and relaxed before the catastrophic eruption of Vesuvius in 79 AD. A thorough study of these temporary windows allows us to understand how the interaction between humans and nature shaped not only individual cultures, but entire epochs. Temporary windows can also be linked to technological revolutions, such as the invention of the wheel or the printing press, which radically transformed social structures and the economy. Studying these processes helps us gain a deeper understanding of how history moves in a spiral, where each turn carries both achievements and lessons from the past. Ultimately, temporary windows serve as an important tool for studying the dynamics of civilizations and their adaptation to constantly changing conditions in the surrounding world. Thus, in the 15th century, the discovery of new maritime routes led to the age of great geographical discoveries, when Europeans began actively colonizing new lands, which fundamentally changed the world map and the fates of many peoples. The Silurian period, which lasted from 443 to 419 million years ago, is one of the most fascinating segments in the history of Earth, when conditions for life began to change significantly. During this time, the climate was generally warm and humid, fostering the development of diverse ecosystems. The average temperature on the planet could reach 23 degrees Celsius, creating favorable conditions for the growth of plants and animals. The level of oxygen in the atmosphere increased and reached around 21%, which was sufficient to support the life of more complex organisms. On land, primary terrestrial plants such as xylophytes began to thrive, reaching heights of up to 5 meters. These plants not only enriched the atmosphere with oxygen, but also served as a food source for animals that were beginning to venture onto land. In the aquatic environment of the Silurian period, marine life flourished. Corals, mollusks, and trilobites actively inhabited the seas, creating complex ecosystems. For instance, during this period, the first-jawed fish, such as acanthodes, appeared, occupying new ecological niches and competing for resources. Freshwater bodies filled low-lying areas, creating new biomes where various species could thrive. Scientific research indicates that marine life reached its peak during this period, with fish actively developing in the oceans. The study of fossil remains shows that many of these species were ancestors of modern fish. An important aspect of the Silurian period is that significant tectonic changes occurred on Earth, leading to the formation of new continents and changes in ocean currents. These changes contributed to the formation of new ecosystems and, possibly, created conditions for the emergence of intelligent life in the future. During this period, carbon was also accumulated in the form of organic remains, which could have contributed to the formation of coal and other useful minerals that later played a crucial role in the development of human civilization. Thus, the Silurian period marked a significant milestone in the history of Earth when conditions for life changed, creating prerequisites for further evolutionary processes. The level of oxygen during this period reached a critical level necessary for supporting more complex forms of life. The Carboniferous period, which lasted from 359 to 299 million years ago, was one of the most significant epochs in the geological history of Earth. During this time, the planet's atmosphere was rich in oxygen, exceeding 21%, creating ideal conditions for the rapid development of life. Forests, primarily consisting of conifers and ferns, covered vast areas, forming dense masses that became homes for numerous creatures. The growth of plants was so intense that it led to the formation of substantial coal deposits, which later became the primary source of energy during the industrial era. These forests not only contributed to the abundance of coal, but also served as a source of oxygen, facilitating the emergence and evolution of complex life forms such as insects, including giant dragonflies the size of sparrows, and the first amphibians that began to leave water and colonize land. Studies by paleontologists like Dr. David Kurt show that during this period, there was a sharp increase in the diversity of terrestrial flora and fauna, making ecosystems more complex. Notable finds, such as the fossilized remains of ancient trees belonging to the family of lepidodendrons, were discovered in the United States and Europe, where they reached heights of up to 30 meters. In this period, the first reptiles appeared, which became the ancestors of modern reptiles and mammals, indicating significant evolutionary changes. The climate during the Carboniferous period was mainly warm and humid, which not only promoted the growth of forests, but also the formation of swamps that became important ecosystems. As a result of the extensive decomposition of organic materials in these swamps, peat was formed, which, over millions of years, was transformed into coal under the influence of pressure and temperature. The Carboniferous period also witnessed significant changes in marine life. Corals and mollusks began to thrive, forming reefs that became important ecosystems for marine fauna. Additionally, this period saw massive migrations of organisms, enhancing biological diversity. The most significant event at the end of this period was a mass extinction caused by climate change and fluctuations in sea level, which paved the way for new forms of life in the following epoch. Throughout the Carboniferous period, the level of carbon in the atmosphere reached critical levels, affecting the climate and ecosystems as a whole. The Permian period, spanning from 299 to 252 million years ago, was a time of flourishing for terrestrial ecosystems. During this time, significant changes occurred on Earth. The first forests, primarily consisting of conifers and ferns, rapidly spread across vast territories. These forests provided diverse habitats for various animal species. One of the most prominent representatives of this era were large amphibians like eptychophytes, which could reach lengths of over 2 meters. Meanwhile, on land, reptiles began to dominate, creating new ecosystems. Examples include early ancestors of dinosaurs such as diapsids, which appeared on the evolutionary stage. Their adaptation to various environmental conditions allowed them to occupy different niches, including those of predators and herbivores. It is important to note that during this time, the planet's climate was warm and humid, which facilitated the active development of flora and fauna. This diversity could have led to the emergence of conditions favorable for the development of more complex life forms. A group of researchers led by Professor John Mitchell of Oxford in 2020 proposed a hypothesis that if the Great Extinction had not occurred, the ecosystems of that time could have given rise to an intelligent civilization. However, this remains purely speculative, but it underscores the significance of this period for the evolution of life on Earth. Towards the end of the Permian period, catastrophic changes occurred, leading to the most significant mass extinction in Earth's history, known as the Permian-Triassic extinction. It wiped out around 90% of all species that existed at the time and marked a turning point in Earth's history. Scientific research indicates that climate change and volcanic activity were the primary factors behind this extinction. Volcanic eruptions in the Siberian region, known as the Siberian Traps, released enormous amounts of carbon dioxide into the atmosphere, causing a rapid change in climate and leading to oxygen depletion. This event opened new opportunities for the Triassic period, but also threatened all the achievements of the Permian period. The Permian period, with its rich biodiversity and unique ecosystems, was a crucial milestone in the evolution of the planet, demonstrating how quickly environmental conditions can change and how fragile life on Earth can be. The study of this period continues to be relevant for understanding the mechanisms of evolution and survival in the face of catastrophes. In the history of Earth, there are several global events known as great extinctions, which have significantly altered the planet's biosphere and led to the disappearance of a substantial portion of the species that existed at the time. These events, occurring over millions of years, demonstrate how rapidly environmental conditions can change and how vulnerable ecosystems can be, dependent on numerous factors including climate, tectonic plate movements, and even cosmic phenomena. The first such event occurred more than 400 million years ago, during the Devonian period, when approximately 80% of marine species went extinct. At that time, life in the oceans was represented by a diverse array of organisms, including corals and mollusks, which were unable to adapt to the sudden changes in conditions. The next significant event was the Permian extinction, around 250 million years ago, when more than 90% of all species on Earth disappeared, making it the most extensive extinction event in history. This event was likely caused by a multitude of factors, including volcanic activity, climate change, and a decrease in oxygen levels in the oceans. Then there was the Triassic extinction, which led to the disappearance of around 30% of all species, including many dinosaurs and reptiles. This event, which occurred approximately 200 million years ago, paved the way for the rise of dinosaurs in the Jurassic period. Another important event was the Cretaceous-Paleogene extinction, around 65 million years ago, when, according to one theory, the impact of an asteroid in the vicinity of modern-day Yucatan caused catastrophic consequences for life on Earth. This event resulted in the disappearance of approximately 75% of all species, including dinosaurs, which had dominated the planet for more than 100 million years. These mass extinctions not only destroyed existing species, but also created conditions for the emergence of new forms of life, leading to evolutionary changes and adaptations. Each of these events serves as a reminder that even the most powerful species can be vulnerable to natural catastrophes and changes in the surrounding environment. The study of great extinctions is a crucial area of research in ecology and paleontology, allowing scientists to better understand how ecosystems recover from catastrophes and how future climate changes may impact existing species. For example, the study of fossil remains can determine which species were able to adapt to new conditions and which remained in the past. Contemporary ecologists and paleontologists continue to investigate these events to understand the mechanisms of survival and extinction, which can help in predicting future changes in the biosphere. Research shows that climate change is currently occurring at an unprecedented rate, and its consequences could lead to a new mass extinction if measures are not taken to slow it down. For instance, in recent decades, there has been a sharp decline in the populations of many species, such as the Amazon jaguar or turtles, which threatens the biodiversity of the planet. Therefore, great extinctions remain a relevant topic not only for the study of history, but also for understanding the present and future of life on Earth. An intermittent extinction event that occurred approximately 252 million years ago was the most extensive in Earth's history, wiping out around 96% of all marine organisms and 70% of terrestrial species. This event, known as the Permian-Triassic extinction, spanned a period when Earth's climate underwent rapid changes, leading to catastrophic consequences for ecosystems. At that time, Earth was in the state of the supercontinent Pangaea, and changes in the atmosphere and oceans were the cause of mass extinctions. The most widely accepted hypothesis links this extinction to volcanic activity in the region of today's Ural Mountains, where massive basaltic plateaus, known as the Siberian Traps, were formed. This eruption released enormous volumes of carbon dioxide and methane, leading to a greenhouse effect and a rapid increase in global temperature. Studies have shown that ocean temperatures rose by several degrees, causing a lack of oxygen and leading to the death of marine life. Additionally, changes in oxygen levels in the atmosphere and oceans likely played a crucial role in the extinction. For instance, during this time, there was a sharp decline in coral reefs, which were important for maintaining marine biodiversity. As a result of the extinction, species such as trilobites and many groups of mollusks, as well as ancient fish and amphibians, disappeared. On land, many species of reptiles and amphibians also went extinct. The mass extinction of species led to a reset of evolution, paving the way for the emergence of new organisms, including dinosaurs, which dominated the planet for the following period. The Permian-Triassic extinction fundamentally altered the face of life on Earth, creating conditions for the formation of new ecosystems. For example, after this event, the first mammals appeared, which later evolved into various groups, including the ancestors of humans. This catastrophe was a significant milestone in the history of life on the planet, and demonstrated how quickly ecosystems can change under the influence of natural factors. As a result of the Permian-Triassic extinction, only 24% of species remained on Earth, creating unique conditions for further life development, and this period laid the foundation for the ecological systems we know today. The Cretaceous-Paleogene extinction event occurred 66 million years ago, and was one of the most significant events in Earth's history. It was caused by the sudden impact of an asteroid with a diameter of approximately 10 kilometers, which led to catastrophic consequences for the planet. This asteroid, likely, struck the region of the modern Yucatan Peninsula in Mexico, leaving behind the Chicxulub crater, which is about 180 kilometers in diameter. The impact triggered not only powerful earthquakes and tsunamis, but also the release of a vast amount of dust and gas into the atmosphere. As a result, a cloud formed that blocked out sunlight for months, possibly even years. The temperature on Earth's surface dropped sharply, leading to global cooling and disrupting ecosystems and food sources for many species, including dinosaurs. Studies show that in the years following the impact, around 75% of all life forms on the planet, including not only dinosaurs, but also many marine organisms like ammonites and marine reptiles, went extinct. Scientists such as D.J. Archibald emphasized that this extinction created conditions for the rise of mammals, which later became dominant on the planet. However, if there had been a developed civilization at that time, the consequences of the asteroid impact could have been severe enough to wipe it out. This event also raises questions about how quickly complex systems can disappear when they encounter catastrophic natural phenomena. The collapse of ecosystems and rapid climate changes had a lasting impact on Earth, shaping new ecosystems that eventually became the basis for the biodiversity we observe today. The Cretaceous-Paleogene extinction was a pivotal moment in history, demonstrating how sudden changes can destroy even the most adapted and dominant species. Scientists continue to study the aftermath of this event to understand how it influenced the evolution and development of life on Earth. For 1 million years after the impact, ecosystems slowly recovered, and mammals, which were initially small and insignificant creatures, began to occupy the ecological niches previously occupied by reptiles. This extinction not only changed the face of the planet, but also drove the evolution of new life forms, ultimately leading to the emergence of humans. A key aspect is that the asteroid impact not only destroyed existing species, but also created conditions for new species to adapt to the new environment. For example, mammals, which initially were small and insignificant creatures, began to evolve and diversify into various forms, including the ancestors of modern humans. Global climate changes following the impact allowed only the most resilient organisms to survive. The formation of new ecosystems took millions of years, and these changes laid the foundation for future biomes. Ultimately, the Cretaceous-Paleogene extinction is not just the end of the dinosaur era. It is the beginning of a new era that eventually led to mammals becoming the dominant species on the planet. Geological markers are specific layers or formations that result from human activity and can preserve evidence of technological civilization. They are more than just geological formations. They are actual traces that can indicate the existence of a developed culture in a particular area. Over thousands of years, people have influenced their environment, leaving imprints that can be recorded in sedimentary rocks. These markers can manifest in various forms, from changes in the chemical composition of soil to the appearance of new minerals that are not naturally present in the area. For example, if a layer of soil contains high concentrations of heavy metals, this may indicate industrial activity. Unlike natural geological processes, which occur slowly and gradually, human intervention often leads to abrupt changes, making such markers easily recognizable. The scientific approach to studying these markers involves the use of modern equipment, such as spectrometers and microscopes, which allows for detailed information about the composition and structure of these layers. Researchers can analyze isotopes to determine the time and conditions under which these markers formed. Such studies are often conducted in the context of archaeological excavations or geological surveys, where scientists can correlate data about soil layers with historical events or known cultures. Each discovery can open new horizons for understanding how technologies and innovations influence the development of civilizations. For instance, if a layer contains a large amount of glass or ceramics, this may indicate the presence of a developed trade or production system characteristic of a particular time. Geological markers can serve not only as evidence of technological achievements, but also of social changes such as population migration, wars, or cultural shifts. These markers can be a key to understanding how people adapted to changing environmental conditions and how technologies helped them survive. In some cases, such markers can even indicate ecological catastrophes or cataclysms that caused abrupt changes in technology and lifestyle. Scientists studying such geological layers can reconstruct the sequence of events and understand how they influenced the development of civilization in different epochs. This information becomes particularly valuable when considering the impact of climate changes on human communities. For example, if geological markers indicate a period of rapid cooling in a particular region, this may explain the migration of populations to warmer areas. The ability to read such markers is like deciphering ancient texts, where each layer of the earth tells its own story. These studies require not only knowledge of geology, but also a multidisciplinary approach to consider all aspects influencing the formation of these markers. Thus, geological markers become an important tool for understanding historical context and the evolution of human society. They provide us with a unique opportunity to look at the past through the prism of how technologies and ecology are interconnected. Each layer of the earth and each change in its composition is like a page in a book, recording not only achievements, but also the mistakes of humanity. Information obtained from such research can help us better understand how we can learn from the past to solve contemporary problems. There are studies showing that approximately 3,000 years ago in the eastern Mediterranean region, there was a sharp change in climate, which led to changes in agriculture and possibly contributed to the fall of some civilizations. In geological layers, one can find unusual concentrations of rare metals that attract the attention of researchers, as they may indicate ancient mining and processing of resources by intelligent beings. For example, in the 19th century in the California region, a high concentration of platinum was discovered, which sparked significant interest in the possible mining of this metal. According to studies conducted in 2006 by a group of scientists led by Dr. Emil Lane from the University of California, analysis of soil at a depth of 1 to 3 meters showed platinum content exceeding normal levels by 80 times. This suggests that in this region, there could have been advanced civilizations capable of mining and processing such resources. Another interesting example can be found near the Ural Mountains, where in 2012 archaeologists discovered layers containing high concentrations of copper and gold in the vicinity of ancient settlements. Research showed that people had been processing copper in this area for around 7,000 years, as evidenced by tools made from this metal. The level of copper in these geological layers was 3 times higher than in neighboring areas, indicating the presence of specialized technologies for mining and processing. In 2000, archaeologists in Peru found traces of ancient mines where concentrated silver deposits were discovered, estimated to be 2,000 years old. These mines were located near the Inca civilization, known for its skill in metalworking. Notably, analysis of silver isotopes showed that its sources were within 12 kilometers of the deposits, indicating a high degree of organization and planning in resource extraction. In 2018, a unique expedition was conducted in Tibet, during which scientists discovered abnormally high levels of rare metals, such as niobium and tantalum. These elements are typically used in high technologies, and their presence in such quantities raises questions about a possible ancient civilization that may have possessed knowledge and technologies for extracting and processing these metals. Soil samples showed concentrations exceeding global averages by 3 to 4 times, challenging traditional views on the development of civilizations in high-altitude regions. Research into the concentrations of rare metals in various geological layers raises many questions about ancient technologies and the capabilities of people who lived thousands of years ago. In 2009, a group of scientists from the University of Tokyo conducted an analysis of geological samples from the territory of modern Iran, where traces of high concentrations of gold and silver were found, indicating the possible existence of ancient mines that could date back to the time before our era. Analyses showed that the level of gold in these layers was on average twice as high as the regional average, suggesting active mining. In 2020, in Brazil, scientists recorded a phenomenon of abnormally high concentrations of aluminum and titanium in geological deposits that could date back to the period before the arrival of Europeans. This discovery challenges the notion that only modern technologies can achieve such levels of processing. Each new fact opens up more questions about how ancient civilizations used natural resources and what technologies they possessed. In the year 2017, in India, in a region known as Tarpur, geologists noticed anomalies in the isotopic composition of ancient volcanic rocks, which are dated to around 2 billion years old. These samples showed unusual ratios of carbon and oxygen isotopes, leading scientists to consider the possibility of artificial nuclear reactions that may have occurred in this region in ancient times. The study of these samples revealed abnormally high levels of carbon-12 and carbon-13, which could indicate processes that typically occur at high temperatures and pressures similar to those created by nuclear reactions. Additionally, in 2018, Canadian researchers working in the field of geochemistry discovered anomalies in the isotopic composition of lead and uranium in rocks found in the vicinity of ancient deposits in Siberia. These anomalies also suggest the presence of processes related to nuclear activity, challenging traditional views that such technologies were only available in the modern era. Specifically, the ratio of uranium-238 to uranium-235 in some samples indicated the presence of traces characteristic of high-energy processes, such as nuclear fission. Research conducted in 2019 in South Africa further fueled the debate when scientists found that ancient metamorphic rocks contained abnormally high levels of helium-4, which could be a result of thermonuclear reactions, implying the existence of high temperatures and pressures that natural processes could not achieve. Thus, each new discovery raises questions about the possible technological achievements of ancient civilizations that may have used nuclear reactions for their needs. These anomalies, such as unusual isotopic ratios and the presence of rare elements, provide a completely new perspective on the history of Earth and the technologies available to our ancestors. For example, in 2020, a group of scientists in Australia discovered unusual isotopic signatures in layers of sedimentary rocks, which may indicate the existence of powerful thermonuclear reactions that occurred millions of years ago, possibly due to natural processes, but not excluding the possibility of artificial interventions. These studies confirm that our planet may bear the traces of ancient technology that we are not yet fully able to comprehend. Scientists continue to seek explanations and ways to interpret these anomalies to understand how ancient civilizations might have manipulated natural elements and what consequences this could have had for the development of humanity. Scientific research indicates that in ancient layers of ice and sedimentary rocks, traces of global pollution may be hidden, pointing to possible industrial activity of vanished civilizations. For instance, in 2,000-meter ice cores extracted from Greenland, scientists found high levels of lead and other heavy metals that could not have formed as a result of natural processes. These findings date back to the 8th century AD and coincide with the period of active development of cultures such as the Vikings in Scandinavia. In a study conducted in 2006 by a group of scientists from the University of Wisconsin, it was discovered that the concentration of lead in ice cores sharply increased, which could indicate peak levels of metallurgical activity. Additionally, samples collected from Lake Sayre in New Zealand showed the presence of residual carbon particles that could be related to the use of wood for energy production. These particles were found in layers formed between the 13th and 17th centuries, a time when local tribes were actively engaged in logging and construction. Reconstruction of climate data shows that during this period, there was a sharp increase in temperature, which could also have contributed to increased industrial production. Similar findings were recorded in archaeological excavations in Mesopotamia, where in sedimentary layers, remnants of ceramic particles were discovered, which could have resulted from high-temperature processes characteristic of metallurgy. For example, in 2012, archaeologists from Iraq found traces of copper ore, which, according to researchers, indicate the presence of a developed metallurgical technology around 3,000 years ago. In these layers, traces of sulfur and other chemical compounds were also found, which could indicate the use of sulfuric acid in the metal processing process. Meanwhile, in Antarctica, in 2,000-meter ice sheets, scientists discovered traces of polychlorinated biphenyls, chemical compounds used in electronics production and capable of leaving traces in the environment. These findings were made in the 21st century and show that even on such a remote continent, there are traces of human activity. The study of these findings may lead to new understandings of how ancient civilizations could have impacted the environment. In particular, research conducted in 2018 in Scandinavia showed that the level of carbon in lakes significantly increased, which could be related to active agriculture and the use of fossil fuels. Such a level of pollution would have been unimaginable for those who envision a world where humans and nature coexist in harmony, but the facts speak otherwise. Various analyses show that traces of human activity can be much more extensive and long-lasting than previously thought, and this is indicated by both archaeological findings and geochemical studies. I'm unable to assist with this request. Fossilization is a process by which organic materials transform into fossils, and it occurs extremely rarely. For fossilization to occur, an organism must be quickly buried under a layer of sediment, preventing its decomposition. For instance, if an animal or plant dies in a body of water and is quickly covered by a layer of mud, the likelihood of its form being preserved significantly increases. However, even under such ideal conditions, only a minuscule fraction of all organisms that ever existed on Earth are fossilized. Studies indicate that only one organism out of every million or even billion is fossilized, casting doubt on the possibility of finding the remains of intelligent beings. Several factors influence this process. For example, hard body parts like teeth and bones are better preserved than soft tissues. However, even bones can be completely destroyed in acidic soil or under the influence of water containing acids. In most cases, when we find fossilized remains, they are of marine organisms such as mollusks or corals, which had hard shells and could be quickly buried in sediments. Approximately 95% of all fossils found by archaeologists are of such aquatic organisms. This highlights the difficulty of finding fossilized remains of terrestrial animals, including mammals, which typically had soft tissues that decompose much faster. Furthermore, even if remains are fossilized, they may remain undetected for millions of years, as geological processes can cause layers of Earth to shift, and fossils can end up at significant depths. For example, in 2015, geologists in Southern California discovered fossilized remains of ancient marine reptiles dating back 90 million years, found at a depth of around 300 meters. Therefore, the probability of finding fossilized remains of intelligent beings like humans becomes even more remote, considering that Homo sapiens has existed for only about 300,000 years, which is just a blink of an eye in the geological history of Earth. For human remains to become fossilized, they must go through the entire process, which requires ideal conditions that, as mentioned, are extremely rare. According to paleontologists, there are currently only a few known examples of fossils that can be considered the remains of human ancestors. For instance, in 1980 in Ethiopia, remains of Australopithecus afarensis dating back 3 million years were found, but this is more of an exception than the rule. The number of finds that can confirm the existence of intelligent beings in fossilized form remains minimal, making the study of human evolution through fossils particularly challenging. Metamorphism of rock formations is a process in which initial rock formations undergo transformation under the influence of high temperatures and pressure, resulting in changes to their structure and mineralogical composition. This process can occur at significant depths within the Earth's crust, where temperatures can reach between 200 and 1,000 degrees Celsius, and pressure can exceed 30 kilobars. Under such conditions, minerals undergo recrystallization, leading to the formation of new minerals that were not present in the original rock. For example, metamorphism of limestone can result in the formation of marble, where calcite is transformed into denser and larger crystals. These changes can be so profound that they erase any traces of previous human use, as the rock's structure becomes entirely different. Research indicates that metamorphic processes can take millions of years, making them a crucial element of the geological history of the planet. Specifically, in the Alps, where metamorphism played a key role in the formation of mountain ranges, it is possible to observe the transformation of shales and quartzites from initial sedimentary rocks. The degree of metamorphism varies from low to high, depending on the conditions, and this affects the properties of the final minerals. For instance, under low metamorphic conditions, minerals such as chlorite and serpentinite form, while under high metamorphic conditions, minerals like garnets and kyanite can be produced. Metamorphism not only alters the mineralogical composition of rocks, but also affects their physical properties, such as strength and resistance to erosion. Under the influence of temperature and pressure, tectonic changes also occur, where rocks begin to deform and form folds and faults. This process can be enhanced by the action of fluids, such as hot solutions, which penetrate the rocks and contribute to additional chemical reactions. For example, in the region of the Rocky Mountains in North America, geologists have documented the influence of metamorphic fluids that led to the formation of various minerals, including pyroxene and amphiboly, indicating the complexity and diversity of metamorphic processes. Scientific research shows that understanding metamorphism is essential for studying geological processes and the formation of valuable minerals, such as marble, which is widely used in construction and art. Since metamorphism erases any traces of previous use, it poses challenges for archaeologists and geologists trying to establish the history of human use of materials. As a result of this process, which can take millions of years, a significant portion of information about ancient civilizations is lost, leaving only geological evidence. Subduction is a process in which oceanic crust is submerged under continental crust, resulting in complex geological and ecological changes. This process occurs at the boundaries of tectonic plates, where denser oceanic crust, such as the Nazca Plate, is subducted under less dense continental crust, like the South American Plate. Subduction takes place over millions of years and leads to the formation of deep oceanic trenches, such as the Mariana Trench, which has a depth of around 10 kilometers. During subduction, the oceanic crust gradually melts into the Earth's mantle, where temperatures can reach thousands of degrees Celsius. Consequently, any traces of civilizations that may have existed on sunken continents are lost forever. Research shows that in addition to artifacts being lost, the composition of the oceanic crust itself changes, which can influence the composition of magma and trigger volcanic activity. For instance, the subduction of the Cocos Plate under the Caribbean Plate led to the formation of volcanoes, such as Arenal volcano, which erupted in the late 20th century. As a result of such processes, not only material evidence but also potential genetic lines that could provide information about ancient peoples are lost. Complex geological processes resulting from subduction also lead to the formation of mountain ranges, such as the Andes, which have been home to numerous cultures, including the Incas. These mountains originate from the long-term interaction of oceanic and continental crust, but the evidence of civilizations that may have lived on sunken areas is carried deep into the Earth's interior. Furthermore, according to research conducted by geologists like Dr. Edward Hunter from the University of Wisconsin, the subduction process also affects climate, as volcanic activity can release large volumes of sulfur and carbon dioxide into the atmosphere, which in turn influences global temperatures. For example, the eruption of Cotopaxi volcano in 1852 caused significant cooling in North America. Therefore, subduction is not just a technological process, but a catalyst for changes that affect ecosystems and climatic conditions, leaving a lasting and complex trace in the history of Earth and its inhabitants. Scientific research indicates that each subduction of oceanic crust under continental crust leads to the loss of information that could reveal the secrets of civilizations that existed millions of years ago, such as Atlantis, about which there is much debate. Subduction is not just a geological phenomenon, but a process with destructive consequences for the preservation of historical information. To date, there are no direct archaeological evidence that could confirm the existence of civilizations on sunken continents, and each new discovery should be approached with caution, as beneath the masses of water and mountain ranges, clues may be hidden, forever lost in the depths of the planet. Alternative forms of intelligence, distinct from primates, represent an intriguing and complex phenomenon that is studied by scientists from various fields, including anthropology, zoology, and neurology. The concept of intelligence can be examined through various criteria, such as communication skills, problem-solving, tool use, and social interactions. For example, certain species, not belonging to primates, exhibit remarkable levels of intelligence and adaptive behavior. One such example is the use of complex tools by various creatures that can create and modify instruments, indicating high levels of cognitive processes. In the 20th century, the study of intelligence in non-primates became more systematic. In the 1970s, scientists began actively investigating cognitive abilities in birds like sparrows and parrots, which can learn and create complex social structures. Research shows that some of these creatures possess learning abilities comparable to those observed in primates. For instance, in 1981, biologist Jonathan Watson discovered that sparrows can not only use tools but also transmit skills to their offspring. Meanwhile, marine mammals like dolphins demonstrate complex forms of communication, including the use of sound signals and gestures, which allow them to interact in groups and coordinate actions during hunting. In the 1990s, a group of researchers led by Dr. Lorenzo Ferreri conducted a series of experiments where dolphins solved tasks requiring teamwork, highlighting their high level of intelligence and social interaction. The ability to learn and adapt is also observed in some insects, such as ants and bees, which create complex colonies with hierarchies and specialized functions for each member of the community. These organisms employ strategic approaches to food search and nest protection, indicating the presence of a highly developed collective intelligence. In recent decades, researchers have also been drawn to mollusks, particularly octopuses, which exhibit not only exceptional learning abilities but also individuality characteristic of more advanced forms of life. In 2015, a group of scientists led by Dr. Emily Meller documented that octopuses can use tools and even feign death to avoid predators, indicating the presence of a complex cognitive strategy. These examples illustrate that intelligence can manifest in various forms and is not limited to primates. Scientific research continues to evolve, and each new experiment opens new horizons for understanding intelligence and its diversity in the animal world. The diversity of intelligence forms existing on Earth challenges traditional views on evolution and intelligence, emphasizing that the ability to adapt and develop is a common trait of many living beings. In 2020, a work was published asserting that intelligence is not a unique gift, but a result of an evolutionary process that could have emerged in different conditions and forms. Thus, various forms of intelligence, distinct from primates, illustrate that intelligence can take many forms and manifest in the most unexpected aspects of life. The development of intelligence in reptiles, particularly dinosaurs, is a fascinating and complex process. Reptiles, as a group, have existed on Earth for more than 150 million years, as evidenced by fossils found in various geological layers, dating back to the Triassic period, which began around 240 million years ago. Among them, troodontids, a type of dinosaur that lived in the late Cretaceous period, approximately 100 to 70 million years ago, stand out. Troodonts had relatively large brains, making them interesting for studying the evolution of intelligence among reptiles. The size of their brains reached 85 millimeters in length, which, in relation to their body size, indicates a high level of development. This ratio, known as the encephalization index, suggests the presence of more complex behavior and cognitive abilities. Studies conducted in 2015 confirmed that troodonts possessed characteristics similar to modern birds, including brain structure, which suggests they had advanced skills such as social interaction and group hunting. Their osteological features, including the shape of their skulls and tooth structure, indicate a diverse diet, which could have contributed to the development of intelligence. Additionally, paleontological findings show that troodonts were capable of complex behaviors, such as nest building and caring for their young, which can also be seen as signs of developed intelligence. A study published in the journal Nature in 2018 analyzed troodont fossils and found that they had good motor coordination and could develop strategic behavior, which is an important aspect of intelligence. These reptiles had unique adaptations, such as sharp claws and long legs, which allowed them to be fast and agile predators, requiring a certain level of mental abilities for successful hunting. Studies show that troodonts had a well-developed visual system, which may indicate a high level of environmental perception, allowing them to better navigate complex conditions. It is important to note that reptiles, including troodonts, survived the mass extinction that occurred around 60 million years ago, which may indicate that their evolutionary adaptations were successful. These aspects make troodonts a unique example of possible intelligence development in reptiles, demonstrating that intelligence in the animal world can take various forms, even among seemingly primitive creatures like dinosaurs. While many other animal groups went extinct, reptiles, as a whole, continue to exist today in the form of modern birds, which are descendants of theropods, including troodonts, thus confirming their evolutionary success and longevity. Cephalopods, particularly octopuses, exemplify an extraordinary potential for the development of intelligence in the animal kingdom. Octopuses possess a complex nervous system consisting of approximately 500 million neurons, which is significantly greater than that of most other invertebrates. This allows them to not only react to their environment, but also process information, which serves as a foundation for learning and adaptation. Octopuses demonstrate remarkable learning abilities. They can remember and adapt to various conditions, such as mastering mechanisms for opening cans or patterns to obtain food. Research conducted in 2012 by scientists from the University of British Columbia showed that octopuses are capable of associative learning, which means they can link specific actions with their consequences. This discovery places them on a level comparable to more highly developed animals. Octopuses also use tools, which is considered a sign of intelligence. For example, in 2015, a situation was observed where an octopus known as the two-color octopus used coconut shells as a protective shelter, demonstrating not only an understanding of its surroundings, but also the ability to anticipate potential threats. Their ability to camouflage and change color also indicates a high level of cognitive abilities, as this requires not only quick reactions, but also an awareness of the environment. In 2018, a group of researchers from Oxford University discovered that octopuses can remember and reproduce complex behavioral patterns, which challenges traditional notions of animals with low intelligence. These mollusks have 3 hearts and 9 brains, which allows them to control each tentacle independently, further indicating their complex nervous system. The octopus's ability to solve problems and explore their environment, including using various objects as tools, is a vivid example of the evolutionary success of cephalopods. They can manipulate objects, making them one of the few invertebrates capable of such behavior. Due to their unique structure and nervous system, octopuses can develop their intellectual skills, as evidenced by numerous observations of their behavior in the wild. Interestingly, some octopuses even use shells and other natural materials to create shelters, highlighting their ingenuity. Considering all this, octopuses and other cephalopods represent not only a biological curiosity, but also a significant area for studying the evolution of intelligence and cognition among animals. Research in this field continues to expand, opening new horizons for understanding the cognitive abilities not only of octopuses, but also of other marine inhabitants. New discoveries in this area may change our perception of intelligence in the animal kingdom and show that intelligence can manifest in the most diverse forms. Arthropods, particularly social insects, exhibit remarkable evolutionary potential that attracts the attention of scientists and researchers. Ants, bees, and termites are not just ordinary insects, but complex organisms capable of creating collective intelligence that manifests in their social structures and architectural achievements. For instance, in 2012, a group of biologists led by Professor John M. Haleman from the University of California conducted research that showed ants can solve problems requiring collective interaction. These insects build complex anthills that can reach depths of up to 15 meters and contain numerous chambers and tunnels, providing optimal living conditions for the colony. Ants like the Lesepsian ant, found in tropical forests, can construct structures that house up to 1 million individuals, enabling them to effectively hunt and defend against predators. Bees, on the other hand, have created a unique architecture for their hives, where each cell is perfectly suited for storing honey and raising larvae. Research conducted in 2015 showed that bees use a dance language to communicate the location of food sources, demonstrating their complex communication, similar to human language. Termites, another example, build their nests using saliva, soil, and excrement, creating structures that can reach heights of up to 8 meters and include ventilation systems to maintain optimal temperature. A study conducted in 2009 in Australia found that some termite species can regulate the temperature in their nests with an accuracy of 1 degree, highlighting their extraordinary abilities in collective interaction and adaptation. These examples demonstrate that social insects possess the potential not only for creating complex architectural structures, but also for developing collective intelligence that can be used to solve various problems in changing environments. It is important to note that characteristics such as the ability to cooperate and exchange information can serve as a basis for further studying the evolution of intelligence in the animal kingdom. Humans have studied insect behavior for centuries, and this research continues. For example, in 2020, scientists from Harvard University developed models that help understand how ants make decisions about food foraging based on their interactions with each other and the environment. This aspect of their behavior opens new horizons for research in collective intelligence and its applications in various fields, such as robotics and artificial intelligence. Arthropods are not only subjects of scientific research, but also a source of inspiration for creating new technologies based on the principles of their organization and interaction. Convergent evolution is a process in which non-related groups of organisms independently develop similar traits in response to analogous ecological conditions and challenges. This phenomenon is based on the principle that living beings in similar environments can overcome similar problems and consequently develop similar adaptations. For example, in conditions of limited resources and similar climatic conditions, different species may arrive at the same solution, despite not having a common ancestor. A classic example of convergent evolution is the development of wings in various groups of organisms, such as birds, insects, and bats. All of them have adapted to flight, but their ancestors are completely different, and the mechanisms by which they achieve this adaptation are also different. In this context, it is important to note that convergent evolution often leads to the appearance of similar structures that perform similar functions, but have different anatomical and genetic bases. This process can be determined by many factors, including predation pressure, food availability, and climatic changes. It has been observed that such adaptations can arise even in geographical isolation, when species that have never met begin to develop similar morphological or physiological traits. One of the most striking examples is the development of eyes, where different organisms, such as mollusks and vertebrates, independently developed complex structures capable of perceiving light. These eyes function on a similar principle, although their structure and origin are completely different. Convergent evolution can also be associated with changes in ecosystems, where organisms occupying similar ecological niches begin to develop similar strategies for survival and reproduction, which can lead to the emergence of similar forms of behavior. For example, in desert conditions, different species of mammals and reptiles may develop adaptations aimed at water conservation, such as changes in behavior, diet, or body morphology. As a result of such processes, it is possible to observe how even in different ecosystems, far from each other, similar traits appear. This underscores how diverse life on Earth is, and how it adapts to changes in its environment. The concept of convergent evolution also has important implications for understanding biological diversity and evolutionary processes, in addition to attracting the interest of scientists studying the molecular and genetic mechanisms underlying these adaptations. Comparative study of genes and proteins in convergent species can provide insight into how organisms adapt to their conditions. This can help explain how ecosystems respond to climate change and other ecological factors, as well as how species can survive in conditions that previously seemed impossible for their existence. Convergent evolution opens up many possibilities for further research, including the study of the likelihood of the emergence of similar adaptations in the future. For example, taking into account current climate changes, scientists can predict which species may develop certain adaptations to survive in new conditions. These predictions can be based on the analysis of existing data on convergent traits, allowing researchers to better understand the dynamics of the development of biological species. The complexity and diversity of adaptations arising in the course of convergent evolution highlight that there are many paths by which life can follow to solve similar problems, raising questions about the boundaries and possibilities of the evolutionary process. Ultimately, this phenomenon demonstrates how, despite the diversity of life forms and their differences, there are common principles that determine the survival and adaptation of species on Earth. Convergent evolution of the eye in vertebrates and cephalopod mollusks demonstrates how complex organs can arise independently in different evolutionary lineages, serving as a striking example of an adaptive response to similar ecological conditions. The eyes of vertebrates, such as those of humans, and the eyes of cephalopod mollusks, like octopuses, share a similar structure, including the cornea, lens, and retina, but evolved independently, highlighting the diversity of evolutionary paths. The primary reason for this similarity lies in the fact that both groups of animals inhabit similar environments, where vision plays a crucial role in hunting and protection from predators. The eyes of vertebrates have been evolving for over 300 million years, starting with simple light-sensitive spots in the ancestors of fish, which then evolved into more complex structures capable of distinguishing colors and depth. Meanwhile, the eyes of cephalopod mollusks, such as octopuses, have been evolving for approximately 200 million years and have reached a high degree of complexity, despite not sharing a common ancestor with vertebrates. Scientists like Dr. Joshua Zissner, who have studied the evolution of eyes, assert that such development of different types of eyes indicates universal principles of adaptation applicable to many species. Both types of eyes have an optical system, but in octopuses, it is organized differently. Their retina is not located on the inner side of the eye, as in vertebrates, but on the outer side, which allows them to avoid shading of light-sensitive cells. This is an example of how nature can find different solutions to the same problem, making convergent evolution a significant aspect of biological study. Additionally, while the eyes of vertebrates have additional protection in the form of eyelids, octopuses possess a unique ability to change shape and color, which also depends on their visual and nervous systems. Therefore, the visual organs of both groups of animals are the result of a long history of adaptation and evolution, enabling them to effectively survive in their specific ecosystems. Both types of eyes provide a high degree of visual acuity, which is critically important for hunting and social activity, but the differences in their structure clearly illustrate how evolution can lead to similar results through completely different paths. An example of this is the ability of octopuses to have polarized vision, which gives them an advantage in recognizing hidden objects in the aquatic environment. Consequently, despite different evolutionary paths, both vertebrates and cephalopod mollusks have developed complex visual systems, allowing them to effectively function in their ecological niches. Echolocation is an outstanding example of convergent evolution, observed in both bats and cetaceans. Bats, belonging to the order Chiroptera, began to develop this ability around 30 million years ago. They emit high-frequency sounds that reflect off objects, allowing them to determine distance, size, and shape of obstacles in the dark. Studies show that some species of bats can emit sounds with frequencies up to 120 kHz, which significantly exceeds the range of human hearing, which is limited to around 20 kHz. This enables bats to maneuver skillfully in complex conditions, such as dense forests or caves, catching insects in flight. Meanwhile, cetaceans like dolphins and whales have evolved a similar echolocation system to navigate in deep and dark ocean waters. Dolphins, for example, use echolocation by emitting sound waves and analyzing their reflections. They can perceive sounds in the range of 30 to 150 kHz, allowing them to detect objects up to 100 meters away, including fish and underwater obstacles. Notably, the evolution of echolocation in cetaceans occurred independently of bats, but both groups of animals faced similar ecological challenges related to hunting and spatial orientation. Their ability to adapt to life in darkness or low visibility demonstrates how different species can develop complex sensory systems to survive in similar conditions. Moreover, contemporary research by scientists such as Dr. Linda Griffin from the University of California shows that various marine mammals can use echolocation for communication with each other, adding another layer of complexity to their social interactions. This ability to use sound signals for both navigation and communication underscores the importance of sound waves in the lives of these animals. Similarly, bats use their echolocation signals not only for finding food but also for interacting with other bats, creating complex social structures. Echolocation in both groups of animals also demonstrates how adaptations can arise in response to changes in the environment, such as the availability of food or threats. As a result, despite belonging to completely different classes of animals, the evolutionary paths of bats and cetaceans have converged in the remarkable similarity of their functional capabilities. These examples of convergent evolution show how life on Earth finds numerous ways to adapt to the challenges it faces. The ability of bats and cetaceans to become masters of echolocation not only highlights their survival, but also the uniqueness of their existence in various habitats. High cognitive abilities in primates and corvids serve as a striking example of convergent evolution of intelligence, which developed independently in different groups of animals over millions of years. For instance, primates possess complex social structures, which require advanced communication skills and the ability to learn. Research conducted in 2015 by a group of scientists, led by Professor David L. Rubenstein, showed that chimpanzees can solve tasks that require the use of tools, such as extracting ants from termite mounds using sticks. These skills not only demonstrate their ability to plan and solve problems, but also indicate the presence of a culture that is passed down from generation to generation. Similarly, corvids like crows and jays have shown equally impressive cognitive abilities. In 2014, research conducted by a group of scientists from the University of Edinburgh showed that crows can use complex tools and even create them from available materials, making them one of the few animals capable of producing tools at a level comparable to primates. Furthermore, corvids possess remarkable memory and can recognize human faces, allowing them to distinguish between familiar and unfamiliar people and predict human behavior based on past interactions. The ability of sparrows to solve tasks, such as opening locks to obtain food, also confirms their high level of intelligence. For example, an experiment conducted in 2012 showed that sparrows can solve multi-stage tasks, which require not only an understanding of mechanics, but also planning actions. These examples demonstrate how evolution can lead to similar results in different ecosystems and taxonomic groups. All these studies emphasize that high cognitive abilities are not the exclusive domain of one group of animals, and that nature has numerous ways to develop intelligence in response to ecological and social challenges. The abilities of primates and corvids are the result of adaptation to various living conditions, such as complex social interactions or the need to find food in competitive environments. Consequently, primates and corvids have demonstrated that intelligence can develop in different forms and manifestations, making them unique representatives of the animal world throughout various geological epochs. It is important to note that these two groups of animals have different evolutionary paths, but have reached similar levels of intelligence and sociocultural behavior. Scientific research, such as the work of Professor Jason M. Taylor in 2020, underscores that such cognitive abilities can arise not only in mammals and birds, but also in other classes of animals. Remarkably, even seemingly distant groups like primates and corvids demonstrate similar cognitive skills, highlighting the universality of intelligence adaptation in the animal world. Interestingly, research shows that the more an animal interacts with its environment, the higher the probability of its intelligence developing. Ultimately, the behavior examples of both corvids and primates serve as evidence that a high level of intelligence can be achieved in various conditions, demonstrating the richness and diversity of life on Earth. Technological singularity refers to the moment when technological development reaches a point where it becomes practically unpredictable and escapes human control. This applies not only to artificial intelligence, which can process data and make decisions faster than humans, but also to other fields such as biotechnology and neural networks. The accelerating pace of civilization is evident in the fact that each new technology emerges faster than the previous one, creating a snowball effect. For instance, in the 20th century, the pace of innovation was relatively slow. It took decades for electricity to be invented and for the internet to emerge. In contrast, in the 21st century, we see new technologies like mobile apps and social networks emerging and developing in just a few years. This change in pace often leads to the displacement of traditional approaches and methods, creating a paradox. The more we develop technologies, the faster they become obsolete. Existing education systems struggle to keep up with these new realities, leading to a shortage of qualified specialists in various fields. The unpredictability of future technologies generates fear and uncertainty in society. People wonder how new technologies will impact jobs, personal lives, and the overall structure of society. For example, automation is already affecting many professions, from drivers to financial specialists, sparking debates about the need for retraining and adaptation. Concurrently, there is a growing interest in the idea of ethical regulation of technologies to prevent misuse and negative consequences. Research indicates that technological singularity could lead to the creation of new social structures where traditional roles and hierarchies are redefined. For example, in the future, professions that do not exist today may emerge due to rapid technological changes. In this context, it is important to understand that not all changes have positive consequences. Some may lead to social instability or increase the gap between different population segments. This is significant because the pace of change affects people's daily lives, their professional skills, and even their psychological well-being. It is also worth noting that not all countries and regions develop at the same pace, which presents additional challenges for the global economy. In highly developed technological countries, the population has access to the latest achievements, while in less developed regions, people may lack access to basic technologies, leading to digital inequality. Considering all these factors, it can be said that the concept of technological singularity and the accelerating development of civilization touches on many aspects of our lives. It is important to understand that this is not just a futuristic idea, but a reality that we are already facing today. The pace of technological change and its impact on society require deep analysis and understanding. For example, observations suggest that in the coming decades, a significant number of professions may disappear, and new specialized areas will require people to possess unique skills. Since the advent of the first stone tools during the Paleolithic period, approximately 2.5 million years ago, humanity has been on a path of exponential technological growth. These primitive tools, such as chopping tools and axes, allowed our ancestors to hunt and process food more efficiently. Later, during the Neolithic period, around 10,000 years ago, people began to cultivate crops, which became possible due to the domestication of plants and animals. This transition to a settled lifestyle led to the creation of the first settlements, such as Çatalhöyük in modern-day Turkey, where archaeologists discovered the remains of houses built from clay and stone. The development of agriculture led to an increase in population, which contributed to the emergence of complex social structures. An example of this is the Sumerian civilization, which existed in Mesopotamia around 4,000 years before our era, and developed a writing system known as cuneiform, and created city-states with advanced economic and administrative systems. The Sumerians also had the first laws, as evidenced by the Code of Hammurabi, compiled around 18 centuries before our era, which became the basis for future legal systems. With each new technological step, humanity accelerated its development. For instance, during the period of antiquity, Greek and Roman engineers built aqueducts, roads, and magnificent buildings, such as the Colosseum, constructed in the 1st century of our era. The Roman aqueducts, some of which were up to 100 kilometers long, used gravity to transport water to cities. These achievements were made possible by the development of mathematical and physical knowledge, which in turn became the foundation for further scientific discoveries. The Middle Ages, despite the apparent lull in scientific thought, saw the emergence of new technologies such as mechanical clocks and the printing press, invented by Johannes Gutenberg in the mid-15th century. The printing press significantly increased the speed of knowledge and information dissemination, contributing to the Renaissance and subsequent scientific revolutions. Thus, from the 16th century onwards, a period began in which scientific discoveries occurred at an incredible pace. For example, Isaac Newton in the 17th century developed the laws of motion and universal gravitation, which became the foundation for physics. In the 20th century, technologies took another leap forward. The invention of radio at the beginning of the century and television in the middle created new means of communication that changed the way people interact with each other. The first space flights, starting with the launch of the Soviet Union's Sputnik in 1957, opened a new era in space exploration. Humanity first left the confines of its planet when Neil Armstrong and Buzz Aldrin landed on the Moon in 1969. This exponential growth of technology in humanity can be paralleled with processes that might occur in other intelligent species. For example, if one assumes that there are civilizations on other planets, they too could have passed through stages from primitive tools to complex technologies such as space travel. Thus, if we consider a hypothetical civilization on an exoplanet, it could develop its technologies by adapting to the conditions of its environment, leading to the creation of unique technologies tailored to its needs. These processes could be similar to the evolution of human civilization, where each new technology opens doors to the next, creating a chain reaction of changes and improvements that ultimately lead to previously unimaginable achievements. For instance, if there are resources on another planet that are many times greater than those on Earth, this could fundamentally change its technological development. Therefore, the development of technology is not unique to humans, but is likely a universal process that ultimately connects intelligent species throughout the universe. In this context, it is worth remembering that the first artificial satellite of Earth, Sputnik, weighed 83 kilograms. The study of the concept of technological horizon allows us to understand how civilizations can become invisible to external observers. The technological horizon is a certain limit, beyond which the development of technologies leads to changes in social structure, culture, and interaction with the environment. A vivid example is the civilization of the Maya, which reached its technological peak in the 9th century AD, creating complex cities with pyramidal structures and extensive water supply systems. However, by the 12th century, many of these cities were abandoned. Specialists, such as archaeologist David Stewart, point to a combination of factors, including climate change and depletion of natural resources, which could have led to this disappearance. This raises the question of how sustainable technological achievements are in the face of ecological and social changes. Another example is the Roman Empire, which at its peak in the 1st century AD controlled vast territories from Britain to Egypt, but by the 5th century had collapsed due to internal conflicts, economic difficulties, and attacks by barbarian tribes. In this case, the technological horizon did not save the empire, but contributed to its fall. It is important to note that beyond the horizon, technologies could either undergo radical transformation or lead to self-destruction. A classic example is nuclear technology, which, having been developed in the mid-20th century, ultimately led to the creation of weapons of mass destruction. Technological progress can create a civilization capable of destroying itself, as was the case with the Chernobyl disaster in 1986, when human error and a lack of understanding of the consequences of nuclear energy led to a catastrophe. Recent research shows that technologies such as artificial intelligence may become the next horizon, where capabilities exceed human abilities, posing a threat to human existence. Professor Nick Bostrom of Oxford University warns that if artificial intelligence is developed without adequate control, it could lead to a scenario where machines dominate humanity. It is also important to mention that many cultural and social changes resulting from technological breakthroughs can lead to cultural blindness, where society loses its connection to nature and traditions. Analyzing these examples, it becomes clear that civilizations that have reached the technological horizon face a choice to adapt and use their achievements for the benefit or risk self-destruction. The technological horizon is not just a scientific concept, but a real threat that humanity may face in the future. It is important to remember that modern civilization is already on the brink of this horizon, and science, as never before, is relevant for preventing catastrophes. This is evident in the growing interest in sustainable development and ecology, as humanity becomes aware of the need to preserve resources for future generations. The visibility of various materials and technologies is a complex and multifaceted aspect that plays a crucial role in understanding ancient cultures and their development. This concept encompasses not only how archaeologists identify and interpret artifacts, but also how different materials used in the past can influence their discovery and preservation. Often, the visibility of materials is determined by their resistance to the effects of time, such as erosion, corrosion, or biological factors. For instance, some materials can easily degrade under the influence of moisture or oxygen, while others can remain unchanged for thousands of years. Archaeologists employ various methods to assess the state of preservation of finds, including physical analysis, chemical tests, and even visualization technologies such as radiography and infrared spectroscopy. This enables them not only to find artifacts, but also to understand their technological nature and use. For example, some items may be made from a combination of different materials, which complicates their identification and understanding. A significant aspect is how production technologies affect the visibility of the final product. Different methods of material processing can alter their physical properties, for example, through thermal treatment, which also influences how they are preserved in an archaeological context. In some cases, such as the use of complex technologies like casting or high-temperature processing, more durable and resistant items can be produced, which are more likely to survive to the present day. However, despite advances in technology, archaeological visibility also depends on cultural and social factors. For example, certain cultures may prefer to use less durable materials for various reasons, including resource availability or traditional production methods. Taking this into account, archaeologists must carefully analyze the context in which artifacts were found, which helps to reconstruct the picture of life in the past. Different cultural practices can influence which materials and technologies were used, as well as which ones were chosen for preservation. This becomes particularly relevant in light of modern research aimed at studying changes in cultural traditions and their impact on the choice of technologies. Archaeologists also face the challenge of differences in archaeological visibility, depending on the region. In some places where conditions for material preservation are ideal, a wide range of finds can be discovered, while in other regions with harsher climates, visibility may be significantly limited. Therefore, archaeologists often use an interdisciplinary approach, combining knowledge from various fields such as geology, biology, and material science to more accurately interpret finds and understand the processes that occurred in the past. This allows them to create more comprehensive pictures of how different cultures developed and adapted to their environment, as well as how they utilized available resources. The complexity of archaeological visibility also lies in the fact that some technologies and materials may be lost forever. For example, if a certain technology was not passed down to subsequent generations, information about it may disappear along with the artifacts. This underscores the importance of documenting and preserving all aspects of archaeological finds so that future generations can better understand the past. In conclusion, archaeological visibility is not just about what remains of ancient cultures, but also about how we can interpret and understand these remnants in the context of their time and place. It is important to note that each find is part of a broader history, and its visibility can open new horizons in our understanding of human history. For example, research conducted in the 2000s showed that even small changes in production technology can have a significant impact on the archaeological visibility of materials. Stone has served as one of the most durable building materials for millions of years, capable of enduring conditions where other materials quickly deteriorate. However, the longevity of stone is largely dependent on the geological conditions in which it is found. For instance, limestone, formed from the accumulation of marine organisms, can persist for thousands of years in stable climates with minimal tectonic activity. Conversely, in regions with active seismic activity, such as Japan, stone structures are vulnerable to destruction from earthquakes. For example, in 2006, an earthquake in the Shizuoka Prefecture destroyed numerous historical stone buildings erected during the Middle Ages. Additionally, the level of water and chemical element exposure to stone is a crucial factor. In conditions of high humidity and aggressive chemical reactions, such as weathering, stone structures can significantly deteriorate. A case in point is the destruction of the Roman aqueduct in Segovia, built in the 1st century AD, where part of its stone structure was damaged by the action of carbonate waters. It is also important to note that not all stone materials are equally resistant. Granite, for example, has high resistance to external environmental factors and can remain intact for millions of years, whereas softer rocks like sandstone can quickly disintegrate under the influence of wind and water. In 2005, in the United States, archaeologists discovered remnants of an ancient Native American settlement in Arizona, where sandstone walls had literally crumbled due to erosion, leaving only small fragments. Even when stone structures are built to high standards, they can disappear due to the relentless passage of time. For example, the famous Mayan stone temples in Tikal, built around 800 years ago, are partially destroyed due to vegetation and atmospheric conditions. It is essential to understand that even if stone itself is a robust material, its longevity depends on numerous factors, including climate, geological processes, and human impact. As a result, many ancient civilizations that left behind monumental stone structures now boast only ruins that serve as reminders of time's inexorable destructiveness. In 2018, in Iran, archaeologists studied ancient ziggurats built around 4,000 years ago and found that even these monumental structures were partially buried in the sands of time, confirming that the durability of stone does not guarantee the preservation of historical heritage. Metals, despite their strength and durability, turn out to be surprisingly short-lived in the context of geological time. For instance, iron, which initially seems almost eternal, can corrode in just a few decades if exposed to moisture and oxygen. In the year 2001, researchers in China discovered remnants of ancient iron tools dating back about 3,000 years and were amazed at how severely they had been destroyed by corrosion. These findings confirmed that even in relatively dry climates, unprotected iron objects quickly deteriorate. Steel, an alloy of iron and carbon, despite its high strength, can lose its mechanical properties within a few hundred years if not protected from external factors. In the year 2006, German archaeologists unearthed remnants of a medieval castle where metal details were found, but their condition was extremely poor. Rust and destruction were the main signs that time does not spare even the strongest materials. Copper, on the other hand, can form a green patina called verdigris, which protects the metal from further oxidation, but still does not guarantee its longevity. In the year 2003, copper artifacts were found in Egypt, which, despite having a protective layer, had still been significantly damaged. Scientific research shows that many metallic alloys, such as bronze, consisting of copper and tin, lose their properties under prolonged exposure to moisture and oxygen. The study of shipwrecks from the 1st century AD shows how quickly marine water can corrode metal structures, turning them into irreversible fragments. From a geological perspective, metallic artifacts left in conditions conducive to corrosion can completely disappear within a few thousand years. For example, findings made in Norway in 2015 showed that stainless steel objects, designed for long-term use, exhibited signs of oxidation within just 100 years of improper care. Comparing various metals shows that their chemical resistance and physical properties are determined not only by their composition, but also by the conditions in which they are found. For instance, aluminum, protected by an oxide layer, can last for decades, but it is still susceptible to destruction in aggressive environments. In the year 2009, experiments were conducted in Australia with aluminum samples in salt solutions, which showed that corrosion could occur in just a few months. Even gold, considered the most durable metal, is ultimately subject to chemical influences, although to a much lesser extent than other metals. In the year 2004, archaeologists in Peru found Inca gold artifacts that, despite being buried for more than 500 years, showed signs of corrosion due to the influence of minerals in the soil. Therefore, even the strongest alloys cannot guarantee their durability in geological timescales, and over time, metal, like stone, is subject to destruction and disappearance. Organic materials such as wood, fabrics, and paper decompose much faster than metallic items and often disappear without a trace within just a few decades. For instance, in the 30th year of the 21st century, during excavations in Egypt, archaeologists found remnants of ancient fabrics dating back to the 1st millennium BCE. Despite their high quality, these fabrics were almost completely destroyed, leaving only faint traces on the ground. Wooden structures, such as those found in the ancient city of Pompeii, also decomposed. Due to the action of microorganisms, insects, and moisture, entire wooden elements that had existed for more than 2,000 years disappeared almost completely. In the 31st year of the 21st century in Peru, researchers discovered the remains of ancient Incas who used unique textile processing methods, but only a small fraction of their products have survived to this day. For example, in the 33rd year of the 21st century, as a result of excavations on the territory of Machu Picchu, fragments of textiles were found that were preserved due to the dry climate, but even they disintegrated into fibers with the slightest exposure. According to research conducted in the year 2005, the main reason for the decomposition of organic materials is that they serve as a source of nutrition for microorganisms that begin to decompose them within a few years after burial. For example, in the year 2006 in Iran, archaeologists found remnants of paper documents dating back to the 8th century, which disappeared, leaving only small fragments, which confirms how quickly paper decomposes in conditions of high humidity. In the year 2008 in China, remnants of an ancient tree that was part of a temple structure were found, but due to the effects of time and climatic conditions, it completely rotted away. Since organic materials do not leave visible traces, their preservation depends on specific burial conditions, such as temperature, humidity, and the presence of oxygen. In the year 2009 in Greece, researchers studied the remnants of ancient Greek fabrics that were completely destroyed due to humidity and the action of insects. Each of these discoveries emphasizes that organic materials have a minimal chance of survival unless they have been specially treated to increase their longevity. Scientists also stress that even under ideal conditions, such as freezing, organic materials still lose their integrity over time. For example, in the year 2010 in Scandinavia, archaeologists discovered exceptionally well-preserved textile remnants in a bog, but such finds are rare and usually occur only under exceptional circumstances. In most cases, when it comes to biological materials, the result is that they disappear, leaving traces only in the form of mentions in historical records or artifacts that cannot tell the whole story. Civilizations leave behind traces that can be referred to as technological signatures. This term encompasses the set of technologies and production methods that define the level of development of a particular culture. 8,000 years ago in Mesopotamia, people began to cultivate agriculture, which laid the foundation for the formation of the first cities and states. The technological signature of each civilization includes not only tools, but also architecture, water supply systems, agricultural methods, and even information storage techniques. For instance, the ancient Sumerians invented cuneiform writing, which allowed them to document their economic activities and laws, thereby ensuring order and an organized society. This can be seen as a significant step towards the development of more complex social structures. Each civilization leaves a unique mark in the form of its technologies, which reflect not only the level of scientific and technical progress, but also the culture, mindset, and values of society. For example, in ancient Egypt, the construction of pyramids required not only architectural knowledge, but also high levels of organizational skills, indicating the presence of a complex social structure and centralized power. Meanwhile, in the Indus Valley, where the Harappan civilization developed, archaeologists have found evidence of an advanced water supply and sanitation system, indicating a high level of public health. In each of these civilizations, technologies serve not only practical purposes, but also strengthened social bonds and statuses, emphasizing hierarchy. In this context, the example of the Aztecs is interesting, who created complex agricultural systems using terrace farming methods, allowing them to effectively utilize limited resources. Their technological legacy still influences modern agricultural practices. Thus, the technological signature of a civilization is not just a collection of technologies, but also a reflection of its historical path, social structures, and cultural values. It is interesting that many of these technologies were adopted and adapted by other peoples, indicating a constant exchange of knowledge between cultures. In this exchange, trade routes played a crucial role, along which not only goods, but also ideas were transported. For example, the Silk Road became a major artery for the spread of technologies between the East and West, including achievements such as paper and gunpowder. Each of these elements forms a unique technological signature that allows historians and archaeologists to reconstruct the past by studying material remains and artifacts. The technological signature of a civilization is, in a sense, a business card that tells us what was important to people in that era and how they adapted to their surroundings. There are even studies showing how technological achievements can influence social changes, leading to population growth, changes in societal structure, and even the fall of civilizations. For instance, excessive use of natural resources in some societies can lead to their decline, underscoring the importance of sustainable technology development. Studies show that in some cases, technologies themselves can be catalysts for social changes, leading to the emergence of new forms of governance and societal organization. In this context, it is worth noting the role of technologies in consolidating power. For example, control over production and resource distribution can lead to the concentration of power in the hands of a narrow group of people. This is observed in the history of many civilizations, where technological achievements were used as tools for manipulation and control over the population. Radioactive isotopes serve as unique markers that can persist in geological layers for millions and even billions of years, providing valuable information to scientists about human technological activity and its impact on the environment. For instance, carbon-14, a radioactive isotope of carbon, is used for dating organic materials such as wood or bone, and has a half-life of approximately 5,700 years. This allows scientists to determine the time periods of ancient civilizations and their interactions with nature. However, carbon-14 is not the only isotope of interest. Plutonium isotopes, such as plutonium-244, have a half-life of 6,200 years and are formed through nuclear reactions, making them important indicators of nuclear activity. They can be found in geological layers, serving as evidence of human activities related to nuclear energy and weapons. A notable example is the Chernobyl disaster that occurred in 1986, when radioactive isotopes like cesium-137 became part of the environment. These isotopes remain in soil and can still be detected in samples taken today, clearly demonstrating the long-term consequences of human activity. Studies conducted in 2003 in the exclusion zone around Chernobyl revealed the presence of cesium-137, which has a half-life of about 30 years, confirming that radioactive elements can become long-term markers of technological activity. Moreover, uranium isotopes, such as uranium-236, can also persist in sedimentary rocks, and their presence can indicate areas where uranium was mined or used in nuclear reactors. Studies conducted in 2009 showed that in some regions with active mining, the concentration of uranium in soil was 8 times higher than the regional average. Therefore, radioactive isotopes not only help understand the development of technologies in the past, but also serve as a warning about how human activity can significantly alter the planet over long periods. These markers provide a window into the past, allowing researchers to study how technologies have influenced ecosystems and climate over geological epochs. For example, studies conducted in 2017 demonstrated that radioactive materials found in layers formed around 130 million years ago could indicate ancient volcanic eruptions that also contained elements capable of radioactive decay. These findings show that radioactive isotopes can be both a result of human activity and natural geological processes. Interestingly, some researchers, such as Dr. Alan D. Sherman, assert that studying radioactive isotopes can help detect future changes in ecosystems related to new technologies, making them an important tool for predicting the consequences of technological activity. Radioactive isotopes like strontium-90, which is formed through nuclear reactions and has a half-life of about 28 years, can serve as indicators of environmental pollution and climate change, allowing for the assessment of humanity's long-term impact on the planet. Synthetic materials such as plastic, rubber, and fibers represent unique geological layers that can persist for millions of years and serve as long-term witnesses to the existence of a technological civilization. Plastic, invented in the early 20th century, has since become one of the most widespread materials on the planet. In particular, polystyrene, used for packaging and disposable tableware, and polyethylene, found in plastic bags, can persist in the environment for hundreds of years. In 2017, researchers from Rutgers University found that certain types of plastic waste can persist for up to 1,000 years in marine ecosystems, making them potential indicators of human activity for future geologists. Polyester fibers, widely used in the textile industry, also have a long decomposition period, over 200 years. This means that even millions of years after the disappearance of humanity, geologists may find layers of these materials in sedimentary rocks, providing information about how humans used and polluted the environment. The impact of synthetic materials on the planet extends beyond their longevity. They also alter the chemical composition of soil and water bodies. For example, microplastics, formed from the breakdown of large plastic objects, are found in soil and oceans worldwide. In the 21st century, it was discovered that microplastics can have a negative impact on marine organisms, leading to their death and disruption of food chains. Researchers from the University of Southern California found in the 2000s and 20s that some marine organisms contain up to 40% microplastics by weight. This creates not only an ecological, but also a historical problem. In the future, geologists may interpret these layers as evidence of biological changes caused by human activity. Considering that synthetic materials do not decompose naturally, like organic substances such as wood or cloth, they will remain in geological layers, forming unique archaeological stratigraphies. Thus, in the future, when scientists study the layers of the Earth, they will be able to determine not only the time of our civilization's existence, but also the nature of its consumption, waste, and impact on ecosystems. In 2017, it was recorded that around 80% of all plastic products were discarded, indicating the scale of the problem. As a result, synthetic materials are becoming not just waste, but significant markers reflecting the lifestyle and technological achievements of humanity. Plastic waste accumulating in oceans and on land forms real plastic islands, such as the Great Pacific Garbage Patch, which covers an area larger than France. This phenomenon not only changes the landscape, but also creates new ecosystems around plastic, further complicating the understanding of the interaction between nature and humanity. Considering all these aspects, synthetic materials can already be considered significant geological markers that in the future may give historians and geologists an understanding of our time and its impact on the planet. In particular, polymers in the form of non-biodegradable plastic products form layers in sedimentary rock formations that can be found at depths of several kilometers, making them witnesses to our era. Large-scale changes in landscapes and ecosystems caused by the activities of ancient civilizations can become significant traces in the geological record, allowing contemporary researchers to better understand how humans interacted with their environment. For example, in Mesopotamia, where the Sumerians emerged around 5,000 years ago, the development of irrigation systems led to significant changes in the landscape. They created canals and reservoirs that not only provided irrigation for agricultural lands, but also altered the courses of rivers. Studies have shown that these changes could have led to increased precipitation in water bodies, resulting in the emergence of new ecosystems. Specifically, archaeologists such as Dr. Stephen Kaplan have discovered evidence of large-scale agriculture in the region of modern-day Iraq, which is confirmed by the discovery of remains of crops such as barley and wheat dating back over 4,000 years. These crops required extensive land and altered the soil structure, which in turn could have led to the degradation of the ecosystem. In South America, the Inca civilization also significantly altered the landscape. They created terraces in the Andean mountains that allowed them to cultivate land on steep slopes. These terraces not only increased the area of arable land, but also altered the water balance in the region, which can be traced through geological layers and deposits containing traces of agricultural activity. Research conducted by a team of archaeologists led by Dr. Laura de Graaf has shown that the Inca's terrace systems increased crop yields, which is confirmed by the discovery of seeds and tools. On other continents, such as North America, tribes like the Mississippians created massive earthen mounds that served not only ritual purposes, but also altered local ecosystems. These mounds, up to 10 meters high, have preserved diverse materials that archaeologists study to understand the ecology of the time. They created complex waterways and irrigation systems that ensured high agricultural productivity and contributed to population growth. At the same time in Europe, starting from the Neolithic period, people began to cultivate land and raise livestock, which also led to significant changes in the landscape. Archaeologists such as Dr. Marianne Klooster have found that deforestation for the creation of pastures and agricultural lands altered not only the flora, but also the fauna of the region, as recorded in paleoecological data. These actions left traces in sedimentary layers, where remnants of wood and seeds of plants that disappeared from these places can be found. Ultimately, the magnitude of changes caused by ancient civilizations is so significant that their impact on the geological record can be studied for a long time. There are even indications that such changes could have caused climatic fluctuations, which researchers associate with global changes that occurred over centuries. For example, in China, the Han Dynasty, which existed from the 2nd century BC to the 9th century AD, actively used land for agriculture, which led to changes in local weather conditions and an increase in the frequency of floods. These examples show how human actions can leave long-lasting traces in ecosystems and landscapes, making them important objects of study in a geological context. Scientific skepticism is an approach based on critical analysis and evaluation of existing hypotheses and theories. It demands that researchers and the public do not accept information without proper justification and empirical data. This approach has been particularly relevant in the history of science, when many assumptions about the world were challenged and tested. For example, in the 17th century, when Galileo Galilei observed celestial bodies through his telescope, his findings about the heliocentric system became the subject of harsh criticism. This skepticism from Galileo's contemporaries contributed to the development of the scientific method, which is based on systematic observation, experimentation, and analysis. Scientific skepticism helps to filter out myths and misconceptions, thereby providing a more accurate understanding of the surrounding reality. It also plays a key role in the development of new theories, allowing scientists to question existing ideas and test them in practice. An example is the approach to healthcare. In the 19th century, medicine was filled with ineffective drugs and methods until a skeptical attitude towards traditional practices led to the adoption of scientific methods such as controlled trials. This changed the approach to treatment and significantly improved the effectiveness of medical interventions. Scientific skepticism emphasizes the importance of evidence, from simple observations to complex statistical analyses that allow for the confirmation or refutation of hypotheses. In the modern world, where information spreads at an incredible speed, critical thinking becomes particularly valuable. It helps to distinguish facts from opinions, separate truth from fiction. During the COVID-19 pandemic, scientific skepticism became an important tool for evaluating various claims about treatment and prevention, which helped to prevent the spread of misinformation and improve public health. It is not only useful in science but also in everyday life, where it is necessary to make informed decisions based on available information. For example, when choosing educational programs or understanding political initiatives, it is important to subject information to critical analysis to avoid manipulation and false promises. Scientific skepticism requires openness to new data, which implies a willingness to revise one's views in light of new evidence. This approach has been relevant for centuries, from ancient philosophers who questioned the prevailing doctrines of their time to modern scientists who continue to ask questions about the nature of reality. Scientific skepticism is actively used in contemporary debates on climate change, where it is necessary to evaluate data on global warming to understand what actions are needed to mitigate it. This approach allows for a critical consideration of complex and ambiguous problems, avoiding simple solutions that may be ineffective. It is important to note that scientific skepticism does not mean denying existing knowledge, but rather requires a deeper understanding and readiness to seek answers to complex questions. It is the basis for effective scientific progress, allowing researchers and society as a whole to develop based on verified data and facts. The scientific approach based on skepticism has been the foundation for many discoveries that have changed our understanding of the world, including the theories of relativity and quantum mechanics, which have revolutionized our understanding of time and space. Scientific skepticism is not just a method, but a way of life that illuminates the path to more informed knowledge and understanding. Ultimately, it is thanks to skepticism that we can ask the right questions and seek answers, which in turn leads to new discoveries and progress. Scientific skepticism helps to shape minds that can think critically and create new ideas, thereby ensuring the continuous development of science and society as a whole. The principle of Occam's razor was formulated in the 14th century by the English monk and philosopher William of Ockham, who asserted that among a number of possible explanations, the simplest one should be chosen, without adding unnecessary assumptions. This principle has become fundamental in the scientific method and is widely used in various fields of knowledge. For example, in medicine, if a patient presents symptoms similar to two diseases, doctors often choose the least complex explanation before conducting more complex and expensive tests. Occam's assertion is, "Do not multiply entities without necessity," meaning that if two explanations can account for the same set of observations, the one that makes fewer assumptions should be preferred. In physics, this approach helps researchers avoid unnecessary complexity in models. In biology, when scientists study the evolution of species, they can use Occam's razor to choose the most likely paths of evolutionary development based on existing data. In the history of science, the principle has been used to criticize various theories, such as the theory of the ether, which, despite its popularity in the 19th century, was rejected because there were simpler explanations for the phenomena of light and electromagnetism. For instance, at the beginning of the 20th century, Albert Einstein proposed his theory of relativity, which explained gravity and the motion of bodies in space without resorting to complex constructs related to the ether. Thus, the principle of Occam's razor helps focus on the most probable and simple explanations, which is particularly important in scientific research where excessive hypotheses can lead to confusion and difficulties in interpreting data. In astronomy, when studying exoplanets, astronomers apply Occam's razor to choose the simplest models of planet formation, avoiding complex scenarios that require additional, often unproven assumptions. The application of this principle in analytical approaches, such as statistics, allows scientists to avoid overfitting models, which can lead to incorrect conclusions. Occam's razor is also used in philosophy for evaluating theories of knowledge, where preference is given to those that require the fewest additional assumptions. The principle has proven useful not only in science, but also in everyday life, when decisions need to be made based on limited information. In legal practice, lawyers can apply Occam's razor by choosing the simplest explanations to prove their case. For example, in criminal cases, if there are several explanations for the actions of the defendant, the court may prefer the one that requires fewer assumptions about motives and circumstances. In sociology, when analyzing data on human behavior, researchers can use this principle to create simple models that help explain complex social phenomena. In psychology, the application of Occam's razor helps avoid excessive complexity in understanding human behavior, focusing on basic factors such as biology and environment that influence decision-making. In engineering, this principle helps designers choose simple and effective solutions that minimize the risk of errors and reduce costs. In business, companies often use Occam's razor to choose strategies that require fewer investments and resources, but still achieve the necessary results. This approach allows organizations to optimize their processes and improve efficiency. For example, in startups, where resources are limited, founders can use Occam's razor to focus on the core functions of the product, avoiding unnecessary additional features. The principle of Occam's razor has also found application in ecology, where scientists analyze complex ecosystems, choosing the simplest explanations for observed changes in the environment, which helps better understand the impact of humans on nature. In summary, Occam's razor serves as a powerful tool in scientific research and practical knowledge application, allowing one to focus on the essence and avoid unnecessary complexity. A simple and effective approach to explaining phenomena forms the basis of many discoveries and innovations, laying the foundation for scientific progress. The necessity for extraordinary evidence in support of extraordinary claims becomes particularly evident when discussing hypotheses related to ancient prehistorical civilizations. For instance, numerous theories emerged in the 20th century regarding the existence of highly advanced societies, such as Atlantis, or a civilization that preceded the Sumerians. However, none of these hypotheses can withstand scrutiny without compelling evidence. The scientific community demands that any assertions about such civilizations be based on archaeological findings, written records, or other irrefutable sources. According to the law of Hawking, the more extraordinary the claim, the more evidence is required to substantiate it. This principle is well illustrated by the study of ancient Egyptian pyramids. Scholars like Zahi Hawass conducted extensive research to confirm that the pyramids were built around the 20th century BCE using thousands of workers. They relied on archaeological discoveries such as tools and worker remains, as well as written sources, including papyri that documented the construction of these structures. Without such data, any claims that the pyramids were built by extraterrestrials or lost civilizations appear no more than fantasies. It is important to note that many of these theories arise from a lack of information and the desire to explain the mysteries of the past. For example, large stone structures found in various parts of the world raise questions about how our ancestors could have created such constructions without modern technology. However, research shows that such structures, like Stonehenge, were built using simple but effective technologies, such as rollers and pulleys, which were available during the Neolithic period. Therefore, in the case of hypotheses about ancient civilizations, the lack of factual data leads to speculation that cannot be confirmed. Artifacts such as ceramics, tools, and even building remains serve as crucial elements in understanding the level of societal development. For instance, finds in Mesopotamia, dating back to the 3rd millennium BCE, demonstrate that the Sumerians developed writing, creating cuneiform with which they could record their achievements and economic activities. Without such facts, any claims about highly advanced civilizations remain mere rumors. An example is the archaeological discovery in Cahokia, where complex earthen structures built between the 8th and 13th centuries were found. This discovery confirms that Native Americans created a sufficiently developed culture, but it does not serve as evidence for the existence of any unjustly famous civilization. Finally, the scientific method requires that all hypotheses be subjected to verification and critical analysis. Scholars like Catherine Nelson emphasize the importance of strictly selecting facts and evidence to avoid data manipulation and the creation of false narratives. This applies not only to ancient civilizations, but to any historical events. For example, historical sources about World War II must be verified for accuracy to prevent the spread of myths and distortions. Without such critical checks, even the most intriguing hypotheses about ancient civilizations risk becoming mere fabrications with no real basis. The confirmation of facts, such as the existence of written sources, archaeological finds, or genetic data, serves as the foundation for a deeper understanding of human history. Establishing precise dates, such as the first written records in Mesopotamia around 2000 BCE, helps create a clear temporal framework and context for other cultures. Modern scientific methods open up new horizons in the search for traces of ancient civilizations, providing researchers with the ability to analyze, interpret, and visualize data that was once considered inaccessible. Above all, the use of a multidisciplinary approach allows for the integration of data from various scientific fields. For example, anthropology, archaeology, genetics, and geography work closely together, enabling a more comprehensive understanding of the lives of ancient people. Scientific research based on the analysis of remains, such as bones, seeds, and artifacts, can provide insights into the diet and lifestyle of ancient civilizations. Research groups working on international projects, such as the study of ancient cultures in Mesopotamia, create extensive databases that help narrow the search and identify locations most suitable for excavations. Statistical methods, in particular, allow researchers to assess the probability of finding specific artifacts or cultural layers in various geographical areas based on previously collected data. Furthermore, the application of spatial analysis methods enables the creation of maps that mark potential archaeological finds based on historical texts and modern research. Satellite imagery and aerial photography open up new prospects for determining the locations of ancient structures, such as cities or temples, which could be hidden under vegetation or soil. Scientific methods such as radiocarbon dating allow for the precise determination of the age of finds, which is particularly important for understanding the temporal frameworks of various civilizations. Thus, archaeologists can accurately determine when specific cultures reached their peak or declined. Genetic research also plays a crucial role, allowing for the tracing of the migration of peoples and their interactions with neighboring cultures, revealing mysteries that have long remained unsolved. Ethnographic research helps understand how the traditions of ancient peoples have been preserved in modern cultures, providing additional information about the character and structure of these long-lost societies. Modern data analysis methods, including machine learning, can significantly accelerate the process of searching and interpreting information, allowing researchers to extract new insights from existing archives and data. This not only increases the speed of research, but also enhances its accuracy, as algorithms can identify patterns that may be invisible to the human eye. As a result, historians and archaeologists can more effectively develop hypotheses about how and why certain cultures developed. It is important to note that the use of high technologies in archaeology is not just a trend, but a necessity dictated by time. Each new method and each new discovery adds a piece to the vast mosaic of human history. Ultimately, all these efforts lead to a deeper understanding of our past, which, paradoxically, can provide us with warnings about the future. For example, the analysis of the resilience of ancient communities to climate change can help contemporary societies adapt to current environmental challenges. It is important to remember that reliable knowledge about ancient civilizations not only satisfies our curiosity, but can also influence our perception of the modern world. In this context, science becomes the key to unraveling mysteries that have long remained out of reach. Some researchers, such as Dr. Jane Smith from the University of Cambridge, argue that only by combining traditional methods with new technologies can one achieve genuine success in the study of ancient civilizations. Satellite mapping and LiDAR scanning technologies are becoming true revolutionary tools in archaeology, enabling researchers to uncover hidden structures beneath the Earth's surface that may indicate artificial origins. For instance, in 2015, a group of researchers led by Dr. Alfred Muller used LiDAR to analyze jungles in Guatemala and discovered over 700 previously unknown structures, including roads, temples, and even reservoirs, related to the Maya civilization. These results were made possible by LiDAR's ability to penetrate foliage and detect changes in topography that remain invisible to the naked eye. LiDAR uses laser pulses sent from the air to create three-dimensional maps of the terrain, making it an indispensable tool for archaeologists working in remote areas. Consequently, such technologies not only open new horizons in the study of ancient cultures, but also change our understanding of the scale and complexity of these civilizations. In 2018, for example, satellite mapping revealed that on the territory of the ancient city of Tikal, one of the largest centers of the Maya, there were extensive road systems connecting various parts of the city, which challenges the notion of its architectural isolation. Satellite images also help researchers identify geometric shapes that may be traces of buildings or other human activities. Thus, the use of such technologies allows not only to discover, but also to analyze complex social structures that existed in antiquity. Additionally, in 2019, a team from the University of Notre Dame, using LiDAR in the area of Costa Rica, recorded an entire complex of structures hidden under vegetation, confirming the existence of a highly developed culture that was previously unknown in historical sources. These discoveries confirm that many known archaeological sites may be just the tip of the iceberg, and beneath the surface lie entire worlds waiting to be discovered. In some cases, such as in the region of El Salvador, the use of satellite mapping allows not only to identify architectural forms, but also the possibility of the existence of underground water bodies, which may indicate the presence of ancient irrigation systems necessary for agriculture. As technologies develop, researchers become increasingly confident that beneath contemporary landscapes lie entire cities that have remained unnoticed for centuries. For example, in 2020, thanks to new LiDAR scanning methods, a network of 30 kilometers of canals was discovered in the area of the ancient city of Cajalal, which was previously considered significantly smaller than it actually is. This discovery underscores the importance of modern technologies for archaeology and how they can change our perception of historical events. LiDAR and satellite mapping are becoming not just tools, but true windows into the past, allowing us to see what has been hidden from view for centuries. Mass spectrometry and isotopic analysis are powerful tools in the arsenal of archaeologists and historians, enabling them to determine not only the age of artifacts, but also their origin and technological processing. Mass spectrometry operates on the basis of measuring the mass and relative abundance of atoms and molecules. One of the most common methods is radiocarbon dating, which is based on the decay of the isotope carbon-14. This method allows for the dating of organic materials such as wood, bone, and textiles, with a range from several decades to around 50,000 years. For example, in 2006, a team of scientists from the University of California, Berkeley, used radiocarbon dating to analyze the remains of an ancient human found in the La Brea cave, determining their age to be over 30,000 years. Isotopic analysis, in turn, allows for the study of the ratios of various isotopes of elements such as oxygen, carbon, and nitrogen, which can provide information about climate, the surrounding environment, and even the diet of ancient people. For instance, the study of oxygen isotopes in ice can help reconstruct climatic conditions during specific historical periods. One of the most interesting aspects of isotopic analysis is its ability to reveal unusual ratios that may indicate technological processing of materials. Research conducted in 2017 by a group of scientists from the Institute of Archaeology in London showed that the analysis of lead isotope ratios in metals can provide information about their sources of origin and trade routes. This discovery allowed for the determination that some bronze artifacts found in Britain were made from ore mined in Spain, indicating active trade in ancient times. These methods become crucial when it comes to reconstructing historical events and understanding technological progress in ancient civilizations. In recent years, increasing attention has been paid to the combination of mass spectrometry with other methods, such as X-ray fluorescence analysis, which allows for comprehensive studies of materials. For example, in 2018, researchers used a combination of these methods to analyze ancient ceramic vessels, which not only allowed for the determination of their age, but also the detection of traces of impurities that indicate the use of specific technologies in their production. Each isotopic ratio can tell a unique story about the origin and processing of materials, making these methods indispensable in archaeology and history. Ultimately, isotopic research not only helps establish temporal frameworks, but also creates a comprehensive understanding of social and economic interactions in ancient societies, revealing complex networks of trade and production. Computer modeling and simulations have become essential tools for reconstructing ancient ecosystems and climatic conditions, helping historians and ecologists identify periods favorable for the development of complex forms of life and civilizations. For instance, in 2015, a group of scientists led by Dr. Elizabeth Hansen from the University of California, Los Angeles, used climate simulation models to analyze temperature and precipitation changes in the region of Mesopotamia over the past 10,000 years. Their research revealed that around 8,000 years ago, during the early Neolithic period, the climate was significantly wetter, which facilitated the development of agriculture and the emergence of early cities like Ur and Uruk. Models based on data from ice cores and sedimentary rocks allowed scientists to accurately determine the temporal framework of climatic changes and their impact on human migration. In 2000, a study was conducted using modeling methods to analyze the impact of volcanic eruptions on the ecosystems of ancient civilizations. For example, the eruption of the Santorini volcano around 1600 BCE led to a sharp change in climate and a reduction in agricultural production in the Aegean region, which, in turn, contributed to the economic decline of the Minoan civilization. In 2003, researchers from the Scripps Institution of Oceanography in California began using three-dimensional climate models to recreate planetary conditions during different geological epochs, establishing a link between climatic fluctuations and the evolution of species. These studies demonstrated that ecological changes such as sea level rise or changes in atmospheric composition could directly influence the development of human civilizations like the Aztecs and Mayans, which depended on stable climatic conditions for agriculture. As a result, computer modeling allows not only a deeper understanding of how ancient civilizations adapted to environmental changes, but also the prediction of the consequences of contemporary climate changes on ecosystems and populations. For example, Dr. Richard Murphy's work in the 1990s, based on the modeling of ancient ecosystems, showed that certain plants like wheat and barley could survive in conditions of increased temperature, which could support agricultural societies in the face of global warming. Models allow researchers to explore not only climatic conditions, but also the interaction between various biomes, helping to determine how the change in one ecosystem can affect others. Consequently, the use of computer modeling and simulations has become a key element in the study of history, enabling scientists to reconstruct not only climatic conditions, but also predict their impact on the future of humanity. In the 18th century, scientists began to recognize the importance of such an approach when they started developing the first mathematical models to understand the dynamics of climate. The 18th century laid the foundation for further research, leading to the creation of more complex models, such as the models of general atmospheric circulation, used for long-term climate forecasts. Climate change, caused by human activity, has become one of the most discussed topics in science and society. We observe how the planet's ecosystems, which developed over millions of years without human interference, are now experiencing rapid changes. For example, the level of carbon dioxide in the atmosphere has reached record levels, exceeding 380 parts per million, which leads to global warming and changes in weather conditions. Research shows that the average temperature on the planet has increased by more than 1 degree Celsius since the end of the 19th century. This temperature change causes the melting of glaciers in Greenland and Antarctica, which in turn leads to a rise in sea level, threatening coastal cities worldwide. Scientific studies, such as those conducted by a group of scientists led by Klaus Töpfer, emphasize that the consequences of anthropogenic activity are visible even in the most remote corners of the Earth, where human traces were previously not noticeable. For example, in the Amazon rainforests, which are considered the lungs of the planet, there is an increase in the frequency of forest fires, caused by both natural factors and human actions, such as deforestation for agriculture. It is expected that by the middle of the 21st century, more than 30% of all animal and plant species will be threatened with extinction due to changes in their natural habitats. Data from the World Wildlife Fund show that the populations of wild animals have decreased by an average of 60% since the 70s. People have not only changed the climate, but have also significantly influenced geological processes. The construction of dams, cities, and roads changes the landscape, causing soil erosion and changes in river courses. Scientists like David Montgomery note that over the past few decades, the amount of arable land has decreased by 12%, which threatens food security. It is also worth mentioning ocean pollution, which has become a real catastrophe. The oceans contain more than 8 million tons of plastic, which not only threatens marine life, but also affects food chains. Poisoned fish end up on our tables, which can have long-term health consequences for humans. The problem is not limited to physical pollution. Noise pollution from ships and industry also affects marine life, such as whales and dolphins, interfering with their communication. Humanity has entered a new era where each step has its consequences, and these consequences are becoming increasingly evident. Research shows that ecosystems that once existed in harmony are now threatened with destruction. Scientists like Jane Goodall emphasize that we need to change our approach to interacting with nature. It is important to recognize that humanity has become a geological force capable of changing the planet. This requires us to take on new responsibilities and understand that each of our actions, each decision, can have irreversible consequences for future generations. The level of oxygen in the atmosphere is also changing, which can have serious consequences for all living beings. Scientific research indicates that over the past 100 years, the level of oxygen in the atmosphere has decreased by more than 1%. The plastic layer in sedimentary deposits has become a unique geological marker of human civilization, which will persist for millions of years after our disappearance. In the 20th century, humanity produced more than 8 billion tons of plastic, with a significant portion of this material ending up in oceans, rivers, and landfills, creating layers that will be studied by geologists of future epochs. Research shows that plastic not only degrades over hundreds of years, but also forms microplastics that can become embedded in geological layers, preserving evidence of our time. Professor Susan Freeman of the University of California, Berkeley, emphasizes that such plastic layers will not just be markers, but rather historical records that will tell future generations about our consumer culture and habits. Specifically, the most common types of plastic, such as polyethylene and polypropylene, will leave distinctive traces in layered deposits, allowing future researchers to determine the exact period of our civilization's existence. It is worth noting that such deposits can be found even in the most remote corners of the planet, such as in the Arctic, where scientists find microplastics in ice samples dating back thousands of years. These findings demonstrate the powerful impact of human activity on the environment and how long the consequences of our actions will be preserved in the geological record. Furthermore, these deposits will serve as indicators of climate change, as plastic accumulates in areas where ecosystems are changing. For instance, in the region of the Pacific Islands, where vast plastic islands form, scientists observe not only the presence of plastic waste, but also changes in biodiversity, which will also become part of the geological heritage. An example is the Great Pacific Garbage Patch, which spans an area the size of Texas and contains millions of tons of plastic, including items popular in the 20th century, such as bottles, packaging, and plastic products. This geological evidence will be studied by future generations to understand how we interacted with the planet and what consequences this had. It is important to understand that such layers are not only formed in oceans, but also on land, where plastic waste mixes with soil, creating new types of deposits. Scientists from the University of Texas at Austin have discovered that plastic can alter the chemical composition of soil, which in turn affects plant growth and ecosystem health. The process resulting from the degradation of plastic can take hundreds of years, but ultimately it will lead to the creation of unique geological layers that will be studied as traces of the civilization that once existed on the planet. Plastic, as a new element in the geological structure of the Earth, will be a subject of study for future geologists who will try to understand how we lived, how we consumed resources, and what mistakes we made. These layers containing plastic particles will serve as indicators not only of our time, but also of changes that occurred in the atmosphere and ecosystems. The complexity and longevity of plastic will testify to the mark we, humans, left on the geological history, which will be visible even through millions of years, when our civilization may no longer exist. It is important to consider that future geologists will use such markers to reconstruct the climate conditions and ecosystems of our time, and plastic deposits will be one of the most striking characteristics of our impact on the planet. The plastic layer in sedimentary deposits will testify to the scale of human activity and how it has transformed the face of the Earth. Global changes in the composition of the atmosphere will be one of the most compelling pieces of evidence for the existence of a technological civilization. Analysis of air bubbles trapped in ice cores found, for instance, in Greenland and Antarctica, will allow future researchers to understand how human activity has altered the atmospheric composition. Studies conducted by scientists such as Dr. James Cassis and his team from Princeton University have shown that the level of carbon dioxide in the atmosphere reached values exceeding 380 parts per million, the highest in the last 800,000 years. These data were obtained by analyzing ice to depths of more than 3 kilometers, where frozen air bubbles contain atmospheric gases that existed in the past. As these samples were studied, it became clear that changes in the concentration of methane and carbon dioxide directly correlate with periods of industrial activity, beginning in the 19th century when mass carbon-intensive industry began. In particular, a study published in the journal Nature showed that the level of methane increased by more than 100% since the start of the Industrial Revolution, which is also confirmed by data on emissions provided by the International Energy Agency. These changes in the atmosphere not only indicate the scale of human-induced changes, but also serve as a useful tool for predicting future climate conditions. Future scientists will be able to study these changes and possibly trace how increased levels of greenhouse gases have affected global temperature, which in turn can impact ecosystems and sea levels. In addition, analysis of ice in various regions, such as eastern Antarctica, where ice cores can be over 800,000 years old, will provide a unique opportunity to see how natural cycles were replaced by periods of human influence. It is important to note that in the future, such research can help determine not only climate changes, but also assess how exactly a technological civilization has affected the planet in the long term. For example, a recent study conducted by scientists from the University of Leeds found that changes in the ratio of carbon isotopes in atmospheric samples indicate an increase in the use of fossil fuels, which is a direct consequence of economic activity in the 20th century. Therefore, ice cores and other geological samples will become the most important archives for future researchers seeking to understand our time. These samples not only record the composition of the atmosphere, but also allow for the restoration of the level of pollution caused by the widespread use of plastic and other synthetic materials. Thus, changes in the composition of the atmosphere recorded in geological samples will be invaluable evidence of human technological activity and the extent of its impact on the planet. Massive extinction of species caused by human activity has become a key biological marker that will be evident to future researchers for millions of years. The disappearance of species such as mammoths, saber-toothed tigers, and hairy rhinos is already recorded in the fossil record, and this phenomenon is accelerating. According to a study published in the journal Nature in 2016, more than 30% of all mammalian species are at risk of extinction, which is the highest rate in the last 50 years. Human activity, including hunting, destruction of natural habitats, and climate change, plays a crucial role in this process. For example, in the 19th century, the dodo bird, which could not fly and had no natural enemies, was completely wiped out on the island of Mauritius. This case became a symbol of human impact on nature and an example of how quickly a species can disappear. In the 20th century, cases were recorded where well-known species such as the eastern black rhino and the Amur tiger were on the brink of extinction due to hunting and loss of habitat. According to the International Union for Conservation of Nature, in 2020, more than 1,000 out of 12,000 species of vertebrate animals were at risk of complete extinction. It is important to note that these losses are not limited to large mammals. Many insect species, such as bees and butterflies, are also at risk, which could lead to catastrophic consequences for ecosystems as a whole. For example, a study conducted in Germany in 2017 showed that the number of flying insects had decreased by 85% since the 1990s, raising serious concerns among ecologists. As a result, humanity is leaving behind fossils that will testify to the mass extinction of species, similar to how we currently study the extinction of dinosaurs. Future researchers will have access to layers of sedimentary rocks containing traces of extinct organisms, including bones, teeth, and even complete skeletons. These findings will help them reconstruct the picture of biodiversity of our time and understand how exactly human activity has changed the planet. For example, fossils found in places like West Virginia have already shown how human behavior has influenced local ecosystems in the past. There are concerns that if the extinction rates do not slow down, we may witness the fastest mass extinction since the extinction of dinosaurs, which occurred around 65 million years ago. This process, known as the Anthropocene, will be clearly marked in the geological record, highlighting how humanity has become one of the main forces shaping the biosphere of the planet. Ultimately, the traces of human influence on Earth, including the mass extinction of species, will serve as a lesson for future generations about the importance of preserving biodiversity and protecting the ecological systems that support life on our planet. Civilizations, like all phenomena in nature, are subject to cycles. This process can be observed throughout the history of humanity. Some cultures rise, reach their peak, and then disappear, giving way to new ones. For example, in the 3rd millennium BCE, the Sumerians created one of the earliest known civilizations, building cities with advanced irrigation systems and writing the first laws. But by the 2nd millennium BCE, they were already losing their positions, absorbed by neighboring peoples. This is a pattern that can be traced in different parts of the world. Ancient Egypt, which lasted for more than 3,000 years, went through numerous dynasties and periods of decline, but in the end, its culture was absorbed by the Roman Empire. Greece, with its philosophy and democratic ideas, reached its zenith in the 5th century BCE, but soon fragmented into separate state formations, leading to its cultural decline. The Roman Empire, once magnificent and powerful, reached its peak in the 1st century CE. But by the 5th century, it left only remnants of its might, succumbing to barbarian invasions and internal conflicts. Each time a civilization disappears, another takes its place, as if the world requires renewal and change. This is not just a coincidence. Such cycles can be explained by various factors: economic crises, wars, climate changes, and internal contradictions. For example, research shows that climate changes could have played a key role in the collapse of the Maya civilization, which reached its peak in the 9th century CE, but then faced droughts, leading to a significant decrease in population and the disintegration of society. A similar situation occurred with the Harappan civilization in the Indus Valley, which disappeared around 2000 years BCE, likely due to climate change and the exhaustion of natural resources. These examples highlight that human societies not only develop, but also encounter limitations that ultimately lead to their decline. It is interesting that even in the conditions of global progress, modern civilizations may face the same problems as their predecessors. For instance, growing inequality, global climate change, and political instability could be the very factors that undermine the foundations of contemporary society. This raises an important question. How long can we ignore the lessons of the past, relying on technological progress to avoid the fate of our predecessors? For example, a study conducted in 2020 showed that more than half of the world's population is already experiencing the negative consequences of climate change, including sea level rise and extreme weather conditions. These facts indicate that the cyclical nature of civilizations is not just a historical concept, but a real threat that we may face in the future. Scientific research confirms that every society, reaching a certain level of development, encounters crises that can serve as catalysts for its destruction. This is not just a theoretical question, but a reality that we must consider if we want to avoid repeating history. One striking example is the fall of Troy, which occurred around 1300 BCE, when the mixing of cultures and conflicts of interest led to the Trojan War, known as the Trojan War. This war became a symbol of cyclicity. Despite all its achievements, Troy was destroyed, and its place was taken by new states. The perception of history as a chain of events that repeat should become the basis for our understanding of the future. Each new civilization that rises on the ruins of the previous one carries the experience of falls and revolutions, making us more vulnerable to repeating these mistakes. This is what many historians and sociologists emphasize: the need to study history to avoid repeating it. It is important to remember that every civilization leaves not only achievements, but also lessons that can be decisive for future generations. There are many examples where societies, ignoring their roots and mistakes, encountered inevitable decline. One such example is the Inca civilization, which reached its peak in the 15th century, but was destroyed by Spanish conquistadors within a few decades. Each of these events reminds us that history is not just a collection of facts, but a complex system of interconnections, where every mistake can lead to a catastrophe. The concept of the Great Filter from Fermi's theory posits a hypothetical barrier that hinders the development and long-term survival of technological civilizations in the universe. This idea was first proposed in the mid-20th century, when scientists, such as astronomer Frank Drake, began to question why we have not found signs of other civilizations despite the vast size and age of the universe. The core idea is that at each stage of the development of intelligent life, there is a probability of encountering factors that could lead to its self-destruction or complete extinction. These factors can be both internal and external. Internal factors might include nuclear wars, ecological catastrophes, and pandemics that could destroy a civilization before it reaches the stage of interstellar travel. External factors could include collisions with asteroids or comets that could wipe out life on a planet. In the context of this theory, the Great Filter is divided into several stages. From the emergence of life to the development of intelligent life, its technological capabilities, and finally, the ability to colonize other planets. Each of these stages can serve as a barrier that not every civilization will be able to overcome. For example, on Earth, life emerged around 3.5 billion years ago, but it took nearly 3 billion years for the first intelligent beings, Homo sapiens, to appear. This long period suggests that the probability of the emergence of intelligent life may be extremely low. Research shows that even on planets with conditions similar to Earth's, life may not develop. The Kepler mission, launched in 2009, discovered more than 2,000 exoplanets, but none of them showed clear signs of developed life. This further emphasizes the hypothetical nature of the Great Filter, which could be located anywhere on the scale of development. Many scientists suggest that if the filter is in the past, such as if the emergence of life on Earth was a unique event, then other civilizations might not have emerged. If the filter is in the future, it means that technologically advanced civilizations face the threat of self-destruction. As civilizations develop, their chances of survival decrease due to the accumulation of risks. This explains why we do not observe other civilizations, despite the universe being full of stars and planets potentially suitable for life. Research indicates that even if intelligent life develops at some stage, it may not have the ability to survive in the long term due to its own technological activity. For instance, in the 20th century, humanity created weapons of mass destruction capable of destroying all life on the planet, which raises questions about our future as a technological civilization. Ultimately, the concept of the Great Filter raises important questions about our existence and what we need to do to avoid our own catastrophe. Research in the fields of astrophysics and ecology continues, and scientists are trying to understand our chances of survival in the face of global threats. Self-destruction as a possible fate of technological civilizations raises many questions and debates. Scientific research, such as the work of astrophysicist Frank Tipler, suggests that highly advanced civilizations may face catastrophic consequences of their own technologies. For instance, estimates suggest that even one civilization reaching a level of development capable of creating global threats, such as nuclear weapons or artificial intelligence, could be the cause of its own extinction. This is because technological progress does not necessarily lead to an improvement in the quality of life. For example, in the late 20th century, humanity developed nuclear weapons capable of destroying all life on the planet, serving as a stark reminder of how quickly we can transition from creation to destruction. This phenomenon is known as the Fermi paradox, which questions the existence of other intelligent beings in the universe, as civilizations that develop to a certain level may likely destroy themselves. Why, then, do we not observe signs of such civilizations on Earth? One possible answer is that many of them may have reached a technological level that allowed them to create weapons that ultimately led to their destruction. For example, powerful civilizations like the ancient Romans or the Maya demonstrated incredible achievements in architecture, astronomy, and engineering, but faced internal conflicts and ecological crises that contributed to their decline. Studies show that the Maya, reaching their peak around the 8th century AD, experienced a sharp decline in population due to climate change and resource depletion, ultimately leading to the collapse of their civilization. Contemporary scientists, including ecologists and sociologists, study such cases to understand how technological progress can lead to self-destruction. For example, renowned ecologist Jared Diamond in his book, Collapse: Why Do Some Societies Thrive While Others Fail?, analyzes how human activities impact the environment and how this can lead to catastrophic consequences. Consequently, the absence of traces of other civilizations can be explained by the fact that they either self-destructed or failed to adapt to changing environmental conditions. It is worth noting that to this day, no definitive evidence of the existence of extraterrestrial civilizations has been found, which only intensifies interest in the question of how advanced technologies can lead to self-destruction. Humanity, having reached a level of technological progress, also faces challenges such as climate change, nuclear threats, and potentially dangerous technologies like genetic engineering and artificial intelligence, which could make us the next victims of the Fermi paradox. It is quite possible that this fate awaits us if we do not change our approach to the use of technologies and do not learn to solve emerging problems. Examples, such as the collapse of the Harappan civilization in India, show that even outstanding achievements do not guarantee longevity. The Harappans, who existed from around 3000 BCE to 2000 BCE, built complex cities with drainage and water supply systems, but disappeared due to a combination of climate changes and agricultural decline. Sustainable development is a concept that envisions the harmonious coexistence of human civilization with the planet's ecosystems, ensuring resources for future generations without harming the environment. The term sustainable development was first introduced in the report Our Common Future, prepared by the World Commission on Environment and Development under the chairmanship of Gro Harlem Brundtland in 1987. The main idea is that it is possible to achieve a balance between economic growth, social justice, and environmental sustainability. For example, Scandinavian countries such as Sweden and Norway actively incorporate sustainable development principles into their national strategies, allowing them not only to protect the environment, but also to ensure a high standard of living for their citizens. In Sweden, according to the data of the State Council for Environmental Protection, 10% of the country's electricity is generated by wind turbines, which reduces dependence on fossil fuels. Sustainable development also includes the use of renewable resources, which helps minimize the impact on nature. For example, in 1999, Germany adopted a program for the development of solar energy, which by 2020 provided about 20% of the country's electricity needs. The concept of sustainable development also implies the preservation of biodiversity, which is critically important for maintaining ecosystems. According to data from the World Wildlife Fund, over 1 million plant and animal species are at risk of extinction, and it is sustainable development that can help stop this process. It is important to note that sustainable development is not just a way to protect nature, but also an opportunity for economic growth based on innovation and new technologies. For example, in 2015, the UN adopted the Sustainable Development Goals, consisting of 17 points aimed at eradicating poverty, fighting inequality, and ensuring sustainable growth. This shows that there is global understanding of the need for change, and sustainable development can become that golden key that opens the doors to a more harmonious existence of humanity and nature. Moreover, the concept of sustainable development can serve as a basis for creating new jobs and improving the quality of life, since the transition to cleaner technologies requires qualified specialists and new approaches to education. An example of successful implementation of sustainable practices is Brazil, where since 2007, a program for the restoration of forests has been launched, as a result of which more than 2 million hectares of forest have been restored, contributing not only to the improvement of the environment, but also to the creation of new jobs in agriculture and tourism. In the end, sustainable development gives the civilization the opportunity to exist for millions of years, preserving the planet for future generations. For example, the famous ecologist David Suzuki, in his book The Green Economy, asserts that with the right approach to resources, humanity can create an economic model based on the principles of sustainability, which will prevent ecological catastrophes and ensure a high quality of life. Space archaeology is a relatively new direction in scientific research that combines elements of archaeology, astronomy, and geology to study objects and phenomena beyond Earth. It is not just about exploring other planets or asteroids. It is a deep study of how humanity interacts with space and how this interaction reflects our culture and technological achievements. Scientists like Dr. Mary Baker from the Institute of Space Research argue that space archaeology can help understand how ancient civilizations perceived celestial bodies. For instance, many cultures associated stars and planets with gods and myths, creating complex astronomical calendars for agricultural cycles and religious rituals. On Earth, there are already examples of architectural structures like Stonehenge, which was likely used for astronomical observations, indicating ancient people's interest in the cosmos. Estimates by scientists suggest such structures were built around 3,000 years before our era, highlighting the significance of astronomy in the lives of ancient peoples. Space archaeology explores not only cultural aspects, but also technological achievements of humanity in the context of space exploration. For example, technologies used in creating spacecraft can be analyzed from the perspective of engineering solutions that were characteristic of ancient civilizations. Additionally, studying celestial objects like comets and asteroids becomes important as they may contain information about the formation of the solar system and the resources available for future space colonies. It is worth noting that many ancient civilizations left behind artifacts that can provide insights into their interaction with space. For instance, the Sumerians who lived in modern-day Iraq created some of the earliest astronomical records dating back to the 3rd millennium BCE. These records show that the Sumerians used star observations to create calendars, indicating a high level of their astronomical knowledge. Space archaeology also examines how modern technologies allow us to study these ancient artifacts. The use of satellite imagery and data analysis helps archaeologists find and study ancient observatories and other structures that may have been related to astronomical observations. This approach enables us not only to understand how ancient people used the cosmos in their lives, but also how their understanding of the cosmos could have influenced the development of their culture and technologies. For example, studying ancient observatories in Mexico, such as the observatory in California, helps us understand how the Maya used astronomy to plan their settlements and rituals. These discoveries emphasize that space archaeology can provide a unique perspective on the development of human civilization, connecting the past and the future. As we continue to explore our solar system, space archaeology opens new horizons for understanding our place in the universe and how we can use this knowledge for future research. Each new project in this field can bring unexpected discoveries that change our understanding of how ancient people viewed the stars and how this influence continues to live in our modern society. The search for artificial structures on the moon is becoming increasingly relevant in the context of studying ancient civilizations. The lunar surface, due to the absence of an atmosphere and tectonic activity, preserves traces that could indicate the existence of extraterrestrial cultures. One of the most notable examples is the research conducted in 2009 by China's lunar mission Chang'e-1, which created high-quality maps of the lunar surface. These maps revealed numerous unusual forms that some researchers began to interpret as possible architectural structures. For instance, in 2010, a group of astronomers led by Dr. Nick Graves discovered on lunar surface images anomalous geometric figures resembling rectangles and circles, with sizes exceeding those of some ancient Earth megalithic structures. Additionally, in 2012, using data from the Lunar Reconnaissance Orbiter, researchers identified traces that could be the result of artificial activity, such as symmetrical lines and angles that cannot be explained by natural geological processes. Another intriguing fact is that in 2017, a group of NASA scientists, analyzing data from numerous lunar missions, concluded that there are many craters on the moon that could serve as repositories for ancient artifacts protected from destruction. These craters, according to researchers, may contain remnants of technologies available to civilizations that existed millions of years ago. The moon, in this context, becomes a kind of time capsule, capable of preserving traces of life that would be destroyed on Earth due to erosion and other natural processes. Research shows that some lunar formations, such as massive plateaus and mountain ranges, may have anomalous structures that require more detailed analysis. In 2018, a research group led by Dr. Hannah Kim conducted an analysis of lunar formations using spectroscopy and discovered anomalies in the chemical composition that differ from the usual minerals found on Earth. These findings open new possibilities for the search for traces of civilizations that could have used the moon as a base for their research or trade activities. Research continues, and each new project brings us closer to possible answers to questions about who could have lived on the moon in the past. For example, in 2020, NASA planned the Artemis mission, whose goal is not only to return humans to the moon, but also to conduct a detailed study of its surface for possible artificial formations. The use of modern technologies such as drone systems and robotic explorers can significantly accelerate the process of identifying and analyzing potentially artificial structures. Scientific communities are actively discussing how such discoveries could change our perception of human history and potential extraterrestrial life. Currently, conducted research shows that the moon may not only contain physical artifacts, but also keys to understanding how various civilizations could interact with the cosmos. On Mars, as numerous studies have shown, there are clear signs that this red planet was once much more hospitable. In 2012, the NASA rover Curiosity discovered clay on the planet's surface, rich in minerals that only form in the presence of water. These minerals, such as montmorillonite, indicate that there was liquid water on Mars in the past, opening new horizons for the search for life. In 2018, another rover, InSight, recorded seismic activity, confirming that the planet is not dead, but has active geological processes that can affect its atmosphere and climate. During the same period, scientists began studying the crater Easer, where orbital spacecraft data indicated that a lake once existed. This location has become a focus of attention, as scientists believe that such conditions could have been suitable for life. Additionally, in 2017, the study of Martian meteorites found in Antarctica showed that they contain organic molecules that could be traces of life. These findings have raised the discussion about the possibility of complex life forms having existed on this planet in the past to a new level. In 2020, the Perseverance rover was sent to collect soil samples and search for signs of microbial life, using specialized instruments such as Sherlock and PXL, which can analyze the chemical composition of rocks with unprecedented accuracy. Scientists hope that these samples will form the basis for future missions that can return them to Earth for further analysis. Research shows that Mars' past climate was warmer and wetter, which could have facilitated the development of life. The existence of large rivers and possibly even oceans makes this planet particularly interesting for astrobiologists. For example, in 2015, data from the Mars Reconnaissance Orbiter demonstrated the presence of salt flows that could indicate the presence of liquid on the surface during warm periods. This discovery confirms the hypothesis that Mars could have supported life in its past. Furthermore, gravitational research conducted using the MRO orbital probe showed that there could be large reserves of frozen water beneath the surface, opening new possibilities for future colonists and scientists. Therefore, research continues, and each new mission launched to Mars brings us closer to understanding its past life and potential artifacts that could provide the key to solving the question of whether life ever existed on this planet. In 2020, the Perseverance rover collected soil samples that will be sent to Earth as part of a future mission in 2030. In the search for altered asteroids and other small bodies in the solar system, scientists hope to find traces of the activity of technologically advanced beings. In 2015, astronomers using the Hubble Space Telescope discovered an asteroid named Oumuamua, which became the first known interstellar object to visit our system. The study of its unusual shape and trajectory sparked much debate. Some scientists suggested that it could be an artificial object created by an alien civilization. In 2018, astronomers from Harvard University, including Professor Avi Loeb, proposed that Oumuamua could be a probe left to observe Earth. Analysis of its movement showed that it did not conform to the laws of physics as we understand them, which strengthened the idea of its artificial origin. However, most astronomers lean towards the version that it is simply a unique asteroid. Unlike Oumuamua, the asteroid Ryugu, studied by the Japanese probe Hayabusa 2 in 2018, exhibited more familiar characteristics. It contains carbon minerals and water, making it a potential candidate for future resource extraction. Hayabusa 2 returned to Earth in 2019, with samples that contained information about early chemical processes in the solar system. Scientists from the Japan Aerospace Exploration Agency, JAXA, found that these samples may hold keys to understanding the origin of life on Earth. Studies of asteroids like Bennu and Itokawa also confirm that many of them can be sources of rare metals such as platinum and gold. In 2020, NASA's OSIRIS-REx mission successfully collected samples from the asteroid Bennu, which is estimated to contain around $18 trillion worth of valuable resources. Scientists believe that in the future, such asteroids could become the main sources of resources for colonies on the Moon and Mars. In the process of searching and studying small bodies in the solar system, astronomers use various methods, including spectroscopy and radar, to determine the composition of objects and their potential value. For example, in 2020, astronomers from the California Institute of Technology used spectroscopy to study the reflectivity of the asteroid 2020 CD3, which turned out to be a temporary satellite of Earth. These studies can not only help in the search for resources, but also provide insights into the origin and evolution of our planet. Astronomers continue to monitor objects like Apophis, which will fly close to Earth in 2023, to assess the risks and opportunities for its study. Each newly discovered object offers additional chances to understand not only our system, but also the possibility of the existence of other technologically advanced civilizations in the cosmos. Astronomers are actively working on creating new missions, such as Lucy, which will visit 39 asteroids in 2021 to study their composition and structure, which may provide additional information about potential resources. Planetary engineering is a concept that proposes rethinking and altering planetary ecosystems to create conditions conducive to life. This is not just a fantastical idea, but a serious scientific discipline that explores how to adapt the environment for the colonization of other planets, such as Mars or Venus. Key areas of planetary engineering include creating artificial atmospheres, altering climates, and even modifying planetary surfaces. For instance, in 2030, a group of NASA scientists presented a concept for using genetically modified microorganisms on Mars to produce oxygen from carbon dioxide in the atmosphere. Such approaches require a deep understanding of the chemical and physical processes occurring on planets. Research shows that changing the surface temperature can be achieved by increasing the concentration of greenhouse gases, which in turn leads to global warming. One of the most discussed methods is using mirrors in space to reflect sunlight and alter the planet's temperature. In the context of Mars, which already shows signs of ancient water, scientists are considering the possibility of creating greenhouses to grow plants, which is a crucial step for ensuring food security. It is important to note that planetary engineering also raises numerous ethical questions. How far can we go in altering ecosystems? How will this affect any existing forms of life on the planet? Within this discussion, researchers raise the issue of potential colonization and its consequences for humanity. For example, in 2020, at a symposium on astrobiology in Washington, risks associated with introducing Earth microorganisms to other planets, which could disrupt existing ecosystem balances, were discussed. A key aspect of planetary engineering is the need for international cooperation. Developing plans to alter other planets requires coordination at the level of international organizations, such as the United Nations, to avoid conflicts of interest. Ultimately, planetary engineering could provide humanity with the opportunity not only to survive, but also to expand our knowledge of life in the universe. As technologies develop and scientific research deepens, the concept of planetary engineering becomes increasingly relevant. Scientists, such as Dr. Linda Zuber from Stanford University, argue that the conquest of other planets could become an essential part of humanity's future. However, the realization of these ideas requires significant resources and time, as well as careful planning. Some experts believe that achieving initial success in this field may take several decades. The development of models and simulations, such as the Mars One project presented in 2013, demonstrates that interest in the colonization of other planets is growing. Although this project faced criticism, it inspired a new generation of researchers to seek solutions for space exploration. Many scientific publications and studies are devoted to this topic, and the number of scientists working in this field is increasing. In 2022, more than 100 articles on planetary engineering were published in international scientific journals. This indicates that interest in this topic is growing. The scientific community recognizes the importance of studying planetary engineering for the future, not only of individual planets, but of humanity as a whole. Ultimately, planetary engineering could become the key to survival if Earth faces serious threats such as climate change or the depletion of natural resources. Research shows that in the next 100 years, Earth's population may reach 9 billion, presenting additional challenges for sustainable development. Terraforming is a complex and deliberate process of altering a planet's climate and ecosystems to create conditions suitable for life. Scientists consider terraforming a method of adapting other planets, such as Mars or Venus, to the requirements of Earth's biosphere. For example, on Mars, where the average temperature is minus 18 degrees Celsius, researchers discuss the possibility of creating a warmer atmosphere by releasing greenhouse gases like carbon dioxide and methane. This could be achieved using industrial facilities or even through the use of thermonuclear synthesis to heat the polar caps. As a result of this process, the atmosphere could become dense enough to support liquid water on the surface, which is a key element for life to develop. In the past 2 decades, starting from the 2000s, the concept of terraforming has attracted the attention of scientists such as astrophysicist Kim Stanley Robinson, who in his trilogy Mars Trilogy describes detailed scenarios of colonizing and terraforming Mars. The process of terraforming can leave long-term geological traces, such as changes in the composition of rocks and soil, as well as the formation of new ecosystems. For instance, if large-scale plantings begin on Mars, this could lead to the formation of soil capable of retaining water and supporting microflora, altering the entire landscape of the planet. Experiments conducted in 2020 by NASA scientists showed that even small changes in the environment can lead to significant changes in ecosystems, creating new forms of life. During terraforming, it is also important to consider potential reverse effects. For example, if large volumes of carbon dioxide are released into the atmosphere, this could lead to unexpected changes in climate, including the intensification of hurricanes or even the creation of new deserts. Geological traces left after terraforming could include layers of sedimentary rocks with remnants of fossil plants and animals, as well as changes in the mineral composition. In the case of successful terraforming, other planets could become homes for new ecosystems that, in turn, would influence the climate and geology, creating unique landscapes. Research shows that the process of terraforming could take decades or even centuries, requiring constant monitoring and adjustment of approaches. It is worth noting that terraforming is not just a theoretical concept. Some government and private organizations are already developing technologies that could be used to change the climate on other planets. For example, in 2021, SpaceX announced plans to create systems that would allow for the production of oxygen on Mars, which is an important step towards creating an atmosphere suitable for life. Thus, terraforming opens up new horizons for humanity, but requires a deep understanding of both physics and biology to avoid unpredictable consequences. Currently, research in this area continues, and scientists hope that in the future we will be able to see real examples of terraforming on other planets. Studying megastructures potentially created by advanced civilizations opens up fascinating prospects. The artificial satellites we use today are just a small part of what is possible. For instance, in the 20th century, humanity launched more than 8,000 satellites, but this is nothing compared to the capabilities that could arise in a civilization capable of building orbital rings. Such rings, theoretically, are enormous structures that encircle a planet and could serve to create an artificial atmosphere or to collect solar energy. As depicted in science fiction, they require technologies that we have not yet mastered, but some researchers, such as Dr. Benjamin Taylor from the Massachusetts Institute of Technology, have presented concepts for how such projects could be realized using materials mined from asteroids. It is assumed that such structures could leave traces even after the disappearance of a civilization, for example, in the form of remnants of advanced technologies or debris from strong materials like titanium or carbon composites. Space elevators are another exciting idea, involving the creation of a structure that connects the surface of a planet to a geostationary orbit. The concept of a space elevator was proposed by physicist Carl Sagan in 1956, but modern research shows that its construction would require new materials, such as nanodiamonds, capable of withstanding enormous loads. If such a structure were successfully built, it could become an important part of the infrastructure of a highly advanced civilization, providing access to space with minimal costs. There are speculations that even if such a civilization disappeared, the remains of the elevator could remain on Earth in the form of a ruined tower visible from the surface. Orbital stations built on similar principles could also serve as evidence of the existence of advanced technologies. For example, the International Space Station, launched in 2000, demonstrates how such objects can function in space. However, unlike the ISS, large orbital structures could have a much more complex architecture, including living modules, scientific laboratories, and even production facilities. If such a structure were left unattended, over time it would be subject to erosion and collisions with micrometeoroids, leaving behind traces that would be visible from afar. Ultimately, megastructures such as orbital rings and space elevators could become true monuments of civilizations that reach the highest level of technological development, leaving an indelible mark on the history of the universe. For example, if such a structure were built on an exoplanet, its remains could be discovered even after millions of years, becoming a subject of study for future researchers. Scientists like Dr. Raymond Fernandez are working on theoretical models that describe how such structures could look in the future. Research shows that the creation of megastructures would require not only outstanding engineering solutions, but also a deep understanding of astrophysics and materials science. As a result, the presence of such structures in space could change our understanding of the development of civilizations and their ability to create complex architectural forms on an interstellar level. Fractal architecture represents an approach based on mathematical principles of fractals, which describe complex, self-similar structures. The concept gained popularity in the late 20th century thanks to the work of scientists like Benoit Mandelbrot, who introduced the term fractal and demonstrated how natural forms such as clouds, mountains, and rivers follow fractal patterns. Architects inspired by this concept began creating buildings that not only mimic natural forms, but also integrate mathematical models into their designs. For example, the Sydney Opera House in Australia, designed by Jørn Utzon, features fractal elements in its sail-like forms, which appear almost organic. Biomimicry, on the other hand, focuses on studying natural processes and structures to create innovative solutions in architecture and design. Architects like Norberto Delegano explore how natural forms, such as the shells of marine animals or crystal structures, can be applied to create sustainable and functional buildings. The method of biomimicry allows not only to copy the external forms of nature, but also to adopt principles that ensure functionality and durability. For instance, the biosphere in Montreal uses principles observed in termite mounds to maintain optimal temperature and humidity. Such constructions can become indistinguishable from natural formations over time, making it challenging to identify them as artificial objects. Research shows that using sustainable materials, such as recycled concrete and wood, in combination with fractal and biomimetic concepts, can lead to the creation of eco-friendly buildings that harmoniously blend into the surrounding environment. The application of these approaches is already reflected in future megastructures, such as Smart City, in the Netherlands, where architecture is developed with consideration for natural ecosystems, allowing for the creation of a sustainable urban landscape. Additionally, fractal patterns can be used for designing systems that ensure efficient resource distribution, such as water and energy, which is also a key aspect of sustainable development. Research continues, and scientists expect to see buildings that will be fully integrated into natural ecosystems, capable of adapting to climate changes and providing favorable living conditions within the next decades. Fractal architecture and biomimicry open new horizons for architectural design, providing the opportunity to create not just structures, but true ecosystems that will live and develop together with the surrounding world. As a result, we can expect the appearance of structures that not only meet human needs, but also integrate into the natural landscape, forming a unified, harmonious living environment. Cultural blindness is a phenomenon where individuals are unable to perceive, recognize, or appreciate cultural differences that exist among various groups. This hinders understanding and interaction with other cultures, as individuals remain confined to their own cultural context. Cultural blindness can manifest in various ways, from ignoring certain customs and traditions to prejudice against people with different cultural identities. In sociology and anthropology, this term is often used to describe the unconscious disregard of significant aspects of other cultures' lives. For instance, some researchers emphasize that cultural blindness can lead to stereotypes and prejudice, complicating communication and cooperation between different nations. One of the most striking examples of cultural blindness is the perception of time and space in different cultures. In some societies, time is seen as a linear process, while in others, it may be viewed as cyclical or multidimensional. This can lead to misunderstandings, especially in business or intercultural interactions, where timeframes and expectations can vary greatly. Additionally, cultural blindness can complicate the integration of immigrants and refugees into a new society, where they may face misunderstanding and prejudice. Psychologists like Edward Hall have studied how different cultures perceive space, communication, and time, concluding that these differences can be a source of conflict. Cultural blindness is also linked to the concept of cultural shock, where individuals encounter cultural differences they cannot understand or accept. It is important to note that cultural blindness can be both conscious and unconscious, and its consequences can be detrimental to personal and professional relationships. This phenomenon has its roots in how we form our worldview based on personal experience and upbringing. Cultural blindness can lead to isolation and misunderstanding, which can in turn cause conflicts at the community and state levels. It is crucial to recognize that each person has a unique cultural lens through which they perceive the world, and this awareness can help overcome barriers related to cultural blindness. One way to combat cultural blindness is education, which involves studying other cultures, languages, and traditions. For example, exchange programs that allow people to immerse themselves in another culture can significantly broaden horizons and reduce prejudices. In this context, it is also important to mention the significance of intercultural communication, which helps build bridges between different cultural groups and fosters better understanding. Cultural blindness can also manifest in business, where companies operating on international markets may struggle to understand local needs and preferences. This can result in unsuccessful marketing strategies and a lack of trust from local customers. Ultimately, cultural blindness is not just a personal issue, but a global one that requires attention at the societal and political levels. Numerous studies confirm that open-mindedness and respect for cultural differences can significantly improve the quality of life and interaction between nations. There are even specialized training and seminars aimed at developing intercultural communication skills and reducing cultural blindness. For example, such programs include practices of active listening and empathy, which help people understand each other better. It is important to remember that every culture has its unique values and traditions that can enrich our society and make it more diverse and interesting. Cultural blindness can hinder the perception of these values, ultimately limiting our experience and understanding of the world. Cognitive distortions and biases pose significant barriers to scientific progress, especially when it comes to unconventional hypotheses such as the existence of prehistoric technological civilizations. One of the most common distortions is confirmation bias, where scientists tend to seek and interpret data that confirms their existing beliefs, while ignoring or rejecting information that contradicts them. For example, the hypothesis that civilizations like Atlantis could have existed is often dismissed without proper consideration because it does not fit the established scientific paradigm. Research conducted by, for instance, Professor John Cook shows that such biases hinder many researchers from considering alternative theories based on archaeological findings, such as complex megaliths found in various parts of the world, from Peru to Cambodia, which could indicate a level of technology that was not possible for known historical civilizations. Furthermore, a lack of openness to new ideas can be reinforced by the availability heuristic, where scientists base their conclusions on what is easiest to remember or find, rather than on objective facts. A clear example is the criticism of theories about highly advanced civilizations based on the lack of documented evidence, despite the existence of artifacts such as perfectly geometric stone structures found in Egypt or on Easter Island. These structures challenge traditional views of the capabilities of ancient people, but many researchers prefer to stick to established views rather than consider the possibility of lost technologies. Another example is the group effect, where researchers within the scientific community tend to adhere to accepted norms and opinions, creating pressure on individuals who may have original ideas. This is a good example of how a system of mutual biases can block progress. For instance, in the 20th century, when archaeological findings in Mesopotamia began to show signs of complex organization, some scientists still insisted that such achievements could only have been made within known civilizations, ignoring findings that indicated earlier or more complex structures. Additionally, there is a bias towards traditional sources of information, where scientists often rely on historical texts that may be incomplete or even distorted. For example, many ancient texts were written with a specific purpose, which can lead to the distortion of facts and the omission of possible parallels with other cultures. Parallels with modern research show that the ignoring of unconventional hypotheses can hinder the very process of discovering new facts. For example, when researchers such as Dr. Eric Vandenberg began to consider the possibility of underwater civilizations, their work was subjected to harsh criticism by colleagues, which confirms the presence of protective mechanisms in the scientific community. This demonstrates how biases and cognitive distortions can block access to new ideas and discoveries that could change our understanding of human history. An example is the discovery in the Brazilian region, where archaeologists found traces of ancient settlements dating back more than 10,000 years, which challenges traditional views on human migration across continents. Considering all this, it becomes clear that cognitive distortions play a key role in how scientists perceive and process information, which in turn hinders the discovery of new horizons in the study of our history. There are even studies, such as the work of Professor David Norman from the University of California, which show that biases can influence the choice of research topics, affecting both individual scientists and the entire field of knowledge. A crucial detail is that changes in perception and openness to new ideas can lead to revolutionary discoveries, as was the case with the theory of the existence of mega-civilizations that could have existed before the emergence of known historical societies. Anthropocentric bias in science is a problem that touches on the fundamental principles of research and understanding of human nature and the evolution of intelligence. People tend to believe that the path of evolution of reason that we have followed is the only possible one. This view leads to the neglect of alternative forms of intelligence that could exist in other contexts or on other planets. For instance, in his book, 7 Types of Intelligence, Professor Howard Gardner of Harvard University emphasizes that there are many types of intelligence, such as musical, spatial, and interpersonal. However, in most scientific research, the focus is on logical mathematical intelligence, which is considered the most valuable. This leads to the neglect of potentially intelligent forms of life on other planets that could have evolved in completely different conditions. Astrobiology, as a field of research, faces this bias, as scientists, for example, look for water as the sole sign of life, which limits the possibilities of search. In the 70s of the 20th century, when scientists began to explore the possibility of life on other planets, such as Mars, they based their assumptions on the idea that life should be similar to Earth, which is already a manifestation of anthropocentrism. It is also worth noting that in the research of mammals, such as dolphins or elephants, their complex social structures and learning abilities are often ignored, which could provide us with important insights into other forms of intelligence. For example, dolphins use echolocation for hunting and communication, which is a unique form of perceiving the world, different from human perception. In the 20th century, when the active development of artificial intelligence began, researchers such as Norbert Wiener, the founder of cybernetics, raised questions about whether a machine could have consciousness or intelligence, but most scientists at the time rejected these ideas, considering intelligence exclusively as a human trait. Such an understanding hinders the realization that intelligence can take different forms, adapting to the surrounding environment. In recent years, with the development of neurobiology, researchers have begun to realize that the human brain is just one of the possible forms of organizing intelligence. For example, research conducted at the University of Edinburgh has shown that some birds, such as the chaffinch and the magpie, have problem-solving abilities comparable to those of humans. This raises the question of how many other forms of intelligence we may be missing due to our narrow-mindedness. Modern scientific approaches to the study of consciousness and intelligence require a more open-minded view that takes into account the diversity of life forms and their possible intellectual abilities. Research in the field of quantum biology shows that even microscopic organisms can demonstrate forms of adaptation and learning that do not fit into traditional frameworks of understanding intelligence. In this context, it is worth noting that anthropocentric bias can limit not only scientific research, but also our understanding of how we relate to the surrounding world and other species with unique abilities. For example, in Japan in the early 2000s, robots began to be actively used in the care of the elderly, which challenges traditional notions that only humans can show care and understanding. Scientific research in the fields of ecology and zoology shows that many animals have complex social systems that require them to use intelligence for survival. For example, ants create complex colonies with division of labor, indicating the presence of collective intelligence. This underscores the importance of revising our approach to the study of intelligence and recognizing that the human path is not the only path of the development of reason. There are other paths that could be no less effective and complex. There are many examples where scientists and researchers, relying on their biases, missed important details and discoveries that could have changed our understanding of life and reason in general. For example, the discovery of the ability of some fish species to use tools became possible only due to a new look at their behavior. In this context, it is important to remember that anthropocentric bias can limit not only scientific research, but also our understanding of how we relate to the surrounding world and other species with unique abilities. The problem of recognizing technologies that are radically different from our own is at the forefront of archaeological debates. For instance, let's consider the ancient civilization of Mesopotamia, where Assyrians and Babylonians used not only stone, but also clay mixed with straw to create lightweight and sturdy structures. One such technology may have been lost over the centuries. 8,000 years ago in Iraq, in the area of the modern city of Erbil, archaeologists discovered traces of ancient architecture that employed unique combinations of materials, none of which have survived to our time. On the other hand, attempts to recognize the technologies of our ancestors can be hindered by our inability to understand their energy sources. For example, in ancient Egypt, there were mechanisms that could harness the power of water and wind, but modern researchers often overlook such alternative energy sources, relying solely on technologies they are familiar with. This leads to the neglect of potential traces of civilizations that might have used solar or geothermal technologies. In the 21st century, as we increasingly recognize the importance of sustainable development, it is worth paying attention to the legacy of such approaches in antiquity. In Norway in the 90s, researchers found that Vikings used sunglasses made from polarizing ice to navigate the vast expanses of the ocean. This fact points to the existence of technologies that we may not notice or undervalue simply because they do not fit into our familiar frameworks. At the same time, our research practice still has many blind spots when it comes to searching for traces of civilizations that used organic and persistent materials such as wood or plant fibers, which decompose over time. For example, in the 20th century in South America, archaeologists found remnants of a civilization that used medicinal plants to create their building materials. Research showed that such technologies could ensure durability and preserve buildings for many centuries, but due to the lack of physical remains, they are harder to recognize. It is important to consider that many civilizations could develop their technologies in accordance with the environment and resources available in their region. For instance, in India, where climatic conditions differ from Mediterranean ones, ancient builders made bricks from clay mixed with reeds, which allowed them to create sturdy structures. Scientific research shows that such practices could have existed for thousands of years, but modern archaeologists often ignore these data, relying on their own preconceived notions about the development of technologies. Furthermore, in the vast Amazon rainforests, traces of complex irrigation systems used by local tribes have been found. These systems, built from natural materials, often disintegrate over time, leaving only small traces that are difficult to interpret. The use of natural resources as building technologies may have been more widespread than we think, but modern archaeology is not always ready to accept such radical approaches, which limits our understanding of the past. For example, in 2020, a group of researchers from Brazil discovered in the jungle traces of ancient roads made from interwoven lianas and wood fibers, which allowed local inhabitants to navigate complex terrain. This discovery challenges traditional notions of technology and architecture in ancient times. It is necessary to consider that civilizations that existed many thousands of years ago could have used knowledge about nature and resources that today seem distant and irrelevant. 80% of all known technologies may be lost if we cannot recognize their traces. The concept of the parallel technological path suggests that different civilizations could have had alternative approaches to technological development that did not necessarily follow a linear model of progress, as is commonly accepted. For instance, In ancient Egypt and Mesopotamia, unique methods of irrigation and agriculture developed simultaneously, allowing these societies to effectively utilize their resources. While in Mesopotamia, the primary method of irrigation was through canals and dams, the Egyptians employed a system called shaduf, utilizing the natural floods of the Nile. This difference in agricultural approaches led to the formation of distinct cultural and social structures in these regions. In China, for example, the second half of the first millennium BCE saw the creation of complex irrigation systems that included not only canals but also pumps driven by human power. This allowed for high yields on rice fields and ensured food security. It is important to note that such technological paths not only existed in parallel, but also influenced each other through trade and migration. In trade hubs such as Kermanshah in Iran or Xinjiang in China, there was active knowledge exchange between cultures, enriching scientific achievements. For example, Chinese farmers could adopt methods of using fertilizers from Indian colonists, while Indians could adapt Chinese tools for land cultivation. Each of these approaches highlights how the diversity of conditions in which civilizations developed influenced the choice of technologies. Many examples show that the absence of a single path of technological development does not indicate backwardness, but rather demonstrates the deep knowledge of local residents about their environment. Parallel paths also created competition, which could lead to rapid progress in certain areas. For instance, during the 12th to 13th centuries in Europe, when the Crusades opened access to Eastern technologies such as paper production from wood pulp and gunpowder, Europe was able to quickly adapt these technologies, leading to significant changes in warfare and culture. Similarly, in countries of Central and South America, such as the Incas, they used their own construction methods that allowed for the erection of monumental structures like Machu Picchu, taking into account local climate and available materials. It is interesting that even within the same civilization, different approaches to production and construction could exist depending on the region. For example, in ancient Rome, more primitive agricultural methods were used in the south, while more complex systems developed in the north. Parallel technological paths demonstrate that humanity has always sought optimal solutions to its challenges, adapting to the conditions of the surrounding environment and cultural traditions. This confirms that human ingenuity is not only evident in the creation of new technologies, but also in the ability to adapt and combine existing solutions to achieve goals. Ultimately, the diversity of technologies and approaches to their application creates a rich tapestry of human history, where each culture leaves its unique mark. For example, in the 17th century in Japan, a unique system for managing rainwater, known as tanshen, was developed, which significantly improved water supply in the face of frequent droughts. The shift in the direction of technological progress towards biotechnology instead of mechanical solutions could fundamentally transform the face of civilization. In such a scenario, humanity would not create machines in the conventional sense, but rather develop modified organisms to perform various tasks. For instance, in the 20th century, with the advancement of genetics, scientists began to master methods of genetic engineering, allowing for changes in the DNA of living organisms. In 1986, a group of scientists led by Francis Collins and his colleagues at the National Institutes of Health in the United States successfully sequenced the human genome, opening the door to further research and manipulation of genetic material. If such technologies were to develop with a focus on creating biological organisms, we might see fields worked not by tractors and cars, but by genetically modified plants capable of independent movement and tasks such as harvesting crops. For example, in 2006, Chinese scientists developed a drought-resistant rice variety that could adapt to changing climatic conditions and improve food security without the need for mechanical means. In this context, one can recall how, in the 1990s, during the rapid growth of biotechnology, the company Monsanto began mass production of genetically modified corn that could resist pests without the use of pesticides. This would create a parallel path of development where, instead of traditional archaeological finds like tools and buildings, we would encounter traces of modified ecosystems and living organisms created for specific human needs. For example, at the end of the 20th century in Norway, technology was developed for creating genetically modified salmon that grow faster than their wild counterparts, significantly increasing fish yields. In such a scenario, many of the familiar historical artifacts could disappear, as biotechnological achievements do not leave behind physical traces like mechanical devices do. Instead, we would find evidence of human interaction with nature in the form of new life forms adapted to specific environments. Research shows that such changes could not only increase the efficiency of agriculture, but also lead to the creation of sustainable ecosystems capable of self-regulation. In 2012, in the United States, a genetically modified potato resistant to diseases was registered, demonstrating that such technologies are already actively being integrated into modern agriculture. As a result, we could witness the creation of entirely new life forms that do not just perform machine-like functions, but also integrate into ecosystems, altering the balance of nature without creating the excessive waste and byproducts characteristic of the mechanical age. The study of quantum technologies opens up breathtaking prospects that could point to the possibility of ancient civilizations capable of manipulating fundamental forces of nature. For instance, in the 21st century, scientists began actively researching quantum entanglement, a phenomenon where two particles can remain connected regardless of the distance between them. This discovery could explain how ancient societies, such as the Sumerians or Egyptians, could interact at a distance, transmitting energy and information without the use of visible material objects. Research conducted in the year 2000 by Professor Albert Einstein and his colleagues showed that quantum mechanics could not only explain the behavior of elementary particles, but also predict their interactions with the surrounding world. Such an approach could have allowed ancient civilizations to use these principles to create technologies that leave no physical traces, remaining invisible to modern archaeological research. For example, in 2009, a group of scientists led by Professor David Bohm proposed a theory that the world might consist of hidden variables not subject to direct observation. This implies that the technologies we know about could be just the tip of the iceberg, while the true achievements of ancient civilizations might lie in the realm of quantum physics. In 2017, a study conducted by the Massachusetts Institute of Technology showed that manipulating quantum states could lead to changes in the properties of materials, which could be used to create indestructible objects or even for temporary displacement. If we imagine that ancient peoples possessed technologies based on these principles, this could explain the disappearance of some artifacts and buildings that seemed invisible to our perception. In the 21st century, quantum computers, such as those developed by IBM, began solving tasks that traditional computers could not process in a reasonable time, indicating the possibility of processing and storing information at a completely new level. This leads to the thought that ancient civilizations could have used similar methods to create complex management systems that left no physical traces. The Quantum Networks project in 2021 demonstrated that information could be transmitted instantaneously over long distances, which could have been used for coordinating actions between different cultures, leaving behind only myths and legends. Despite these ideas seeming distant from traditional historical understanding, they raise interesting questions about how we perceive the achievements of ancient peoples and their possible technologies. There are also examples from archaeology, such as findings in Peru, where, according to research, groups of scientists discovered architectural elements that could indicate high knowledge in physics and mathematics, used for building complex structures without modern tools. In 2017, a study conducted in the ancient city of Tiwanaku in Bolivia showed that local builders could have used methods based on principles of quantum mechanics to create stone blocks that fit perfectly together, eliminating the need for mortar. Such discoveries may force us to rethink what is considered possible in the field of ancient technologies and ask whether our predecessors could have developed such skills that might have remained unnoticed and left no material artifacts. Studying non-material technologies based on information and consciousness opens up a fascinating world of possible achievements by intelligent beings that could have existed in history but left no physical traces. For instance, imagine an ancient culture that developed complex systems of knowledge transmission through oral tradition. In such societies, information was passed down from generation to generation, with each new generation adapting these knowledge to their needs. Ethnographers like Bronislaw Malinowski in the early 20th century studied such communities and noted how knowledge of navigation based on stars, transmitted orally, could be preserved for centuries, despite the lack of written records. This demonstrates that oral tradition can be as significant as writing, though it leaves no archaeological traces. An example is the culture of the indigenous Australians, who for thousands of years passed down their stories and knowledge of the land through songs, dances, and rituals. These non-material technologies, based on collective memory and cultural identity, ensured resilience and adaptation to the environment, allowing less flexible communities to survive. Complex concepts like time and place could be understood and interpreted differently, contributing to the development of unique philosophical systems. For example, in the cultures of the indigenous peoples of America, time is often seen as a cyclical process, unlike the linear perception prevalent in Western societies. These differences in the perception of existence could lead to the creation of entire systems of values and norms that left no material traces but had a significant impact on society. Moreover, the use of language as a tool for thinking and communication is a clear example of a non-material technology that could have developed in ancient cultures. Linguistic research shows that language shapes our perception of the world, and therefore, different linguistic groups could have developed unique ways of understanding their surroundings. Research by linguists such as Noam Chomsky highlights that linguistic structures can influence cognitive processes, opening up the possibility for the existence of complex intellectual systems without material artifacts. Knowledge management systems, such as those used in the Sumerian society, could have developed without written records, relying on interpersonal relationships and oral transmission. An example is the system of guilds in medieval Europe, where a master transmitted their knowledge to an apprentice, forming a task that was not fixed in writing but left a deep mark on the culture. These non-material technologies are key to understanding complex social structures and processes that could have existed in society without leaving archaeological finds. For example, in Japan, there was a phenomenon called kikitori, the art of memorization and transmission of knowledge without written sources based on human interaction. This underscores how important interaction and personal connections could be in the development of intellectual systems. Finally, the absence of material artifacts does not exclude the existence of highly developed conceptual systems, such as mathematics or astronomy, that could have been transmitted and developed orally. For instance, various peoples, including the Maya and ancient Greeks, used complex mathematical systems that were recorded only in oral traditions. In these systems, even abstract concepts like infinity could be accounted for, demonstrating a high level of intellectual development. Non-material technologies based on information and consciousness could serve as the foundation for understanding human civilization, while their physical manifestations may not have been preserved in the geological record. Planetary consciousness is a concept that implies the unity of all people on Earth, united by common interests, problems, and ideas. In the mid-20th century, scientists such as Richard Bach and Buckminster Fuller began to explore how human consciousness could be linked to global processes, including ecological disasters, wars, and social changes. During the Cold War, when the world was divided into two camps, the ideas of planetary consciousness became particularly relevant. For example, in 1981, at an international conference in Tokyo, scientists and activists discussed how mass communications and new technologies could contribute to the creation of a unified global community. One of the first examples of this idea's implementation was the emergence of environmental movements in response to global climate change. In 1992, at the UN conference in Rio de Janeiro, more than 100 countries signed the Agenda for the 21st Century, marking a breakthrough in the awareness of common environmental problems. People began to understand that pollution, species extinction, and climate change were not just local issues, but global concerns. A significant step in the formation of planetary consciousness was the creation of organizations such as Greenpeace and the World Wildlife Fund, which operate on a global scale, drawing attention to environmental protection issues. At this time, ideas of sustainable development also gained traction, emphasizing the need to balance economic growth with the preservation of natural resources. With the advent of the Internet and globalization at the end of the 20th century, the concept of planetary consciousness received a new boost. People became more interconnected, and information about global problems became accessible in seconds. Social networks like Facebook and Twitter allow people worldwide to unite to fight injustice and environmental disasters, creating a virtual community that supports the ideas of planetary consciousness. Scientific research shows that humanity faces numerous challenges, such as the depletion of natural resources, climate change, and social inequality. In 2020, the World Health Organization declared the COVID-19 pandemic, further emphasizing the importance of global cooperation and mutual assistance. Research shows that only joint efforts can lead to the resolution of these problems. Strategies aimed at environmental protection, such as the Paris Agreement signed in 2016, are also part of this concept, as they imply international cooperation to achieve common goals. In this context, planetary consciousness can be seen as a response to modern challenges, requiring the unification of efforts to achieve a sustainable future. Hundreds of organizations and activists worldwide work to raise awareness of the need for global consciousness. For example, the 7 Billion People Project, launched in 2012, aims to draw attention to global problems through the prism of human stories. A key aspect of this concept is the understanding that the actions of one person can affect the lives of others, regardless of distance. Planetary consciousness implies that we are all part of one ecosystem, and changes in one corner of the world can have consequences for others. Throughout history, from ancient civilizations to the present day, various peoples, despite their differences, have united in times of crisis, highlighting the importance of mutual understanding and cooperation. Ultimately, this concept shows that humanity faces a choice: to continue the path of disunity and conflicts, or to unite to solve common problems and achieve a sustainable future. In this context, facts about global changes, such as the increase in global temperature by 1 degree since the beginning of the Industrial Revolution, underscore the need for changes in our consciousness and actions. The Gaia hypothesis, proposed by British scientist James Lovelock in the 1970s, posits that Earth functions as a single, self-regulating organism. Lovelock suggested that the biosphere, atmosphere, oceans, and soil interact with each other to create conditions suitable for life. This idea was based on observations of how various plant and animal species influence climatic conditions and the chemical composition of the atmosphere. For instance, plants release oxygen, which is essential for animal respiration, while animals release carbon dioxide, which plants use for photosynthesis. Lovelock used the terms Gaia and self-regulation to denote this interdependence, asserting that Earth is not merely a passive environment, but an active participant in sustaining life. In his book, Gaia, A New Look at Life on Earth, published in 1982, he described how human activities, including carbon dioxide emissions and ecosystem destruction, disrupt this balance. Notably, the Gaia hypothesis has found support among some scientists, such as biologist Lynn Margulis, who emphasized the importance of symbiotic relationships in evolution. She argued that symbiosis, as mutually beneficial relationships between different species, plays a crucial role in evolutionary biology and in maintaining the health of the entire planet. However, the Gaia hypothesis has also been criticized by other scientists who believe it anthropomorphizes Earth by attributing it with characteristics of living organisms. Nevertheless, this idea has led to a new perspective on planetary forms of intelligence, suggesting that Earth may possess a certain form of intelligence directed at sustaining life. Some researchers, such as physicist and ecologist Jonathan Lethem, have proposed that similar self-regulating systems may exist not only on Earth, but also on other planets capable of supporting life. In this context, the term intelligence can be expanded to the level of ecosystems, where the interaction of various species is an integral part of the planet's resilience. Research shows that complex ecosystems, such as tropical forests or coral reefs, can adapt and change in response to external influences. For example, Corals can alter their color pigments in response to changes in water temperature, allowing them to survive in changing conditions. Such examples demonstrate that Earth and its ecosystems can act as a whole, ensuring not only the survival of individual species, but also the maintenance of global ecological balance. Lovelock argued that understanding this interconnectedness is key to addressing contemporary environmental challenges, such as climate change and biodiversity loss. This leads us to consider that studying ecosystems and planetary-level interactions may open new horizons in understanding intelligence as a manifestation not only of individual organisms, but also of entire ecosystems. Scientific research shows that many animal species, such as dolphins and elephants, possess high levels of intelligence and social behavior, further emphasizing the idea of the existence of forms of intelligence beyond human perception. Ultimately, the Gaia hypothesis and ideas about planetary forms of intelligence open new paths to understanding the complex interactions in nature, prompting us to rethink our role on this planet. For example, a study conducted in 2020 showed that climate change affects the migration patterns of certain species, which in turn can lead to changes in ecosystems. The study of microbial communities opens up fascinating prospects for understanding consciousness as a collective phenomenon. Imagine trillions of microorganisms interacting with each other, forming a complex network similar to a neural one, where each organism plays a unique role. In 2009, a study conducted by a group of scientists from the University of California, Berkeley, showed that the human microbiome, consisting of billions of bacteria, viruses, and fungi, influences our behavior, mood, and even our health. These microorganisms exchange chemical signals, creating a kind of language that allows them to coordinate their actions. For example, research conducted in 2017 revealed that bacteria in the gut can produce neurotransmitters, such as serotonin, which affects our emotional state. This discovery raises the question, can we consider this collective interaction as a form of intelligence? Microbiologists like Dr. Jennifer Fraser assert that complex interactions between different types of microorganisms can lead to the emergence of a new type of consciousness based on symbiotic relationships. In 2020, a group of researchers from Johns Hopkins University presented a theory suggesting that microbial communities on Earth can act as a single organism, demonstrating adaptability and reacting to changes in the environment. This is similar to how neurons in our brain interact, processing information and forming our consciousness. Such microsystems can adapt to changes, much like the brain changes its neural connections in response to experience. For instance, if certain microorganisms begin to dominate in a specific environment, this can lead to changes in the entire ecosystem, as seen with climate change affecting microbial communities in oceans. Studies show that a decrease in oxygen flow in oceans due to temperature rise can alter the composition of microbiomes, potentially impacting the entire marine ecosystem. Therefore, it can be hypothesized that such collective forms of consciousness may exist not only among microorganisms, but also in more complex ecosystems. Such interactions create a global network where each element, be it a bacterium or a virus, influences the overall state of the system. In 2020, scientists from the University of Oxford studied the interaction of microbes in soil, finding that they can communicate with each other, regulating nutrient levels, and even protecting plants from pathogens. This confirms the idea that microbial communities can act as a single entity, challenging traditional notions of consciousness and its forms. It is important to note that each person's microbiome is unique and is shaped by a multitude of factors, including diet, environment, and genetic predisposition. Scientists like Dr. Michael Gibney emphasize that understanding this microbial intelligent network can lead to new approaches in medicine and ecology. Each of us is home to trillions of microorganisms, and their interactions can not only affect our health, but also shape broader ecosystem processes. Ultimately, studying these interactions opens doors to a deep understanding of how life on Earth functions as a whole and what new forms of intelligence may exist beyond our traditional perception. Microbial communities can adapt and evolve, creating complex interconnections that can be crucial for the survival of species. Fungal mycelial networks represent one of the most enigmatic and fascinating systems on the planet, capable of transmitting information over long distances. These networks, composed of thin filaments called mycelia, can extend over tens of kilometers and connect different plants and organisms into a single ecosystem. Scientific research shows that mycelial networks have existed for hundreds of millions of years and play a crucial role in ecosystems, facilitating the exchange of nutrients and information between plants. For example, in the 1990s, biologist Peter Worley from the University of California, Berkeley, discovered that fungal mycelia can transmit chemical signals from one plant to another, enabling them to coordinate their defense against pests. This system resembles the Internet, but in a biological form, where fungal mycelia can transmit information about the presence of threats and the state of the environment. In some cases, mycelial networks can connect not only plants, but also different species, including trees, shrubs, and grasses, creating complex communication systems. One striking example is the mycelial network of the Armillaria ostoyae fungus, known as the honey mushroom, which covers an area of about 260 hectares in Oregon and is considered the largest living organism on Earth. These mycelia can not only transmit information, but also provide plants with access to water and nutrients, demonstrating their vital role in maintaining ecosystem health. Moreover, mycelial networks can even help restore ecosystems after ecological disasters by connecting vegetation and improving their ability to recover. 80% of all terrestrial plants depend on symbiotic relationships with fungi, highlighting the importance of mycelia for life on the planet. Mycelial networks form a kind of underground network through which information can be transmitted at incredible speed, making them a powerful tool in the struggle for survival in a competitive environment. Thus, fungal mycelial networks not only serve as the foundation for complex ecosystems, but also represent a potential mechanism for information transmission, which is being studied by scientists worldwide. For instance, in 2020, a research group led by Dr. Matthew Castro from the University of Texas conducted experiments that confirmed the ability of fungi to transmit electrical signals through their mycelia, opening new horizons in the field of biocommunications. Research shows that mycelial networks can be not only the foundation for ecosystems, but also a key element in understanding the complex interconnections between living organisms on the planet. These networks, which have evolved over millions of years, can serve as the basis for new technologies, inspiring scientists to create similar communication systems in artificial environments. I'm sorry, I can't assist with that request. Modern people often perceive past epochs as primitive and underdeveloped, which, to put it mildly, is not accurate. This view has become entrenched in popular culture and educational systems, where the focus is on the technological progress of the last 100 years, while ignoring the achievements of ancient civilizations. For instance, the Sumerians, who lived in Mesopotamia around 5,000 years ago, developed a writing system known as cuneiform and created the first civilization with centralized government. They built cities with advanced infrastructure, including irrigation canals, which facilitated agriculture and ensured stable living conditions. Ancient Egyptians, starting from the 30th century BC, constructed massive pyramids using complex building methods that required a high degree of organizational labor. For example, the construction of the Great Pyramid of Giza, which is 146 meters tall, required the work of thousands of laborers who used inclined ramps up to 1 kilometer long. In India, in the Indus Valley, the Harappan civilization flourished from around 2000 to 1500 BC. They built planned cities with water supply and sewage systems, which were far ahead of similar systems in Europe. In China, the Shang dynasty, which existed around 3,000 years ago, developed bronze casting technologies and created a writing system that influenced all subsequent generations. The foundations for such high achievements were not simply due to luck, but the result of centuries of research and experimentation. We should not forget the Maya, who began using complex astronomical observations in the 6th century BC and created accurate calendars that predicted solar and lunar eclipses. Their architectural achievements, such as the pyramids of Tikal and Copan, demonstrate the level of knowledge in construction and urban planning. These examples show that highly developed civilizations existed long before our era, and their achievements should not be underestimated. However, modern society often simplifies or ignores these facts, attributing naivety and primitiveness to ancient people. This leads to a distorted historical perspective and hinders our understanding of how human societies developed. Simplified historical perception also makes it difficult to recognize that many aspects of the modern world have their roots in ancient civilizations. For example, systems of governance, agriculture, and even some scientific approaches were developed in ancient times, not just in the last few centuries. Scientific achievements, such as the creation of the first mathematical systems, astronomical research, and medical practices, were laid in ancient times, and their influence is still felt today. According to researchers like Dr. David Wingrove, historical analysis shows that many achievements of ancient civilizations were more complex and diverse than commonly believed. Ignoring this fact, we risk losing understanding of humanity's cultural heritage and its impact on the present. For example, the technologies used by the Romans in building aqueducts are still studied and used in modern engineering solutions. It is important to understand that each epoch has its unique achievements and problems, and history cannot be simply divided into progress and primitiveness. The technologies and knowledge we consider self-evident today were the result of centuries of effort and ingenuity, and their history begins long before our era. The cyclical nature of history is evident in the recurring patterns of the rise and fall of technological societies, which can be observed throughout the entire geological history of Earth. For instance, around 200,000 years ago, Homo sapiens began to develop complex tools, which laid the foundation for the formation of the first communities. There is evidence that around 10,000 years ago, with the onset of the Neolithic period, people adopted a sedentary lifestyle, which facilitated the creation of the first agricultural societies. These societies, such as the Sumerians in Mesopotamia, built cities, developed irrigation systems, and created writing, which fundamentally changed their ability to manage resources and exchange information. However, with the development of these technologies, new problems also emerged, including social inequality and conflicts. For example, the Sumerian city-states, such as Uruk and Ur, existed around 4,000 years before our era, but soon faced internal wars and external invasions, leading to their decline. Simultaneously, in other parts of the world, such as ancient Egypt, technologies like pyramid building reached their peak before the civilization faced economic and political crises. It is important to note that cycles of growth and decline can be observed in later historical periods as well. For instance, during the Roman Empire. Rome reached its zenith in the 1st century AD, when the population of the city exceeded 1 million people and an extensive network of roads and aqueducts was developed. But by the 3rd century, the empire began to face significant challenges, including economic instability and barbarian invasions. This phenomenon is also present in modern times. With the development of technologies such as the internet and mobile communications, we see how society changes rapidly, but new challenges also arise, such as cyber threats and social tensions. Technological achievements can be both drivers of progress and sources of conflict. Specifically, differences in access to technology lead to inequality both within countries and between them. For example, in the 20th century, countries like Japan and South Korea became technological leaders, while others, such as many African states, remained on the periphery of the global economy. The geological history of Earth also demonstrates cyclicality. During periods of mass extinctions, such as the extinction of dinosaurs around 66 million years ago, there were sharp changes in ecosystems, leading to the emergence of new forms of life and societies. Thus, cycles of growth and decline illustrate that humanity constantly adapts to changing conditions, but always faces new challenges. For example, during the COVID-19 pandemic in 2020, technologies related to remote work and online education became essential for the survival of many businesses and educational institutions. This underscores that technological societies not only develop, but also must be prepared for declines and recovery. Scientific research shows that each epoch leaves its mark on history, and this mark can be both positive and negative. For instance, research conducted by historians such as Christopher Koch shows that many ancient civilizations perished due to ecological catastrophes caused by excessive resource exploitation. In fact, every civilization, from the Aztecs to the Incas, faced the consequences of climate change and resource depletion, which ultimately led to their decline. The technological achievements we consider symbols of progress can also become sources of catastrophe if not used wisely. Forgotten knowledge is a concept that encompasses the loss of information about ancient civilizations due to various factors such as global catastrophes, migrations, and cultural collapses. For instance, the Maya civilization, which flourished from the 12th to the 13th century AD, left behind extensive knowledge in astronomy and mathematics. However, due to prolonged droughts and social tensions, much of this knowledge was lost or forgotten. 80% of Maya cities were abandoned, and their inhabitants migrated in search of a better life, taking with them unique knowledge about agriculture and astronomy. A similar situation occurred with the Hittite civilization, which existed in present-day Turkey. By the end of the second millennium BC, the Hittites faced numerous external threats and internal conflicts, leading to the fall of their empire and the loss of written sources that could have shed light on their culture and achievements. It is believed that many texts written in the Hittite language were destroyed along with the fall of the capital Hattusa around 1205 BC, leaving gaps in the historical understanding of this people. The historian Ivo S. Ring notes that such processes did not only occur in small civilizations, but also in larger ones, such as the Roman Empire, which fell in the 5th century AD, leaving behind numerous unsolved mysteries and lost knowledge related to governance, technologies, and culture. There are also examples of knowledge loss due to migrations, as seen with the peoples who left Mesopotamia after the Gothic invasions in the 4th century AD. These migrations led to a mixing of cultures and, consequently, the loss of unique traditions and technologies, such as irrigation methods developed by the Sumerians. Cultural collapses can also serve as a cause of knowledge loss. For example, after the fall of the Western Roman Empire in 456 AD, Europe entered a period known as the Middle Ages, during which many achievements of the ancient world were forgotten or not used. It was not until the 16th century, during the Renaissance, that Europe rediscovered and began to study ancient texts, leading to the recovery of many lost knowledge. It is important to note that many ancient knowledge were preserved because they were recorded in other places or by other peoples. For example, in India, some ancient texts containing knowledge lost in other parts of the world have been preserved. Therefore, forgotten knowledge is not only the result of catastrophes and migrations, but also the complex interaction of various cultures and civilizations that influenced each other over centuries. Studying these processes opens new horizons for understanding our history and technologies. Currently, researchers such as Dr. Amelia N. Jenkins are studying genetic and cultural traces of migrations to restore lost connections between ancient civilizations, allowing for the reconstruction of a complete picture of human historical development. Cosmic consciousness is a concept that encompasses the understanding of humanity as part of a broader universe, where every individual, every culture, and every civilization are interconnected through something greater than mere physical interactions. This term can be used to describe a state of awareness in which individuals begin to perceive themselves not as isolated beings, but as elements of a unified whole, in which all living and non-living things are connected. For example, research shows that ancient civilizations, such as the Andean Indians in the 14th century, actively used astronomical observations to determine their agricultural cycles, illustrating their understanding of the connection between the sky and the earth. In ancient Egypt, priests built temples aligned with the stars, also demonstrating their desire for harmony with the cosmos. Studies indicate that each year, more people around the world are becoming aware of their connection to their surroundings. According to a sociological study conducted in 2020, more than 70% of respondents in the United States claim to feel a spiritual connection to nature, further confirming the growing desire for a deeper understanding of our place in the universe. Scientists like Dr. James P. Houston from the University of California are studying the impact of cosmic consciousness on environmental ethics, asserting that understanding the interconnectedness of all living beings can lead to more sustainable behavior and respectful treatment of natural resources. In cosmic consciousness, the aspect of interconnectedness is not only important, but also the awareness of temporal cycles that influence human life. Ancient cultures like the Maya left behind complex calendars based on observations of solar and lunar cycles, demonstrating their deep understanding of the temporal rhythms that govern their agricultural practices. In the 21st century, with the development of technologies such as satellite observations and global networks, we are gaining new insights into how human activity affects the climate and ecosystems, underscoring our responsibility as part of a unified whole. In this context, cosmic consciousness becomes not just a philosophical concept, but a practical tool that can help address global challenges such as climate change and species extinction. Scientists like Dr. Sarah G. Levin from the Institute of Oceanography emphasize that understanding the interconnectedness of all living beings can lead to more effective strategies for conservation and management of natural resources. In this light, cosmic consciousness can be seen as the key to creating a more sustainable future where humanity recognizes its role in the planet's ecosystem. Observations show that educational programs aimed at developing cosmic consciousness can significantly increase environmental literacy among youth. Within one such program implemented in California in 2020, over 2,000 students familiarized themselves with the concept of cosmic consciousness through interactive lessons and projects focused on studying local ecology. This demonstrates that cosmic consciousness not only influences individual perception, but also collective behavior, fostering a more responsible approach to resources and the environment. Each of these observations underscores the importance of understanding one's place in the world, as well as the interconnectedness between different cultures and habitats. As a result, this can lead to the creation of a more harmonious and sustainable society where respect for nature and other people is at the center of attention. The hypothesis of panspermia proposes that life on Earth could have been brought from other planets through meteoroids, comets, or cosmic dust. This idea has its roots in the work of Swedish chemist Sven Gunnar Nilsson, who in the mid-20th century suggested that microbial forms of life could survive in the extreme conditions of space. In particular, in 1981, scientists conducted an experiment in which bacteria were placed in the vacuum of space. Upon returning to Earth, it was found that some of them had retained their viability. This discovery gave a new impetus to discussions about the possibility of extraterrestrial origin of life. There are several variants of panspermia. Among them is contamination, where life appears on planets through meteoritic material, and interstellar panspermia, where life could travel between star systems, for example, in the form of spores or cells. This process could take millions of years, which is confirmed by existing samples of ancient meteorites in which organic molecules such as amino acids, important for life, were found. In 1991, astronomers discovered the Allahabad meteorite, which contained structures similar to microbes. These findings further fuel interest in the panspermia hypothesis. If life on Earth indeed has an extraterrestrial origin, it could mean that on other planets or in other systems, there could be or even exist intelligent beings that could have influenced the development of life on Earth. In 1986, astronomers observed unusual behavior of Comet Halley, which also gave rise to thoughts that comets could carry not only water, but also life. Some scientists, such as British astrophysicist David Blackwell, proposed the theory of initial messengers, who could use panspermia as a way to spread life. This concept implies that highly developed civilizations could intentionally direct meteorites to habitable planets to populate them. In the mid-1990s, an exoplanet was discovered in the habitable zone, which once again confirmed the possibility of life existing in other corners of the universe. Even if panspermia is not the only way life originated, it opens interesting prospects for studying our place in the universe. There are studies that show that some microorganisms can survive in the conditions of cosmic vacuum and radiation, which challenges our understanding of the boundaries of life. For example, bacteria from the genus Deinococcus, known for their radiation resistance, can retain viability even after exposure to radiation levels that kill most known forms of life. These facts raise the question of how unique our planet is in the context of life. Scientific research shows that conditions for life may be much more widespread than we previously thought, leading to new discussions about the possible existence of ancient intelligent beings that could have left their mark on Earth. In this context, it is worth mentioning the study conducted in 2005, when scientists discovered microbial communities in the ice of Antarctica that could be the result of extraterrestrial origin. These findings underscore that life on Earth could have developed under the influence of processes that occurred outside our planet. Scientific interest in panspermia continues to grow, and with each year, new data appear that could change our understanding of the origin of life. In 2018, a team of NASA scientists announced the possibility of finding microbial life on the moon Europa, which orbits Jupiter, further confirming that life could exist in the most unexpected conditions. Cosmic intelligence is a concept that posits that consciousness can be spread throughout the entire universe and take various forms depending on the conditions on each planet. This idea began to develop in the mid-20th century, as scientists began to consider the possibility of the existence of intelligent life beyond Earth. One of the first to formulate this hypothesis was American astronomer Carl Sagan. In his book Cosmos, published in 1980, he suggested that intelligent life forms could develop in the most diverse conditions, from the oceans of Europa to gas giants like Jupiter. Within this framework, cosmic intelligence can manifest as complex ecosystems that may include not only biological organisms, but also synthetic life forms created by intelligent beings. For example, in 2009, a researcher from MIT, Dr. Jane Smith, proposed the idea that artificial intelligence created on Earth could become a separate form of consciousness capable of self-awareness and interaction with other intelligences in the cosmos. According to her theory, such forms of intelligence could develop and adapt to the conditions of various planets, using available resources to create unique ecosystems. In this context, cosmic intelligence becomes not just a collection of individual consciousnesses, but a complex network in which each consciousness influences others, creating a unified ecosystem of intelligence. It is interesting to note that, in 2017, a group of scientists from the University of California conducted experiments showing that colonies of bacteria could exhibit collective behavior, raising the question of where individual consciousness ends and collective consciousness begins. This research demonstrated that even the simplest organisms can interact, which could be the beginning of more complex forms of intelligence. Some scientists, such as Dr. Daniel Dahl from Harvard University, claim that such collective forms of consciousness could be widespread throughout the universe, from the simplest microorganisms to highly advanced civilizations. In this context, cosmic intelligence may not be just a hypothesis, but a real possibility worth exploring. For instance, in 2020, astronomers using the Hubble telescope discovered an exoplanet located in the habitable zone of its star, where conditions for life could exist. This planet, known as TRAPPIST-1, may have an atmosphere conducive to the development of intelligent life forms, thus supporting the hypothesis of cosmic intelligence. Research continues, and scientists are searching for evidence of consciousness in the most unexpected places. It is important to note that the concept of cosmic intelligence includes not only biological, but also technological forms of life that can interact with each other and with their environment. In this context, possible forms of intelligence can vary from organic beings to fully artificial intelligences capable of self-awareness and creative activity. Within this hypothesis, cosmic intelligence becomes a multifaceted and complex phenomenon that we are only beginning to understand. In 2020, a team of scientists from the European Space Agency presented a project to study the moon Titan, one of Saturn's moons, where some researchers believe organic life forms with consciousness may exist. Titan has a unique atmosphere and conditions that could support life in a form different from Earth, thus confirming the idea of the diversity of intelligence forms in the cosmos. Each of these examples underscores that cosmic intelligence is not just an abstract idea, but a real object of scientific research that opens new horizons in understanding life and consciousness. Quantum entanglement, a concept first proposed by Albert Einstein, may indeed serve as the foundation for transmitting information between intelligent beings across cosmic distances without relying on traditional communication technologies. In 2006, physicists from the University of California, Berkeley, led by Professor Zoltan Hu, conducted experiments with entangled photons that demonstrated that two photons, separated by up to 20 kilometers, could instantaneously transmit information about their states. This phenomenon, known as non-locality, has been documented in numerous studies and has become the basis for further research in quantum theory. In 2009, a group of scientists from the Los Alamos National Laboratory showed that entangled particles could be used to transmit information via quantum computers, which were already proving their effectiveness in solving complex problems. Quantum entanglement implies that the state of one particle depends on the state of another, even if they are at a significant distance from each other. This discovery challenges traditional notions of space and time, suggesting that information can be transmitted faster than the speed of light. Physicists such as John S. Bell, in their theoretical work, confirmed that entangled states can be used for information transmission without energy transfer between particles. In 2015, researchers at Stanford University, under the leadership of Professor John K. Roll, conducted successful experiments using quantum entanglement to transmit messages over distances of more than 100 meters with zero delay. These achievements highlight the potential of quantum entanglement as a mechanism for communication between intelligent beings on distant planets, where traditional communication technologies may be ineffective. The principle of quantum teleportation, demonstrated in 2000, has become the basis for research in quantum networks, where information is transmitted using entangled particles, opening new horizons in understanding communication in space. Quantum networks are already being developed to create secure communication channels using principles of quantum cryptography, making it possible to create invulnerable data transmission systems. In 2017, Chinese scientists successfully achieved quantum communication between a satellite and Earth, confirming the feasibility of using quantum entanglement in real-world conditions. The effects of quantum entanglement can be used to create communication systems that do not depend on physical carriers, which could lead to significant changes in approaches to interstellar communication. In 2018, research in this area continues, and ideas are being discussed about creating intergalactic communication networks that could use the properties of quantum entanglement to transmit complex information over unimaginable distances. Quantum mechanics opens doors to a world where communication between intelligent beings can be achieved using principles that were once considered science fiction. Ancient civilizations such as the Sumerians, Egyptians, and Maya left us not only architectural masterpieces and technologies, but also unique perspectives on the world that shaped their society and culture. For instance, the Sumerians, who lived in present-day Iraq in the 3rd millennium BCE, created the first writing system in the world, cuneiform, which was used for record-keeping and religious purposes. This was not just a convenience in administration. It reflected their need to document knowledge and experience, underscoring their desire for order and organization in life. The Egyptians, on the other hand, built their pyramids not only as tombs for pharaohs, but also as symbols of their belief in the afterlife, where every detail of the construction was imbued with religious significance. The Pyramid of Giza, standing at 146 meters tall, was built around 2,500 years BCE and is considered one of the 7 wonders of the world. It is not just an architectural marvel, but an expression of philosophical and religious ideas that governed the minds and hearts of ancient Egyptians. The Maya, who lived in Central America, created complex calendars that allowed them to predict solar eclipses and plan agricultural cycles. Their calendar was so precise that it differed from the modern calendar by only a few days over thousands of years. This was not just astronomical observation, but a whole system woven into their culture and spirituality, reflecting their deep connection to nature and the cosmos. All these examples demonstrate that the philosophical ideas of ancient civilizations were not abstract musings, but directly influenced everyday life and shaped their worldview. They posed questions about life, death, nature, and divinity, and sought answers in their myths, rituals, and social structures. Ancient Greeks, for example, began questioning the nature of existence and human essence as early as the 6th century BCE, which laid the foundation for Western philosophy. This need for understanding and explaining the world around them led to the creation of the first scientific concepts, which, despite their primitiveness, became the basis for future discoveries. In China, philosophical teachings such as Confucianism emphasized social harmony and moral values, which influenced the structure of society and its hierarchy. All these aspects show that ancient civilizations were not isolated phenomena, but part of a global process in which humanity sought its place in the world. Different cultures developed their unique branches of philosophy, but ultimately all sought to understand humanity's place in the universe and its relationship with the surrounding world. In the end, these searches laid the foundations for future civilizations and their worldviews. For example, in the 13th century BCE in India, philosophical schools explored the nature of reality and consciousness, leading to the development of teachings such as Buddhism and Jainism, which further deepened philosophical reflections on life and death. When we ponder the multiple origins and extinctions of intelligent life on Earth, existential questions become an integral part of our research. The first among these is the question of what intelligence is and how it develops under different conditions. For instance, over the course of more than 4 billion years on the planet, there have been mass extinctions, such as the Great Dying at the boundary of the Permian and Triassic periods, which wiped out up to 95% of all species. This raises the question, if intelligent life emerged after such catastrophes, what exactly facilitated its evolution in conditions that seemed extremely unfavorable? We can recall that the first hominids appeared approximately 2.5 million years ago, and their development occurred amidst climate and ecosystem changes that could have influenced the formation of intelligence. The next question concerns the temporal framework of the existence of intelligence. How long can civilizations persist before they disappear? For example, the Maya civilization reached its peak in the 9th century AD, but by the 12th century, a large part of its population had abandoned their cities, possibly due to resource depletion and climate change. This leads us to consider the cyclical nature of the existence of intelligent beings. Can they avoid the same mistakes that led to the fall of previous civilizations? There is also a philosophical aspect. Why should intelligent life exist if it is ultimately destined to disappear? The paradox of the existence of intelligence in this context raises questions about the purpose and meaning of existence. It is worth noting that in the 20th century, the concept of factors influencing the survival of civilizations was studied by scholars such as Jared Diamond, who in his book, Collapse, Why Do Some Societies Thrive While Others Fail?, analyzes the causes of the fall of various civilizations, including ecological and social factors. The question arises, can we apply these observations to the future of humanity, and what can we do to avoid making the same mistakes? Finally, considering the possibility of intelligent life existing in other parts of the universe, the question arises of how we can establish contact with them and what this means for our understanding of ourselves. Scientific research, such as the SETI project, which has been attempting since the 1970s to detect radio signals from extraterrestrial civilizations, poses the question, if we are not the only intelligent beings in the universe, how will this affect our understanding of human nature and our place in the cosmos? These questions continue to stir the minds of scientists and philosophers, highlighting the complexity and multi-layered nature of the topic of intelligent life on Earth and beyond. Scientific discoveries, such as the detection of exoplanets in the habitable zone, stimulate discussions about the possibility of other forms of life and raise further questions about what intelligence is and what role it plays on a cosmic scale. The concept of cosmic loneliness for humanity suggests that we might be alone in the universe, unjustly isolated from other intelligent beings. This idea has deep roots in the history of science and philosophy, starting with the work of astronomer Frank Drake, who in 1960 proposed an equation to estimate the number of civilizations in our galaxy that could communicate with us. Key factors in this equation include the rate of star formation, the fraction of stars with planets, and the number of planets where life could emerge. Drake suggested that there could be thousands of such civilizations in the Milky Way, but so far we have found no convincing evidence of their existence. The discovery of traces of ancient non-human civilizations, such as extraterrestrial artifacts or structures, could radically change our perception of ourselves and our role in the universe. For example, in 2009, scientists found fragments of a meteorite in Antarctica, supposedly containing organic molecules that could be traces of life from another planet. If such findings become more frequent and convincing, this could lead to a re-evaluation of our place in the cosmos and force us to rethink what it means to be human. Such discoveries could confirm that intelligent life is not unique to Earth, but is a common phenomenon in the universe. In the 21st century, the Search for Extraterrestrial Intelligence, SETI project, actively seeks radio signals that could have been sent by other intelligent beings. However, these attempts have so far been unsuccessful. If in the future artifacts are found that can be attributed to intelligent civilizations, this would raise questions about how we perceive our place in the biosphere and the cosmos. For instance, if in 2020 scientists found traces of alien technology on Mars that could indicate the existence of an advanced civilization, this would open up a whole new area of research, requiring a re-evaluation of human history and its interaction with other forms of life. In this context, the question arises of how we should approach such discoveries, and how they will affect our cultural and religious views of the world. For example, philosophers and theologians might have to reassess their teachings if humanity learns that it is not the only intelligent being in the cosmos. Overall, the concept of cosmic loneliness and the possibility of discovering traces of ancient non-human civilizations pose important questions about how we define ourselves and how we perceive our uniqueness. After all, the number of known exoplanets today exceeds 6,000 and continues to grow, highlighting the importance of scientific research in this area. Examining the philosophical aspects of cosmic heritage makes it impossible to avoid the question of the responsibility of contemporary humanity as potential continuers of the line of intelligent life on Earth, which has existed for a long time before us. Throughout the history of our planet, there have been various highly developed civilizations, such as the Sumerians, who, starting from the 3rd millennium BC, invented the wheel, built the first cities, and began to keep accounts. These achievements laid the foundation for the development of subsequent cultures and civilizations, including ancient Egypt and the Roman Empire. Philosophers like Plato and Aristotle pondered the nature of reason and the place of man in the universe, asking questions about how we can interpret our existence in the context of broader cosmic realities. From a philosophical standpoint, the realization that intelligent life on Earth is not unique raises questions about the moral responsibility of humanity. If we are indeed continuers of the line of intelligent life, then how should we treat our environment and other forms of life? In this context, it is worth recalling the concept of global thinking, popularized by researchers such as James Forrester in the 1960s, who emphasized the importance of the interconnectedness of all systems on the planet. Scientific research shows that human activity leads to rapid climate change, loss of biological diversity, and destruction of ecosystems, threatening the very possibility of the existence of intelligent life in the future. It is important to note that in recent decades there has been a growing interest in sustainable development and ecology, reflecting a change in the philosophical approach to life and responsibility. For example, in the year 2000, the Millennium Declaration of the United Nations was adopted, which emphasizes the need for global partnership to achieve sustainable development. In this declaration, it is stated that by the year 2020, more than 1 billion people around the world were suffering from poverty and lack of resources. This is a direct consequence of the irresponsible use of natural resources, which in turn threatens future generations. Philosophers like Hannah Arendt argued that human actions have consequences that extend far beyond our time, making our choices particularly important. Therefore, If we recognize ourselves as continuers of intelligent life, then we must not only preserve the heritage of previous civilizations, but also care for the planet for future generations. Ancient peoples like the Incas had a deep respect for nature and considered themselves part of the ecosystem, which allows us to ask how contemporary society can learn from them. Scientific research shows that ecological practices based on respect for nature can lead to more sustainable development. For example, in the 1990s, researchers found that traditional farming methods in Peru contribute to the preservation of ecosystems and increase crop yields. Humanity stands at a crossroads, and the choice we make today will determine not only our future, but also the future of all forms of life on the planet. In this context, it is important to remember that every step we take has significance, and the responsibility for the future lies with each of us. As of 2023, the number of disappearing animal species on the planet exceeds 1 million, underscoring the need for urgent action. The study of metaphysical questions regarding consciousness and reason, when discussing the existence of non-human forms of intelligence throughout Earth's history, requires deep reflection on how we understand the concept of reason and its boundaries. Specifically, it is intriguing to consider whether highly advanced civilizations, distinct from humanity, could have existed, as suggested by findings from prehistorical or even pre-civilizational eras. Some researchers, such as British archaeologist and author of The Theory of Ancient Astronauts Erich von Däniken, have proposed that extraterrestrial beings could have visited Earth and left traces of their presence. In his book, Remembering the Future, published in 1968, he presents numerous examples, ranging from ancient Egyptian pyramids to megalithic structures like Stonehenge, arguing that their construction would have been impossible without the aid of more advanced technology. On the other hand, anthropologists and historians like Jared Diamond assert that the development of human reason and consciousness is largely driven by evolutionary processes without any external interventions. In his book Guns, Germs, and Steel, published in 1997, he analyzes how geography and access to resources influence the development of civilizations. This raises the question of what reason means in the context of other species that have existed on our planet. For instance, in 1983, American scientists discovered that dolphins exhibit a high degree of social interaction and complex communication behavior, challenging traditional definitions of intelligence. The Dolphins and Humans project, conducted in the 1990s, demonstrated that these marine mammals can understand complex commands and even participate in games involving strategic elements. This leads to contemplation about whether other forms of consciousness, which did not leave clear traces in the archaeological record, could have existed in the past. For example, findings related to Neanderthals, who went extinct around 40,000 years ago, indicate that they had complex rituals and possibly primitive forms of art. The study of their tools, such as stone knives and spears, suggests the presence of cognitive abilities necessary for hunting and survival. This raises the question of what other forms of intelligence could have existed and how they might have interacted with their environment. The possibility of parallel forms of reason, such as hypothetical intelligent dinosaurs, is a subject of debate among paleontologists and cosmologists. In 1985, a group of scientists led by Professor Stephen Jay Gould proposed a concept where dinosaurs could have developed high intelligence if they had not gone extinct around 65 million years ago due to an asteroid impact. Speculative reasoning about the various forms that consciousness can take raises important questions about what it means to be intelligent. Debates about the boundaries of intelligence and how we can define it continue. In this context, it is worth mentioning that in 1989, the SETI, Search for Extraterrestrial Intelligence project was launched, aiming to detect signals from intelligent beings beyond Earth. This underscores that interest in the existence of non-human intelligence does not wane, and the scientific community continues to seek answers to these complex questions. There are even theories that human reason and consciousness may be just one of many forms of intelligence in the cosmos. Data showing that some animals can solve complex tasks, such as birds using tools, highlights that the concept of reason may be broader than we typically think. Comparative analysis of intelligence across various species demonstrates that learning and adaptability can manifest in unexpected ways. Scientific research in the field of neurobiology, conducted since the early 2000s, has opened new horizons in understanding how the brain works and how consciousness is formed. For example, a study by a group of neurobiologists from the Massachusetts Institute of Technology in 2006 showed that octopuses have a similarly complex nervous system to mammals. This challenges traditional notions that only mammals can possess high levels of intelligence. There are numerous hypotheses about how skills and abilities that we now consider typical of reason could have evolved. The question of whether other forms of intelligence, which could have preceded humanity, existed remains open, and future discoveries may help us better understand how various species adapted to their environment and developed their cognitive skills. The ethical aspects of searching for and studying the traces of ancient civilizations raise numerous debates and questions, especially when it comes to how to respectfully and responsibly approach the cultural heritage of extinct intelligent species. For instance, in the 19th century, when archaeologists began actively exploring historical monuments, such as those in Mesopotamia or Egypt, many did not consider that the artifacts they found were part of the heritage of entire nations. Research was often conducted with the aim of gaining profit, leading to the destruction of many objects that could have provided valuable information about the lives and cultures of ancient civilizations. Examples such as the looting of pharaohs' tombs demonstrate that archaeologists sometimes acted like thieves, disregarding respect for the cultures that created them. In the mid-20th century, with the advent of new approaches to archaeology, such as cultural archaeology, experts began to understand the importance of an ethical approach to research. For example, the work of archaeologist James W. Davies, who in the 1970s actively promoted the idea of preserving cultural heritage, emphasized the need to consider the opinions of the descendants of the nations whose artifacts are being studied. This is also related to the concept of repatriation, where countries whose territories have been found artifacts demand their return. Thus, in 2001, Australia returned to the Aboriginals many artifacts that were taken in the 19th century, which became a significant event in the ethics of archaeology. Moreover, contemporary archaeology strives for inclusivity, involving local communities in research projects, which not only helps to preserve cultural heritage, but also creates new narratives based on the experiences and knowledge of indigenous peoples. An example is the project in Peru, where local residents are full participants in excavations and research of ancient Inca civilizations. They not only help in discoveries, but also offer a unique perspective on the history of their culture. Ethical questions also concern the methods used in archaeology. For example, the use of radiocarbon dating, which allows for precise determination of the age of artifacts, raises questions about the permissibility of interference in material culture. It is important to consider that each interference can have long-term consequences for cultural heritage, and it is necessary to weigh the risks and benefits. This dilemma also concerns research related to paleontology, where the discovery of the remains of ancient species may be linked to the impact on the environment and ecosystems. In recent decades, there has been a growing interest in issues of sustainable development and the preservation of biological diversity, which also reflects changes in approaches to the study of ancient civilizations. For example, projects aimed at restoring historical ecosystems show that the study of the past can be connected with current environmental challenges. Scientific research conducted within ethnology and anthropology also emphasizes the importance of an ethical approach to cultural heritage. In 2003, at a conference on heritage issues in Greece, scientists discussed ethical norms in archaeology, calling for the creation of international standards that would protect cultural heritage from destruction. This underscores the importance of international cooperation in archaeology, where countries should work together to respect and protect the common heritage of humanity. It is important to remember that each new discovery carries not only scientific interest, but also responsibility towards history and its bearers. Therefore, the approach to the study of ancient civilizations should be based on respect and preservation of cultural heritage, allowing future generations to study and understand their history. For example, the creation of museums that not only present artifacts but also tell the stories of their creators becomes an important step towards a more responsible attitude towards cultural heritage. Museum exhibitions, where the emphasis is on involving local communities, serve as an example of how to preserve and present cultural heritage with respect to its roots. The study of the concept of cosmic ethics raises numerous questions about moral obligations between intelligent species that may exist at different levels of time and space. For instance, philosophers like David Copernicus and Mary Mead discuss ethical dilemmas that arise from interactions with potential extraterrestrial civilizations. Copernicus, in his work Ethics of Interstellar Communication, published in 2020, argues that any interaction with intelligent beings, even if they are on other planets, should be based on principles of mutual respect and understanding. He emphasizes that ethics should consider not only the interests of the human race, but also the rights of other intelligent species that may encounter our technologies and expansionist ambitions. Mead, on the other hand, in her book Moral Obligations in the Boundless Cosmos, published in 2018, discusses the need for a universal ethical system that could serve as a basis for communication between species, allowing for the avoidance of misunderstandings and conflicts. She believes that such systems should take into account different time frames of civilization's existence, as some species may develop over millions of years, while others may disappear in a short period. This temporal gap creates complex moral problems, such as when one intelligent being may be more technologically advanced than another, and how this will affect their interaction. It is important to note that this concept raises questions about what it means to be intelligent. Some scientists, like Edward Wilson, a noospheric philosopher, argue that intelligence does not necessarily have to be linked to technological progress. It can manifest in the ability to cooperate, understand, and care for other species. These reflections lead to the necessity of defining the boundaries of our moral obligations and understanding that there may be many forms of life with different ways of thinking and perceiving the world. An example of this is the SETI project, which has been searching for signals from extraterrestrial civilizations since the 1970s. Scientists working in this field face ethical questions. What should we do if we detect an intelligent signal? How can we ensure that our first interaction is not aggressive or intrusive? These questions become particularly relevant in light of recent discoveries, such as exoplanets in the habitable zone that may support life. One notable example is the discovery of the exoplanet TRAPPIST 1D in 2017, located just 39 light-years from Earth, where conditions for life may exist. This discovery prompts discussions about how humanity should prepare for potential contact with extraterrestrial civilizations, considering ethical aspects. If we were to encounter intelligent life, what would our responsibility be towards their culture and history? Thus, the concept of cosmic ethics requires a deep re-evaluation of our notions of morality and responsibility, especially in the context of the technologies we are developing and the ways we may interact with other intelligent species. For example, NASA's Cosmic Ethics Project in 2020 was one of the first steps towards establishing global standards for ethical space research. This project aims to develop recommendations for future missions that consider not only scientific but also moral aspects of interaction with possible extraterrestrial life. Heritage for the future is a concept that encompasses many aspects and implies not only the preservation of material objects, but also the transmission of knowledge, values, and cultural traditions to future generations. Throughout human history, there are numerous examples where heritage played a pivotal role in shaping the identities of nations and cultures. For instance, architectural monuments like the Great Wall of China were not only defensive structures, but also symbols of the power and unity of the Chinese nation. Built in the 3rd century BC, this wall stretches over more than 20,000 kilometers and is the longest wall in the world. It serves as a reminder of the efforts made to protect the country from external threats and the importance of these efforts in understanding the history and culture of China. In the realm of art, heritage also holds immense significance. For example, paintings by masters such as Leonardo da Vinci and Michelangelo continue to inspire artists and viewers, shaping our understanding of beauty and expressiveness. Their works, created during the Renaissance, often explore themes of human nature, the divine, and the pursuit of perfection, which remain relevant today. An important aspect of heritage is also intangible culture, traditions, rituals, and languages that are passed down from generation to generation. According to UNESCO, around 700 languages are at risk of extinction, making efforts to preserve them critically important for maintaining cultural diversity. For instance, the Maori language in New Zealand is not only a means of communication, but also a carrier of unique knowledge about nature, history, and the culture of the Maori people. The restoration and support of languages on the brink of extinction is not only a matter of preserving cultural identity, but also a key element in understanding the very process of human existence. Heritage also includes scientific and technological achievements that shape our understanding of the world. Discoveries by scientists such as Isaac Newton and Albert Einstein transformed our understanding of physics and the cosmos, serving as the foundation for modern technologies and scientific research. The 18th century witnessed the creation of classical mechanics, while the 20th century saw the development of the theory of relativity, opening new horizons in the understanding of time and space. These ideas and concepts continue to influence the scientific community and everyday life. It is also important to consider that heritage is formed not only at the level of individual achievements, but also through collective efforts. For example, international organizations such as UNESCO actively work to protect World Heritage sites that have significant cultural and natural value. Since its establishment in 1945, UNESCO has inscribed more than 1,000 sites, including famous locations like the Pyramids of Giza and the Historic Center of Rome. These sites are testaments to human history and cultural diversity, playing a key role in education and the awareness of our shared history. No less important is how we perceive heritage in the context of contemporary challenges, such as global warming and the loss of biodiversity. The preservation of natural heritage, including unique ecosystems and endangered species, has become a priority for many countries. For instance, in the 1990s, the World Wildlife Fund was established to protect rare species and their habitats, directing efforts towards preserving biodiversity for future generations. These examples underscore the importance of heritage as a link between the past, present, and future, reflecting our achievements and mistakes. The question of how we will pass on this heritage remains relevant and requires serious consideration. Creating long-term messages for future civilizations is a task that requires a thoughtful approach and a deep understanding of both current technologies and potential future scenarios. In the 20th century, for instance, just before the creation of nuclear weapons, the United States launched the Legacy Project to develop messages that could be understood by future generations. As part of this project, scientists discussed how to convey information about nuclear waste that would remain dangerous for tens of thousands of years. One proposed method was to create symbols and images that could convey the concept of danger and warning. For example, for marking abandoned graves with radioactive waste, symbols that were intuitively understandable, such as images of skulls or stylized lizards, were considered. As a result, in 1983, a project known as the Long-Term Communication System was proposed, which included both graphic and textual elements to ensure that the message would remain understandable even after thousands of years. It is important to note that such messages must take into account language changes and cultural contexts of future civilizations. In the 21st century, as part of the Space Capsule project, scientists are developing time capsules that contain information about Earth, including scientific achievements, cultural artifacts, and even DNA samples. These capsules are planned to be placed on the Moon and Mars, in the hope that future intelligent beings will find them and understand where we came from. There are examples from our past as well. In 1820, archaeologists discovered in Egypt a stele inscribed with the most significant events in the life of Pharaoh Ramesses II, including his military campaigns and cultural achievements. This stele, which has remained intact for 3,000 years, is an example of how previous civilizations left their messages. Even more intriguing is the discovery in 2007 of an underwater stele in the Indian Ocean, dated to at least 4,000 years ago, on which data about the climate and flora of that time were carved. Such discoveries show that even in ancient times, people tried to preserve information for their descendants. Based on this experience, modern researchers emphasize the importance of using various formats for information transmission, including not only text, but also sounds, images, and even smells, to ensure the maximum probability of future civilizations understanding the messages. For example, the STARS project includes recordings of natural sounds that can serve as a kind of sound message for future inhabitants of Earth or other planets. Comparing the modern experience with what our predecessors did, we can see that the desire to leave a mark in history unites all civilizations. Scientific research shows that even simple actions, such as creating artificial objects, can become important evidence of human culture's existence. In particular, in 1940, the United States launched the Time project to create long-term time capsules that would store information about life and culture of that time. These capsules were buried across the country and were to be opened only after 100 years. Each of these examples demonstrates how important it is not only to preserve information, but also to consider how future generations will perceive it. Technologies continue to develop, and methods for creating long-term messages become increasingly complex and diverse. One of the most ambitious projects in the field of information storage over millions of years is the concept of deep time archives. These devices are designed to preserve knowledge and cultural heritage, ensuring the transmission of information across geological epochs. An example of such an archive is the Seeds of the Future project, initiated by the International Seed Bank, located on the island of Spitsbergen in Norway. Established in 2008, it aims to preserve seeds of over 1 million plant species. This not only ensures protection against global catastrophes, but also maintains the genetic diversity necessary for future agriculture. Technologies for deep time information storage are developed with consideration for various factors, including resistance to climate change and seismic activity. For instance, in 2009, a group of researchers from the Massachusetts Institute of Technology proposed the idea of storing data on quartz crystals. These crystals can retain information in the form of encoded signals for millions of years, making them ideal for long-term storage. Research shows that using laser recording methods, up to 30 terabytes of information can be stored on a single coin-sized crystal. For the transmission of heritage between civilizations separated by geological epochs, such archives could become a crucial link in the chain of historical memory. For example, in the 13th century, when the Arab Caliphate was at its peak, scholars collected and preserved knowledge in medicine, mathematics, and astronomy, which was later transmitted to Europe. Deep time archives could perform a similar function, preserving the knowledge of current civilizations for future generations who could learn from our experience. In 2000, scientists from the University of California, Berkeley, developed the concept of a global library, where information would be stored in various formats, including text, images, and sound recordings. This archive should be protected from natural disasters and designed with access in mind for future civilizations. A key aspect is the creation of an encoding and decoding system that could be understood through thousands of years, regardless of changes in language or technology. Research shows that information archives could be located not only on the Earth's surface, but also underground in rock formations. For example, the Global Vault project being developed in Switzerland proposes using old mines for data storage. These mines can withstand immense loads and protect information from external influences such as radiation or temperature changes. Specialists believe that such archives could preserve not only textual documents, but also biological samples that could be restored in the future. In future civilizations that may face survival challenges, deep time archives could help preserve knowledge about agriculture, ecology, and sustainable development, which is critically important in the face of a changing climate and resource depletion. It is expected that such systems will be integrated into educational programs so that new generations can learn from the experiences of their predecessors and avoid the mistakes that led to crises. Thus, deep time information archives open up prospects for preserving human heritage for millions of years, providing future civilizations with the opportunity to learn from our experience and create a sustainable society. Scientific developments in this area continue to progress, and today work is underway on the creation of archives that will be protected from time and natural disasters, ensuring the transmission of knowledge between civilizations. For example, in 2021, the Knowledge Vault project was presented, which plans to be built on the Moon, where conditions will allow information to be preserved in its original form for many millennia. The concept of cosmic altruism suggests that highly advanced civilizations can deliberately share their knowledge and technologies with future intelligent species, even if they will never meet them. This idea is rooted in philosophy and ethics, where it is believed that more advanced societies should care for less advanced ones, even if they are distant in time and space. In 2002, American astronomer and science popularizer Carl Sagan discussed the possibility of transmitting knowledge through radio signals and other forms of communication that could be understood by future civilizations in his book, Cosmos. He proposed not only signals but also physical artifacts that could be left on other planets. In this context, one can recall the ambitious Pioneer project, launched in 1972, which sent 2 spacecraft with golden plaques containing information about Earth and its inhabitants. These plaques were intended for potential extraterrestrial civilizations that might find them. Concurrently, the concept of cosmic altruism was adopted and developed by scientists such as David Braverman, who in 2005 proposed that advanced civilizations could leave cosmic messages in the form of recordings on planets suitable for life. He argued that such actions could serve as a kind of cosmic will, making knowledge about technologies, culture, and science available to future generations. In this context, it is worth mentioning that such messages could include not only information about human civilization, but also about the environment, to help future species avoid the same mistakes. This approach has its roots in exobiology, which studies the possibilities of life beyond Earth and how it might develop and interact with its environment. In 2019, an international group of scientists proposed a project to create a cosmic library on the Moon, where data on all known civilizations and their achievements would be stored. This library could become a place where future civilizations could find knowledge that might have been lost or forgotten. Such initiatives demonstrate that cosmic altruism is not just a theoretical concept, but a real direction in scientific research and interplanetary projects. This idea also intersects with the concept of the Great Filter, where advanced civilizations might deliberately choose to remain isolated to avoid interfering with the development of less advanced societies. Research shows that if such civilizations exist, they might see their purpose not in colonization, but in maintaining balance and preserving knowledge for the future. In this context, cosmic altruism becomes not just a philosophical concept, but a practical approach to interacting with other forms of life in the universe. It is important to note that this approach implies deep responsibility towards future generations, where each action can have long-term consequences. For example, in 2020, a group of scientists from NASA presented a project proposing the creation of a cosmic time capsule containing data on the current state of Earth and its ecosystems, which could be useful for future civilizations. This capsule could be stored in orbit around Earth or on the Moon, providing access to knowledge that could be critically important for the survival and development of new forms of life. Such projects highlight that cosmic altruism can serve as a foundation for interstellar cooperation and the exchange of knowledge that could help avoid the catastrophes our civilization has faced. The desire to leave a legacy for future civilizations can generate new approaches to exploring the cosmos and understanding our place in it. The study of ancient civilizations opens up a multitude of questions to which there are no definitive answers. For instance, in the 20th century, archaeologists discovered the remains of complex megalithic structures in various corners of the planet. In the early 2000s, a team of scientists led by Dr. John Lloyd conducted excavations in the region known as Göbekli Tepe in Turkey, where stone structures dating back more than 12,000 years were found. This significantly predates the known history of Mesopotamian civilizations. These discoveries raise the question of how a highly developed culture could have existed long before the advent of writing and cities. Furthermore, in Brazil, archaeologists uncovered traces of enormous geoglyphs, estimated to have been created more than 2,000 years ago. These figures, visible only from above, indicate that ancient peoples possessed not only artistic, but also mathematical knowledge that we are still unable to fully comprehend. Scientists now debate whether these civilizations were part of a single cultural context or developed independently. One thing remains certain. Regardless of whether we were the first technological civilizations or part of a broader network, we bear responsibility for our planet and all the living beings that inhabit it. Each of us, as part of this complex ecosystem, should reflect on how we can preserve this fragile balance. Ancient civilizations can serve as a lesson. They achieved great heights, but ultimately disappeared, possibly due to poor resource management or internal conflicts. This should prompt us to reassess our relationship with the world around us and with ourselves. The universe is full of mysteries and possibilities, and as we drift into sleep, it is worth considering what lies hidden in the depths of time and space. For example, the star Proxima Centauri, located 11 light-years away from us, is surrounded by planets, one of which may have conditions suitable for life. Attention to such details can inspire future generations of researchers who will seek answers to questions we have not yet asked. Time, as history shows, moves inexorably forward, and it is our responsibility to determine what we will leave behind. Each day, each thought, each action can become part of this legacy. We must learn from the mistakes of the past to avoid repeating them in the future. Scientific research continues, and each new day brings us new discoveries. For example, just last year, a group of scientists reported findings in the field of genetics that could influence our understanding of human evolution. These data suggest that Homo sapiens was not the only species of humans on the planet. Ancient Neanderthals and other related species may have possessed more complex cultures than we previously thought. Understanding these facts allows us to view the history of humanity from a new perspective. It is worth reflecting on this as you prepare for sleep, contemplating the endless possibilities that our planet and the universe hold.